C. Methodology. Depleted uranium in Bosnia and Herzegovina. 167. D. Appendix D. Dune soil D.1 Background. Uranium in bedrock and soils. Without the presence of uranium, the Earth would be a rather different planet, as heat produced by the radioactive decay of uranium is partly responsible for keeping the planet's core and mantle hot enough for convective flow to occur, in addition to other naturally occurring radionuclides. When measuring isotopic ratios in environmental samples, it is important to realize that uranium may sometimes become depleted, or enriched, in some of its isotopes due to natural processes such as chemical weathering. Uranium is ubiquitous in all rocks, soils, rivers and groundwaters on the Earth's surface. Average values for uranium in rocks are about 2 to 3 mg/kg, ppm, parts per million, and concentrations usually vary slightly, 1 to 30 parts per million, according to rock type. Granites, acid volcanic and carbonatitic rocks often have higher uranium content than other rocks. Certain types of black shales have higher uranium concentrations, such as Chattanooga Shale, 50 to 100 parts per million, alum shales, 50 to 400 parts per million, and phosphor-containing sediments, up to 200 parts per million. These types of rocks cover large areas. A rock containing 3 parts per million uranium holds 8.1 grams of uranium per cubic meter of rock, 1 cubic meter. If a single penetrator is added, the concentration of uranium increases to 308 grams or 115 part per million uranium. For natural waters, uranium is much lower in concentration than in natural rocks, and the variations are higher, typically from less than 1 microgram/kg, ppb, parts per billion, to 100 parts per billion or more. Plutonium, which can be present in ammunition in very low concentrations depending on its fabrication process, is also found worldwide in surface soil, air and water, mainly as a result of contamination, delayed stratospheric fallout, from nuclear weapons tests carried out in the atmosphere until the 1960s. Uranium in surface and subsurface soil. 10 to 35%, up to a maximum of 70%, of a dew penetrator piercing through an armored vehicle will aerosolize into a uranium oxide on impact when the uranium metal dust catches fire. Rand 1999. Most dust particles formed are smaller than 5 micrometers in size and, when released into the atmosphere, spread according to wind direction. By sedimentation, dew particles are deposited on the ground and other various surfaces. Pieces or fragments of metallic dew can also be formed and scattered a corroded penetrator fragment in surface soil around. According to reports from the Nellis Air Force Range, a U.S. training range for dew ordnance, most dew dust is deposited within a distance of 100 meters from the target. Nellis, 1997. This dust consists mainly of uranium oxides. It is estimated that in a real attack scenario, only about 10% of the fired rounds will hit a hard target. Most of the penetrators hitting soft ground will probably penetrate intact. More than 168. Post-conflict environmental assessment. 50 centimeters into the ground and remain there for a long period of time, depending on the weathering, geochemical conditions. Penetrators that impact on a hard ground surface such as concrete, rock or stony soil are, after dispelling their kinetic energy into the superficial ground layer, often found lying on or near the soil surface. They are usually found almost intact, or split into large fragments, and have lost only a small part of their mass through the formation of dust or small uranium particles. D. Analysis results of surface soil samples taken during the earlier UNEP missions shows that topsoil contamination, which was equal or higher than the soil's natural uranium content, could only be found at distances less than a few meters from penetrator impact points in the ground. UNEP, 2001. Around impact points on soft ground, localized dew contamination higher than the detection limit, that is about 30 micrograms per kg soil, could be found for distances less than 20 meters. For impact points on hard ground surfaces, this distance grew to a maximum range of 50 to 100 meters. No widespread dew contamination of topsoil for distances exceeding approximately 100 meters from the impact points was detected. Dew in soil. Uranium or uranium oxide dust as well as fine fragments will initially be deposited on the ground surface. Over time, these will be gradually transported down into the upper soil layer, mostly through physical weathering, rain and wind. Through the dissolution of corrosion products, uranium can also be transported to deeper ground layers. Nevertheless, it is expected that even after many years at least part of the initially deposited uranium could still be found in the surface soil layer. Various impact points from dew munitions. This explains why sampling of surface soil and subsurface soil profiles is very important in order to analyze and understand the distribution of dew contamination at and around identified or assumed attack sites. Through the use of transfer models, results from soil sample analyses are important input parameters in order to estimate doses to inhabitants living at and around contaminated soil surfaces. The results of inductively coupled plasma mass spectrometry, ICP-MS, analyses allow us to identify and measure dew to very low limits and to differentiate it from natural uranium always present in soil. See Appendix C. Soil profile analyses provide insight into the downward transport of dew in subsurface soil. With respect to the food-to-human ingestion pathway, reports state that due to the very low transfer factors of dew from soil into biological material, that is vegetables, and from foodstuffs to human, the expected doses due to ingestion would only be a few microsieverts per year, EU, 2001, WHO, 2001. Even in very conservative scenarios with high consumption of vegetables grown in highly contaminated soils, doses to local inhabitants are insignificant. Inhalation of resuspended dew from contaminated soil in the zone adjacent to the target area, for example where a tank was hit by dew, could result in an annual dew intake of a maximum of 0.660 micrograms, UNEP, 1999, UNEP, 2001, EU, 2001, Keller et al., 2001. The resulting effective dose of 0.07 to 7 microsieverts per year is negligible, compared to the typical dose from natural radiation sources, which for most populations worldwide is in the range of 1 to 10 millisieverts per year. Geochemical aspects of uranium in soil. Most of the 3 tons of depleted uranium penetrators introduced into the Baja environment are buried in soils, not rocks. Consequently, the most likely harm that dew could cause to the local population would be through the dissolution of penetrators by soil water and subsequent transport of the dissolved uranium down through the profile and into the groundwater. Depleted uranium in Bosnia and Herzegovina. 169. D. Table. The uranium could in turn enter water for drinking wells and be a possible cause of radiation and chemical toxicity. UNEP observed that 10 attacks introduced one penetrator into the ground at an interval of 1 to 3 meters along target lines. In addition, U.S. test range data indicate that penetrators entering soft soil can go as deep as 6 to 7 meters depending on velocity and angle of impact and can sometimes fragment. Therefore, as available data are reviewed, it is assumed that each penetrator can contaminate a minimum of 1 cubic meter of soil. Sampled groundwater wells had depths to the groundwater table of 2 meters. Hence, if we imagine in this analysis a column down to the groundwater table with a surface of 1 square meter, each penetrator has the capacity to contaminate 2 cubic meters of soil before the groundwater is affected. The average concentration of uranium in 1 cubic meter of soil, natural uranium plus 1/300 grams penetrator with a density of the soil of 1/600 kilograms/m3, will be 115 parts per million, that is a 38-fold increase over natural uranium in most soils. A penetrator can only slightly contaminate rock, but would more likely contaminate the water in its pore spaces or fractures. The available scientific data for the behavior of uranium in the natural environment is summarized below. Uranium metal is unstable when in contact with oxygen and water, therefore, uranium oxides form on the penetrator or fragment surfaces according to the following reaction. in which uranium is in its tetravalent form. U plus metal. O2 equals UO2 uraninite. However, in contact with the atmosphere, uraninite is unstable and oxidizes to its hexavalent form. UO2 plus 0.5O2 equals UO3. In the presence of water, these oxides are hydrated, contain water. The maximum solubility of oxidized uranium faces forming surface layers on penetrators, for example soapite, UO3.NH2O, at near-neutral pH is about 10 mg/L, ppm. Waters in B were found to have near-neutral pH. In this case, the dissolved uranium was in the uranyline form, UO22+. However, there are many processes in nature which can retard the transport of uranium, sorption to minerals and organics in the soil, co-precipitation with calcite, and reduce, iron to bearing minerals, bacteria, organic matter, the uranium from its hexavalent soluble form to its tetravalent insoluble form, UO2, solubility at neutral pH, pH 7, equals 0.1 micrograms/L. Some confusion about the solubility of uranium oxide still persists today. Here, aqueous uranium is on the form of U4+. Before evaluating the dissolution and transport of penetrators, it is important to consider the composition of soils and rocks. The rocks that make up the visited areas were largely limestone and dolomites. Soil thickness varied from tens of centimeters in some areas, to only a few centimeters in others. Again, depth to the groundwater table was measured to be tilde 2 meters when water was collected from private wells. These wells can thus be considered to be in unconfined, or surface, aquifers with no confining layer that can protect the aquifers from dew. The climate in BA is humid continental with precipitation close to 75 centimeters/year. This precipitation value represents the infiltration rate into surface aquifers. Retrieved penetrators had clear signs of two alteration phases, one black and the other yellow. They had been present in soil for 7-8 years and had grown in size by roughly 100% through the formation of uranium oxides at the penetrator's surface. Analysis of the penetrators from Kosovo using spectroscopy, Raman spectroscopy and X-ray photoelectron spectroscopy, XPS, and scanning electron microscopy with energy dispersive spectrometer, SEM/EDS. 170. Post-conflict environmental assessment indicated that the alteration phases contain only uranium and oxygen, entity. Scintilla levels of other metals known to be present in DU ordnance, iron, titanium, chromium, silicon and aluminum, UNEP, 2000. XPS analyses of a penetrator fragment show uranium in these oxides in both its U6+ and U4+ state. The yellow and black alteration phases are thus uranium oxides. A French study of DU metal found in a test site in southern France used X-ray diffraction studies of the Altera. DU corrosion products are left behind in the soil. Phases observed, also black and yellow, to show that these two phases are UO2 O2s and UO3.2H2O, Soapite, Granson, 2001. The former is likely to be the black alteration phase and the latter the yellow. Since the yellow phase is more abundant on the surface, it is concluded that the black phase, U4+, is an intermediary step in the alteration. From uranium metal, U0, to the fully oxidized yellow phase, U6+. The alteration phases of the penetrators collected in BA had the same colors and were considered to be in the same phases as those found in Kosovo. Investigation of oxidation rates of penetrators found in Kosovo indicated that, in soil solutions, the rate of soapite dissolution is about the same as that of oxidation. This can be concluded by comparing laboratory dissolution studies of soapite in the presence of CO2 from the atmosphere, Duro, 1996, which is 32 grams/300 grams of soapite, assuming that the surface area of the penetrator is 27 square centimeters. If the penetrator fragments into smaller pieces, its surface area is increased and the dissolution rate increases accordingly. It is thus considered likely that all of the penetrators will completely corrode in 25-35 years. Studies of the retrieved penetrators buried in soil from this mission show that roughly 50% of the penetrator had transformed to oxides at the surface. Therefore, it is likely that total corrosion of the penetrator will take longer than estimated from the Kosovo data. As the uranium metal penetrators oxidize, the soils and rocks will initially contain elevated concentrations of soapite rather than solid uranium metal penetrators. With time, the soapite will dissolve and uranium will move downward through the soil. How far the uranium will be transported is limited, however, if the penetrator is embedded in organic-rich soil. Once the uranium comes into contact with organic matter and minerals, less than 100 micrometers, the uranium will initially be sorbed to these minerals. Waite et al., 1994, and organic matter, Nash et al., 1981. This is particularly the case if the pH of the soil is intermediate, pH 6-8. At low pH, no sorption occurs to mineral surfaces as they are positively charged by H+ sorption, and the aqueous uranium is in the form of the uranyl ion, UO22+. At high pH, no sorption occurs either because the dissolved uranyl ion forms negatively charged aqueous complexes with carbonate, CO32, and hydroxide, O, and the mineral surfaces are also negatively charged. Due to the presence of divalent iron in soil minerals, Liger et al., 1999, and bacteria, for example Lavalley et al., 1991, uranium can be reduced to its insoluble quadrivalent form. See for example Ragnar Ersdotter and Charlotte, 2004, a summary of uranium behavior in the natural environment. However, this will only occur where soil profiles have reductive conditions. Such conditions were not observed in the soil profiles sampled. Do in soil. D. Depleted uranium in Bosnia and Herzegovina. 171. D. D.2 Results of measurements. D.2.1 Uranium in surface soil. Natural uranium levels at the investigated sites. The natural uranium concentration of the uncontaminated soils that were sampled at the investigated sites during the UNEP mission was in the range of 1.3 to 4.8 mg U/kg soil. These values are within the normal range of natural uranium concentration of soil. The results of the measurements of the isotopic composition of uranium in these samples were indicative for natural uranium. They proved that, in these samples, there was no DU contamination present above the detection limit, which is in the range of about 2% of the natural uranium content of the soil, equivalent to about 30 micrograms DU per kilogram topsoil. Contamination points. The soil directly at DU penetrator impact points and in their immediate vicinity is the most contaminated. At Honpijsk's artillery storage and barracks, for example, the soil around 2 penetrators lying in undisturbed, grass-covered ground at a depth between 3 to 8 centimeters below the soil surface was investigated. The average contamination in the top 10 centimeters of the soil was 24 grams of DU per kilogram of soil on a surface of 15 by 15 centimeters immediately surrounding an undamaged penetrator without its jacket. Samples Nuke 2002028101 and Nuke 2002-028102. Whereas the average contamination around a whole penetrator still in its jacket was 2.6 grams of DU per kilogram of soil. Samples Nuke 2002028120 and Nuke 2002028121. A dominant part of the DU contamination of these samples consists of the thick layer of DU corrosion products. These had formed on the exposed surface of the penetrators over the 7 years in which they had been present in the soil. These corrosion products remain partly in the ground after removing the DU penetrator. Localized DU contamination of surface soil. The analyses of surface soil samples taken from areas targeted by DU weapons show that there exists local soil contamination around DU penetrator impact points. This localized DU contamination was measurable at the target areas of the former Hadzici tank repair facility, sample Nuke 2002-024008, Hadzici ammunition storage site, samples Nuke 2002-027004 and Nuke 2002-027005, and the Han Pajsk artillery storage and barracks, samples Nuke 2002-028001 and Nuke 2002-028003. At all other sites where surface soil samples were collected, no indication of DU contamination exceeding the detection limit could be found. The detection limit for soil samples is noted above. Inside DU target areas, at distances under 10 to 20 meters to the nearest visible penetrator impact points on hard surfaces, concrete, asphalt, rocks, stony ground, localized DU contamination of topsoil. Surface soil sampling near Hadzici. 172. Post-conflict environmental assessment. Not exceeding 3.8 mg per kilogram could be measured in some of the collected samples. This value is roughly equivalent to the average concentration of natural uranium in soil. The existence of DU in the visible impact holes was confirmed by measuring the beta radiation of DU in the field with portable instruments. In certain places, at distances greater than 50 to 100 meters from confirmed hard surface impact points, the DU concentration was normally less than 0.3 mg per kilogram of soil. In most samples, however, it was even lower than the detection limit. These values are equivalent to less than 10% of the average concentration of natural uranium in soil. Localized DU contamination was measured at 0.1 mg per kilogram of soil in only one soil sample from the eastern area of the Han Pajsk military barracks, sample Nuke 2002-028001, at a distance of about 170 meters to the nearest confirmed impact point. This unusually large distance for localized ground contamination may be explained by local contamination coming from potential undetected penetrator impact points on the soft ground between the sampling point and the nearest confirmed impact points. The two other samples taken from the same area of the site showed no indication of DU contamination exceeding the detection limit, D. DU in soil. Outside the restricted area of the former Hadzici tank repair facility, where public access is unlimited, no signs of DU topsoil contamination could be detected. Localized contamination at the Hadzici ammunition storage site and Han Pajsk artillery storage and barracks was limited to the attacked areas of the sites. No indication of widespread DU contamination could be found at distances exceeding 100 to 200 meters from confirmed penetrator impact points. It is assumed that this is probably true even at distances greater than about 50 to 100 meters. The short distribution distances of DU contamination is thus defined as localized ground contamination. Around impact points on soft surfaces, for example soil without stones, localized DU contamination of topsoil was generally less intense, reaching even smaller distances. For example, in a topsoil sample, Nuke 2002-028004, from Han Pajsk, the DU concentration was below the detection limit at a distance of only 3 meters from an impact point on soft ground. At the edge of a large cobblestone square, yard at the center of the former Hadzici tank repair facility, 2 sand samples were collected on a surface where rainwater runoff had deposited a roughly 3 centimeters thick layer of sand and dust from the yard. Samples Nuke 2002-024011 and Nuke 2002-024012. Within a distance of about 30 meters, a lot of penetrator impact points were identified on this cobblestone surface. Under these circumstances, a certain local enrichment of DU combined with the deposited sand at some distance from the surface of the original deposition can be anticipated. The DU concentration of this material was 30 mg per kilogram, or equivalent to approximately 10 times the natural uranium concentration. D.2.2 Dew in subsurface soil. Contamination of subsurface soil immediately below the impact points of 3 dew penetrators at Hanpajsk was investigated by taking soil profile samples down to a depth of 60 to 65 centimeters below the soil surface. The penetrators were lying in undisturbed, grass-covered ground at a depth of 3 to 8 centimeters below the soil surface. The average contamination in the 5 cm layer of soil around an intact penetrator without its jacket was measured at 45 grams of dew per kilogram of soil on a surface of 15 by 15 cm immediately surrounding it. Samples Nuke 20020281001 to -112. The average contamination in the layer around a whole penetrator remaining in its jacket was only 4.7 grams of dew per kilogram of soil. Samples Nuke 200202810 to -132. The difference is probably due to the penetrator's surface being partly protected from corrosive attack by the jacket. The contamination of these samples consists mainly of the thick layer of dew corrosion products, which formed at the exposed surface of the penetrators over the last 7 years in the soil. Penetrators without their jackets have, in that period, lost roughly 25% of their metallic mass by corrosion. Depleted uranium in Bosnia and Herzegovina. 173. D. Within the first 10 centimeters of soil below the penetrator, dew concentrations diminished by about 2 orders of magnitude to values of 230 and 69 mg/kg soil respectively, figure D.1, profile 1 and 2. Respectively. Within the next 30 centimeters, this concentration diminished by roughly another 3 orders of magnitude to values of 0.09 mg/kg of soil and below. The detection limit, less than 0.06 mg/kg of soil, respectively. Finally, the dew concentration diminished by almost 6 orders of magnitude to values that were below the detection limit of the analytical method for soil within 40 centimeters below the penetrators. No traces of dew could be detected in layers deeper than 40 centimeters. Based on these results, it is concluded that the mobility of dew corrosion products is very low in the type of soil found at Hanpajsk. A full dew bullet was retrieved from Hanpajsk. Figure D.1 Concentration of dew in soil profiles from Hanpajsk. D.3 Uranium depth distribution and extraction experiments. Soil profile description. One of the sampled profiles from Hanpajsk was analyzed through extraction experiments. The sampled soil profile consisted of 3 distinct soil horizons, which may have been disturbed prior to the intrusion of the penetrator, as it was adjacent to a built-up road track. The 174. Post-conflict environmental assessment profile consisted of a surface organic layer, L, unorganic rich silty sand layer, A, a clay horizon, BS1, and a horizon of silty sand textured matrix, with downward coarsening clastic content, BS2. Ochre-colored iron oxidation and organic matter smearing was evident in the clay and sand horizons. Clasts were dominantly calcareous. D.2. D.3. D.4. D. Dew in soil. Figure D.2 shows the soil profile midway through the sample collection, figure D.3 shows the soil profile after sample collection and figure D.4 shows the soil description log, the depths at which samples were collected and those samples which were later analyzed. Total uranium, 238U, total fusion and residue fusion. In order to measure the total uranium content of the soil samples collected, total fusions were performed. In addition, to evaluate the recovery of uranium throughout the extraction experiment procedure, the soil residue remaining at the end of the 6 extraction stages was also fused. Fusion method and measurements by HRIC-PEMAS are outlined under SPE's laboratory in Appendix C. Depth distribution results. The quantitative analysis for total fusion 238U concentration indicates that the uranium predominantly occurs within the top 10 centimeters of the soil profile. Of the total 238U measured in the profile, 87% occurs within the top 10 centimeters. However, the 238U concentration remains above the average soil uranium concentration, 1 to 10 mg/kg, down to a depth of 40 centimeters. As uranium isotope ratio studies have not yet been performed on this particular soil profile, it is not possible by this means to confirm the elevated uranium concentrations as depleted uranium. Depleted uranium in Bosnia and Herzegovina. 175. D. However, using the assumption that measured uranium concentrations exceeding the average soil uranium concentration of 1 to 10 mg/kg are due to uranium mobilization from the penetrator, it is possible to infer that depleted uranium has been mobilized down to a depth of 40 centimeters. The uranium mobility may in fact extend down below this depth, however, as figure D.3 shows. The samples collected from 40 to 47.5 centimeters were not analyzed. Given the uranium mobilization to a depth of 40 centimeters within a period of 7 years, the rate of movement of uranium can be estimated as ~5 centimeters/year. This rate of mobility varies with soil composition. For example, the porosity and permeability of the soil, that is, dense clay horizons have reduced permeability, while a horizon with a sand matrix has higher permeability, as well as the organic matter content and mineralogical composition, provide binding sites for the uranium. Loss on ignition, LOI, measurements were performed to establish the organic content down the profile. As figure D.5 illustrates, the organic content of the soil varies between 1 to 7%, with the highest content occurring within the top layers, 15 centimeters, of the soil, as expected. This depth corresponds with the depth of maximum uranium concentration. However, organic matter may also increase the mobility of uranium, through the formation of humic acid complexes, which can be mobilized down the profile. The movement of trace metals by this means tends to occur in acidic soils. As this soil was neutral, it is unlikely that the formation of organouranium metal complexes are a significant cause of uranium mobility. Figure D.5 Total uranium measured in soil profiles. Sequential extraction results. As the results from the measurement of total 238U concentration confirm, the 238U concentration decreases with depth. However, the sequentially extracted uranium concentrations infer that the proportion of uranium associated with each geochemical phase varies down the profile. As figure D.5 shows, in the near-surface horizons where the penetrator was embedded, the dominant fraction is the readily exchangeable fraction. At lower levels in the profile, for example, at 37.5 to 40 centimeters, the carbonate-bound uranium dominates. This change in proportion down the profile is seen more clearly in figures E.I. 176. Post-conflict environmental assessment. Figure E, Figure F. D. Figure G. Dew in soil. Figure H. Figure I. Figures F, I, show the proportion of 238U recovered from each extraction step at depths of F, 0 to 4 centimeters, G, 4 to 10 centimeters, H, 14 to 16 centimeters and I, 37.5 to 40 centimeters. Depleted uranium in Bosnia and Herzegovina. 177. D. The dominance of the readily exchangeable fraction in the upper layers of the soil is most likely due to the constant replenishment of uranium from the penetrator to the exchange sites at the surfaces of organic matter and clay minerals, countering the removal of uranium from these sites by leaching as water infiltrates down through the soil. At lower levels in the soil, further from the penetrator, where the concentration of uranium is considerably lower, figures D and E, this replenishment does not occur to the same degree. Therefore, Larger proportions of uranium are associated with the geochemical phases that bind uranium more strongly, that is carbonates and organic matter. Uranium held by these binding sites is not so easily removed by percolating groundwater. Soil pH is neutral and remains fairly constant throughout the profile, between pH 7.4-7.8. These conditions favor the sorption of uranium to the surfaces of soil organic matter, iron oxides and other minerals. The organic content in the upper layers of the profile, -7%, down to 15 cm depth, contributes significantly to the cation exchange capacity, SEC, of these soil layers, that is a measure of the number of exchange sites to which the readily exchangeable fraction is bound. Between 25 to 90% of the total SEC of the top layers of mineral soils is thought to be associated with the organic matter content, Stevenson, 1985. Therefore, the organic content within the top layers of the profile plays an important role in providing sites to which uranium can bind. The SEC contribution by organic matter increases with pH, and is therefore greater in a neutral soil, such as the one studied here compared to a more acidic soil, a forest soil. Such soils of lower pH are more likely to result in the downward mobilization of uranium through the formation of uranium-humic complexes. Finally, the profile appeared fairly well oxidized, as indicated by the visible presence of ochre-colored Fe3+ oxidation products throughout the 60 cm profile. Therefore, the immobilization of uranium through reduction of U6+ to U4+ is unlikely. However, this may occur during fluctuations of the water table, causing more reduced conditions. D.4 Summary of the findings. Penetrators hitting the ground result in contamination points of several grams per kilogram of soil. However, the extent and distribution of the contamination is low, roughly 15 by 15 centimeters, and restricted to a mass of a few kilograms of soil in the shot hole. An additional contamination of tens of grams due per kilogram of soil can occur after a number of years through the corrosion of penetrators laying in soil. Due to the rather low mobility of dew corrosion products in the type of soil sampled to date in BIH, the extent and distribution of the major part of subsurface contamination is expected to remain restricted to a volume of about 20 kilograms of soil in the shot hole. Penetrators hitting a hard ground surface, concrete, asphalt, rocks, stony ground, give rise to localized dew contamination of the topsoil around the site of impact, with concentrations decreasing as distance increases. Concentrations of dew in topsoil exceeding 10 times the natural concentration of uranium in soil are generally not observed outside the immediate surroundings of the impact points, 1 to 2 meters. Concentrations exceeding the natural concentration of uranium in soil are not expected at distances greater than about 10 to 20 meters from impact points. Measurable dew contamination of topsoil is generally restricted to a maximum distance of about 150 meters from confirmed penetrator impact points. Widespread dew contamination at distances of more than 200 meters from confirmed impact points of penetrators is not expected. That is, ground contamination remains localized. 178. Post-conflict environmental assessment. Around penetrator impact points on soft ground surfaces, localized dew contamination of topsoil is expected to be less intense and have a lower distribution than on hard surfaces. Although current literature states that widespread dew contamination occurs once penetrators have hit heavily armored vehicles at attacked sites, no signs of such contamination could be found based on the sampling procedure used on this mission or previous UNEP studies. Outside the fenced area of the former Hadzisi tank repair facility, no signs of a dew contamination of the topsoil could be detected. The localized contamination at the Hadzisi ammunition storage and Hanpajsk military barracks is clearly limited to below 200 meters from the attacked areas of the sites. These results generally confirm the major findings of the earlier UNEP missions to Kosovo and Serbia and Montenegro. Due to the very limited extent of the contamination zones, defined by dew concentrations in topsoil above the natural uranium concentrations, a health risk for the local population can hardly be expected, either from living close to the aforementioned sites or by visiting these areas. Based on the results from the measurement of total 238U concentration, it is clear that the 238U concentration decreases with depth. However, the sequentially extracted uranium concentrations infer that the proportion of uranium associated with each geochemical phase varies down the profile. Figure D.5 shows, in the near-surface horizons where the penetrator was embedded, the dominant fraction is the readily exchangeable fraction. While at lower levels in the profile, for example, at 37.5 to 40 centimeters, the carbonate-bound uranium dominates. The soil pH is neutral and remains fairly constant down through the profile, between pH 7.4-7.8. These conditions favor the sorption of uranium to the surfaces of soil organic matter, iron oxides and minerals. The organic content in the upper layers of the profile, 7%, down to 15 cm depth, contributes significantly to the cation exchange capacity, SEC, of these soil layers. That is a measure of the number of exchange sites to which the readily exchangeable fraction is bound. Between 25 to 90% of the total SEC of the top layers of mineral soils is thought to be associated with the organic matter content, Stevenson, 1985. Therefore, the organic content within the top layers of the profile plays an important role in providing sites to which uranium can bind. The SEC contribution by organic matter increases with pH, and is therefore greater in a neutral soil, such as this compared to a more acidic soil, for example a forest soil. Such soils of lower pH are more likely to result in the downward mobilization of uranium through the formation of uranium-humic complexes. The profile appeared fairly well oxidized, as indicated by the visible presence of ochre-colored Fe3+ oxidation products. Therefore, the immobilization of uranium through reduction of U6+ to U4+ is unlikely. However, this may occur during fluctuations of the water table, causing more reduced conditions. Dew in soil. D. Depleted uranium in Bosnia and Herzegovina. 179. D. Table D.1 Surface soil samples. Sample code. Nuke 20020240001 Nuke 20020240002 Nuke 20020240003 Nuke 20020240004 Nuke 20020240005 Nuke 20020240006 Nuke 20020240007 Nuke 20020240008 Nuke 20020240009 Nuke 20020240010 Nuke 20020240011 Nuke 20020240012 Nuke 20020250001 Nuke 20020250002 Nuke 20020250003 Nuke 20020250004 Nuke 20020260001 Nuke 20020260002 Nuke 20020270001 Nuke 20020270002 Nuke 20020270003 Nuke 20020270004 Nuke 20020270005 Nuke 20020280001 Nuke 20020280002 Nuke 20020280003 Nuke 20020280004 Nuke 20020280006 Nuke 20020280007 Nuke 20020300001 Nuke 2002030002. Nuke 2002030003. Nuke 2002030004. Nuke 2002030005. Nuke 2002031001. Nuke 2002031002. Nuke 2002031003. Nuke 2002032001. Nuke 2002032002. Nuke 2002033001. Nuke 2002033002. Nuke 2002033003. Nuke 2002034001. Nuke 2002034002. Nuke 2002035001. Nuke 2002035002. Sampling site. Coordinates UTM-34T. Sample type. Herzegovina, Tank Repair Facility BP 74418, 56 345 Soil, 10 course, 25 SQM. Herzegovina, Tank Repair Facility BP 74141, 56 496 Soil, 10 course, 25 SQM. Herzegovina, Tank Repair Facility BP 74456, 56 161 Soil, 10 course, 25 SQM. Herzegovina, Tank Repair Facility BP 73850, 56 303 Soil, 10 course, 25 SQM. Herzegovina, Tank Repair Facility BP 73797, 56 502 Soil, 10 course, 25 SQM. Herzegovina, Tank Repair Facility BP 74117, 56 107 Soil, 10 course, 25 SQM. Herzegovina, Tank Repair Facility BP 74115, 56 310 Soil, 10 course, 25 SQM. Herzegovina, Tank Repair Facility BP 74154, 56 426 Soil, 10 course, 25 SQM. Herzegovina, Tank Repair Facility BP 74208, 56 207 Soil, 10 course, 25 SQM. Herzegovina, Tank Repair Facility BP 73945, 56 470 Soil, 10 course, 25 SQM. Herzegovina, Tank Repair Facility BP 74025, 56 386. Sand, shovel. Herzegovina, Tank Repair Facility BP 74051, 56 398. Sand, shovel. Lukovica, former barracks BP 88 222, 55 799 Soil, 10 course, 25 SQM. Lukovica, former barracks BP 88 439, 56 016 Soil, 10 course, 25 SQM. Lukovica, former barracks BP 88 608, 55 676 Soil, 10 course, 25 SQM. Lukovica, former barracks BP 88 527, 55 883 Soil, 10 course, 25 SQM. Jeljugovici, T55 Tank BP 81 838, 61 784 Soil, 10 course, 25 SQM. Jeljugovici, T55 Tank BP 81 811, 61 800 Soil, 10 course, around ruin. Herzegovina, Barracks. BP 75 285, 54 682 Soil, 10 course, 25 SQM. Herzegovina, Barracks. BP 75 434, 54 623 soil, 10 course, 25 SQM. Hadsisi, Barracks. BP 75 367, 54 840 soil, 10 course, 25 SQM. Hadsisi, Ammunition Storage Area. BP 76 577, 53 496 soil, 10 course, 25 SQM. Hadsisi, Ammunition Storage Area. BP 76 603, 53 432 soil, 10 course, 5 SQM. Hanpijsk, Barracks CP 35 969, 84 314 soil, 10 course, 25 SQM. Hanpijsk, Barracks CP 35 595, 84 331 soil, 10 course, 25 SQM. Hanpijsk, Barracks CP 35 681, 84 350 soil, 10 course, 25 SQM. Hanpijsk, Barracks. CP 35 468, 84 445. Soil, 10 course, 3 meters around penetrator. Hanpijsk, Barracks CP 36060, 84 244 soil, 10 course, 25 SQM. Hanpijsk, Barracks CP 35 909, 84 409 soil, 10 course, 25 SQM. Vogoska, Ammunition Production Site. BP 88 927, 64 949 soil, 10 course, 25 SQM. Vogoska, Ammunition Production Site. BP 89 334, 65067 soil, 10 course, 25 SQM. Vogoska, Ammunition Production Site. BP 89 185, 65 195 soil, 10 course, 25 SQM. Vogoska, Ammunition Production Site. BP 90088, 66 734 soil, 10 course, 25 SQM. Vogoska, Ammunition Production Site. BP 91 215, 67 689 soil, 10 course, 25 SQM. Kalinovic, Water Reservoir BP 93 325, 2622 soil, 10 course, 25 SQM. Kalinovic, Ammunition Destruction Zone. BP 91 586, 18 312 soil, 10 course, 25 SQM. Kalinovic, Ammunition Destruction Zone. BP 91 714, 18 349 soil, 10 course, 25 SQM. Foka, Bridge, Srbinj, CP 2345, 2444 soil, 10 course, 25 SQM. Foka, Bridge, Srbinj, CP 2545, 2492 soil, 10 course, 25 SQM. Ustakolina, Barracks. CP 19356, 29118 soil, 10 course, 25 SQM. Ustakolina, Barracks. CP 2198, 28000 soil, 10 course, 25 SQM. Ustakolina, Barracks. CP 2470, 27780 soil, 10 course, 25 SQM. Pale, Karan Barracks CP 05514, 52 297 soil, 10 course, 25 SQM. Pale, Karan Barracks CP 05304, 52 293 soil, 10 course, 25 SQM. Bielasnoka Plateau, Ammunition Destruction Zone. BP 61 932, 42 464. Soil, 10 course, 25 SQM. Bielasnoka Plateau, Ammunition Destruction Zone. BP 61 877, 42,288. Soil, 10 cores, 25 sqm. Depth, 0 to 5 centimeters, 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 0 to 5 centimeters. 0 to 5 centimeters, 0 to 5 centimeters, 0 to 3 centimeters, 0 to 3 centimeters, 0 to 5 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 centimeters. 180. Post-conflict environmental assessment. Table D.2 Concentration of uranium isotopes and in surface soil samples, mg/kg. Sample code U238, mg/kg. U234, mg/kg. U235, mg/kg. U236, mg/kg. U., mg/kg. U235% due of U238 ratio total U. Nuke 20020240001. 4.43 E plus 0. Plus minus. 7.68 E minus 2. 2.18 E minus 4. Plus minus. 3.71 E minus 5. 3.22 E minus 2 plus minus 8.68 E minus 4. 4.00 E minus 5 4.47 E plus 0 plus minus 7.68 E minus 2 7.273 E minus 32. Nuke 2,002,024.002. 4.74 E plus 0. Plus minus. 8.61 E minus 2. 2.32 E minus 4. Plus minus. 3.79 E minus 5. 3.43 E minus 2 plus minus 7.89 E minus 4. 4.00 E minus 5 4.77 E plus 0 plus minus 8.61 E minus 2 7.247 E minus 32. Nuke 20020240003. 2.77 E plus 0. Plus minus. 5.62 E minus 2. 1.54 E minus 4. Plus minus. 3.18 E minus 5. 2.01 E minus 2 plus minus 5.11 E minus 4. 3.00 E minus 5 2.79 E plus 0 plus minus 5.62 E minus 2 7.264 E minus 32. Nuke 20020240004. 3.77 E plus 0. Plus minus. 6.47 E minus 2. 1.92 E minus 4. Plus minus. 3.45 E minus 5. 2.72 E minus 2 plus minus 6.42 E minus 4. 3.00 E minus 5 3.79 E plus 0 plus minus 6.47 E minus 2 7.247 E minus 32. Nuke 20020240005. 3.81 E plus 0. Plus minus. 7.32 E minus 2. 1.83 E minus 4. Plus minus. 3.41 E minus 5. 2.76 E minus 2 plus minus 6.44 E minus 4. 4.00 E minus 5 3.83 E plus 0 plus minus 7.32 E minus 2 7.251 E minus 32. Nuke 20020240006. 4.01 E plus 0. Plus minus 6.68 E minus 2. 2.03 E minus 4. Plus minus 3.53 E minus 5. 2.92 E minus 2 plus minus 6.51 E minus 4. 4.00 E minus 5 4.04 E plus 0 plus minus 6.68 E minus 2 7.278 E minus 3 2. Nuke 20020240007. 3.87 E plus 0. Plus minus 6.52 E minus 2. 2.01 E minus 4. Plus minus 2.88 E minus 5. 2.77 E minus 2 plus minus 7.26 E minus 4. 4.00 E minus 5 3.90 E plus 0 plus minus 6.52 E minus 2 7.152 E minus 3 2. Nuke 20020240008. 3.72 E plus 0. Plus minus 6.57 E minus 2. 1.83 E minus 4. Plus minus 3.05 E minus 5. 2.58 E minus 2 plus minus 5.99 E minus 4. 4.00 E minus 5 3.74 E plus 0 plus minus 6.57 E minus 2 6.954 E minus 3. 6. Nuke 20020240009. 3.41 E plus 0. Plus minus 6.41 E minus 2. 1.77 E minus 4. Plus minus 3.03888 E minus 5. 2.47 E minus 2. Plus minus 1.77 E minus 3. 4.00 E minus 5 3.44 E plus 0 plus minus 6.41 E minus 2 7.218 E minus 3 2. Nuke 20020240010. 3.67 E plus 0. Plus minus 5.81 E minus 2. 1.82 E minus 4. Plus minus 3.33 E minus 5. 2.65 E minus 2 plus minus 7.70 E minus 4. 4.00 E minus 5 3.70 E plus 0 plus minus 5.81 E minus 2 7.205 E minus 3 2. Nuke 20020240011. 1.26 E plus 1. Plus minus 2.12 E minus 1. 1.61 E minus 4. Plus minus 2.55 E minus 5. 3.37 E minus 2 plus minus 7.73 E minus 4 3.04 E minus 4 plus minus 3.71 E minus 5 1.26 E plus 1 plus minus 2.12 E minus 1 2.683 E minus 3. 87. Nuke 20020240012. 3.20 E plus 1. Plus minus 6.74 E minus 1. 2.99 E minus 4. Plus minus 3.93 E minus 5. 7.41 E minus 2 plus minus 2.05 E minus 3 8.61 E minus 4 plus minus 1.09 E minus 4 3.21 E plus 1 plus minus 6.74 E minus 1 2.317 E minus 3. 94. Nuke 20020250001. 2.11 E plus 0. Plus minus. 3.85 E minus 2. 1.12 E minus 4. Plus minus. 1.81154 E minus 5. 1.53 E minus 2. Plus minus. 3.40 E minus 4. 3.00 E minus 5. 2.13 E plus 0 plus minus 3.85 E minus 2. 7.244 E minus 3 2. Nuke 20020250002. 2.98 E plus 0. Plus minus. 5.24 E minus 2. 1.64 E minus 4. Plus minus. 2.2268 E minus 5. 2.16 E minus 2 plus minus 4.95 E minus 4. 3.00 E minus 5. 3.00 E plus 0 plus minus 5.24 E minus 2. 7.236 E minus 3 2. Nuke 20020250003. 2.76 E plus 0. Plus minus. 4.89 E minus 2. 1.47 E minus 4. Plus minus. 2.28499 E minus 5. 2.00 E minus 2. Plus minus. 4.63 E minus 4. 3.00 E minus 5. 2.78 E plus 0 plus minus 4.89 E minus 2. 7.251 E minus 3 2. Nuke 20020250004. 2.52 E plus 0. Plus minus. 4.91 E minus 2. 1.36 E minus 4. Plus minus. 1.95353 E minus 5. 1.82 E minus 2. Plus minus. 4.39 E minus 4. 3.00 E minus 5. 2.53 E plus 0 plus minus 4.92 E minus 2. 7.244 E minus 3 2. Nuke 20020260001. 1.78 E plus 0. Plus minus. 3.18 E minus 2. 9.14739 E minus 5. Plus minus. 1.9308 E minus 5. 1.29 E minus 2 plus minus 3.73 E minus 4. 2.00 E minus 5. 1.79 E plus 0 plus minus 3.18 E minus 2. 7.265 E minus 3 2. Nuke 20020260002. 1.51 E plus 0. Plus minus. 3.72 E minus 2. 7.63188 E minus 5. Plus minus. 1.56208 E minus 5. 1.10 E minus 2. Plus minus. 3.22 E minus 4. 2.00 E minus 5. 1.52 E plus 0 plus minus 3.72 E minus 2. 7.284 E minus 3 2. Nuke 20020270001. 2.97 E plus 0. Plus minus. 4.65 E minus 2. 1.54 E minus 4. Plus minus. 2.15589 E minus 5. 2.15 E minus 2. Plus minus. 4.95 E minus 4. 3.00 E minus 5. 3.00 E plus 0 plus minus 4.65 E minus 2. 7.233 E minus 3 2. Nuke 20020270002. 2.60 E plus 0. Plus minus. 5.26 E minus 2. 1.35 E minus 4. Plus minus 2.33 E minus 5. 1.88 E minus 2 plus minus 4.39 E minus 4. 3.00 E minus 5 2.62 E plus 0 plus minus 5.26 E minus 2 7.244 E minus 3 2. Nuke 20020270003. 3.08 T plus 0. Plus minus 5.16 E minus 2. 1.63 E minus 4. Plus minus 2.58 E minus 5. 2.23 E minus 2 plus minus 4.52 E minus 4. 3.00 E minus 5 3.10 E plus 0 plus minus 5.16 E minus 2 7.238 E minus 3 2. Nuke 20020270004. 6.75 E plus 0. Plus minus 1.07 E minus 1 1.84 E minus 4. Plus minus 3.43 E minus 5. 2.95 E minus 2. Plus minus 6.86 E minus 4. 1.11 E minus 4. Plus minus 1.85226 E minus 5. 6.78 E plus 0. Plus minus 1.07 E minus 1. 4.362 E minus 3. 55. Nuke 20020270005. 3.40 E plus 0. Plus minus 5.61 E minus 2. 1.69 E minus 4. Plus minus 2.89 E minus 5. 2.41 E minus 2 plus minus 5.58 E minus 4. 3.00 E minus 5 3.43 E plus 0 plus minus 5.61 E minus 2 7.084 E minus 3. 3. Nuke 20020280001. 2.51 E plus 0. Plus minus 4.28 E minus 2. 1.30 E minus 4. Plus minus 2.16 E minus 5. 1.77 E minus 2 plus minus 3.75 E minus 4. 3.00 E minus 5 2.53 E plus 0 plus minus 4.28 E minus 2 7.043 E minus 3. 4. Nuke 20020280002. 2.41 E plus 0. Plus minus 4.47 E minus 2. 1.35 E minus 4. Plus minus 2.15 E minus 5. 1.75 E minus 2 plus minus 4.44 E minus 4. 3.00 E minus 5 2.43 E plus 0 plus minus 4.47 E minus 2 7.246 E minus 3 2. Nuke 20020280003. 2.08 T plus 0. Plus minus 3.46 E minus 2. 1.12 E minus 4. Plus minus 1.82 E minus 5. 1.42 E minus 2 plus minus 3.78 E minus 4. 3.00 E minus 5 2.09 E plus 0 plus minus 3.46 E minus 2 6.829 E minus 3. 8. Nuke 20020280004. 2.56 E plus 0. Plus minus 4.31 E minus 2. 1.35 E minus 4. Plus minus 2.03 E minus 5. 1.84 E minus 2 plus minus 5.24 E minus 4. 3.00 E minus 5 2.57 E plus 0 plus minus 4.31 E minus 2 7.216 E minus 32. Nuke 20020280006. 2.43 E plus 0. Plus minus 4.12 E minus 2. 1.28 E minus 4. Plus minus 2.26 E minus 5. 1.75 E minus 2 plus minus 3.64 E minus 4. 3.00 E minus 5 2.45 E plus 0 plus minus 4.12 E minus 2 7.208 E minus 32. Nuke 2,002,028.007. 1.34 E plus 0. Plus minus 2.54 E minus 2. 6.57 E minus 5. Plus minus 1.46 E minus 5. 9.70 E minus 3 plus minus 2.68 E minus 4. 3.00 E minus 5 1.35 E plus 0 plus minus 2.54 E minus 2 7.256 E minus 32. Nuke 20020300001. 1.78 E plus 0. Plus minus 3.86 E minus 2. 9.69 E minus 5. Plus minus 1.96 E minus 5. 1.30 E minus 2 plus minus 3.96 E minus 4. 2.00 E minus 5 1.80 E plus 0 plus minus 3.86 E minus 2 7.329 E minus 32. Nuke 2,002,030.002. 1.79 E plus 0. Plus minus 4.90 E minus 2. 9.81 E minus 5. Plus minus 1.64 E minus 5. 1.30 E minus 2 plus minus 4.42 E minus 4. 2.00 E minus 5 1.80 E plus 0 plus minus 4.90 E minus 2 7.268 E minus 32. Nuke 2,002,030.003. 2.01 E plus 0. Plus minus 4.02 E minus 2. 1.09 E minus 4. Plus minus 1.74 E minus 5. 1.47 E minus 2 plus minus 4.01 E minus 4. 2.00 E minus 5 2.02 E plus 0 plus minus 4.02 E minus 2 7.313 E minus 32. Nuke 2,002,030.004. 1.56 C plus 0. Plus minus 3.90 E minus 2. 8.45 E minus 5. Plus minus 1.74 E minus 5. 1.14 E minus 2 plus minus 3.37 E minus 4. 2.00 E minus 5 1.57 E plus 0 plus minus 3.90 E minus 2 7.332 E minus 32. Nuke 2,002,030.005. 1.80 E plus 0. Plus minus 3.14 E minus 2. 8.84 E minus 5. Plus minus 1.92 E minus 5. 1.31 E minus 2 plus minus 3.10 E minus 4. 2.00 E minus 5 1.81 E plus 0 plus minus 3.14 E minus 2 7.278 E minus 32. Nuke 2,002,031.001. 4.52 E plus 0. Plus minus 7.63 E minus 2. 2.10 E minus 4. Plus minus 4.56 E minus 5. 3.27 E minus 2 plus minus 7.08 E minus 4. 4.00 E minus 5 4.55 E plus 0 plus minus 7.63 E minus 2 7.249 E minus 3 2. Nuke 2,002,031,002. 3.14 E plus 0. Plus minus 6.14 E minus 2. 1.67 E minus 4 plus minus 3.28 E minus 5. 2.29 E minus 2 plus minus 5.64 E minus 4. 3.00 E minus 5 3.16 E plus 0 plus minus 6.14 E minus 2 7.300 E minus 3 2. Nuke 2,002,031,003. 3.11 E plus 0. Plus minus 5.05 E minus 2. 1.59 E minus 4 plus minus 3.37512 E minus 5. 2.26 E minus 2. Plus minus 5.28 E minus 4. 3.00 E minus 5 3.13 E plus 0 plus minus 5.05 E minus 2 7.287 E minus 3 2. Nuke 2,002,032,001. 3.10 E plus 0. Plus minus 5.43 E minus 2. 1.68 E minus 4 plus minus 2.69 E minus 5. 2.26 E minus 2 plus minus 5.77 E minus 4. 3.00 E minus 5 3.13 E plus 0 plus minus 5.44 E minus 2 7.293 E minus 3 2. Nuke 2,002,032,002. 2.56 E plus 0. Plus minus 4.41 E minus 2. 1.39 E minus 4 plus minus 2.02 E minus 5. 1.87 E minus 2 plus minus 3.95 E minus 4. 3.00 E minus 5 2.58 E plus 0 plus minus 4.41 E minus 2 7.310 E minus 3 2. Nuke 2,002,033,001. 2.50 E plus 0. Plus minus 4.55 E minus 2. 1.39 E minus 4. Plus minus 2.20 E minus 5. 1.81 E minus 2 plus minus 4.69 E minus 4. 3.00 E minus 5 2.52 E plus 0 plus minus 4.55 E minus 2 7.245 E minus 3 2. Nuke 2,002,033,002. 2.50 E plus 0. Plus minus 4.02 E minus 2. 1.38 E minus 4. Plus minus 2.96 E minus 5. 1.82 E minus 2 plus minus 3.77 E minus 4. 3.00 E minus 5 2.52 E plus 0 plus minus 4.02 E minus 2 7.285 E minus 3 2. Nuke 2,002,033,003. 2.49 E plus 0. Plus minus 4.26 E minus 2. 1.42 E minus 4. Plus minus 2.06 E minus 5. 1.81 E minus 2 plus minus 3.82 E minus 4. 3.00 E minus 5 2.51 E plus 0 plus minus 4.26 E minus 2 7.280 E minus 3 2. Nuke 2,002,034,001. 3.10 E plus 0. Plus minus 5.00 E minus 2. 1.59 E minus 4. Plus minus 2.25 E minus 5. 2.25 E minus 2 plus minus 6.06 E minus 4. 3.00 E minus 5 3.12 E plus 0 plus minus 5.00 E minus 2 7.279 E minus 3 2. Nuke 2,002,034,002. 2.63 E plus 0. Plus minus 5.16 E minus 2. 1.43 E minus 4. Plus minus 2.54 E minus 5. 1.92 E minus 2 plus minus 5.27 E minus 4. 3.00 E minus 5 2.65 E plus 0 plus minus 5.16 E minus 2 7.303 E minus 3 2. Nuke 2,002,035,001. 1.71 E plus 0. Plus minus 4.51 E minus 2. 8.07 E minus 5. Plus minus 1.76 E minus 5. 1.25 E minus 2 plus minus 4.69 E minus 4. 3.00 E minus 5 1.73 E plus 0 plus minus 4.51 E minus 2 7.278 E minus 3 2. Nuke 2,002,035,002. 2.57 E plus 0. Plus minus 7.03 E minus 2. 1.29 E minus 4. Plus minus 2.36 E minus 5. 1.87 E minus 2 plus minus 7.95 E minus 4. 3.00 E minus 5 2.59 E plus 0 plus minus 7.03 E minus 2 7.267 E minus 3 2. Do in soil. D. Depleted uranium in Bosnia and Herzegovina. 181. D. Table D.3 Activity of uranium isotopes and do in surface soil samples, BQ/kg. Sample code U238, MBGQ//KGG. U234, MBGQ//KKGG. U235, MBQG//KKGG. U236, MBQG//KKGG. U.MBQG//KKGG. U235% do of U238 ratio total U. Nuke 20020240001. 5.52 E plus 1. Plus minus 9.56 E minus 1. 5.04 E plus 1. Plus minus 8.56 E plus 0. 2.58 E plus 0. Plus minus 6.94 E minus 2. 9.59 E minus 2 1.08 E plus 2 plus minus 8.61 E plus 0 7.273 E minus 3 2. Nuke 20020240002. 5.90 E plus 1. Plus minus 1.07 E plus 0. 5.35 E plus 1. Plus minus 8.76 E plus 0. 2.74 E plus 0. Plus minus 6.31 E minus 2. 9.59 E minus 2 1.15 E plus 2 plus minus 8.83 E plus 0 7.247 E minus 3 2. Nuke 20020240003. 3.44 E plus 1. Plus minus 7.00 E minus 1. 3.56 E plus 1. Plus minus 7.33 E plus 0. 1.60 E plus 0. Plus minus 4.09 E minus 2. 7.19 E minus 2 7.16 E plus 1 plus minus 7.37 E plus 0 7.264 E minus 32. Nuke 20020240004. 4.68 E plus 1. Plus minus 8.05 E minus 1. 4.43 E plus 1. Plus minus 7.96 E plus 0. 2.18 E plus 0. Plus minus 5.13 E minus 2. 7.19 E minus 2 9.33 E plus 1 plus minus 8.00 E plus 0 7.247 E minus 32. Nuke 20020240005. 4.74 E plus 1. Plus minus 9.10 E minus 1. 4.22 E plus 1. Plus minus 7.87 E plus 0. 2.21 E plus 0. Plus minus 5.16 E minus 2. 9.59 E minus 2 9.18 E plus 1 plus minus 7.92 E plus 0 7.251 E minus 32. Nuke 20020240006. 4.99 E plus 1. Plus minus 8.31 E minus 1. 4.70 E plus 1. Plus minus 8.15 E plus 0. 2.33 E plus 0. Plus minus 5.21 E minus 2. 9.59 E minus 2 9.92 E plus 1 plus minus 8.20 E plus 0 7.278 E minus 32. Nuke 20020240007. 4.81 E plus 1. Plus minus 8.11 E minus 1. 4.65 E plus 1. Plus minus 6.65 E plus 0. 2.21 E plus 0. Plus minus 5.81 E minus 2. 9.59 E minus 2 9.68 E plus 1 plus minus 6.70 E plus 0 7.152 E minus 32. Nuke 20020240008. 4.62 E plus 1. Plus minus 8.17 E minus 1. 4.23 E plus 1. Plus minus 7.05 E plus 0. 2.07 E plus 0. Plus minus 4.79 E minus 2. 9.59 E minus 2 9.06 E plus 1 plus minus 7.10 E plus 0 6.954 E minus 3. 6. Nuke 20020240009. 4.25 E plus 1. Plus minus 7.97 E minus 1. 4.09 E plus 1. Plus minus 7.02 E plus 0. 1.97 E plus 0. Plus minus 1.42 E minus 1. 9.59 E minus 2 8.54 E plus 1 plus minus 7.06 E plus 0 7.218 E minus 32. Nuke 20020240010. 4.56 E plus 1. Plus minus 7.23 E minus 1. 4.20 E plus 1. Plus minus 7.70 E plus 0. 2.12 E plus 0. Plus minus 6.16 E minus 2. 9.59 E minus 2 8.98 E plus 1 plus minus 7.73 E plus 0 7.205 E minus 32. Nuke 20020240011. 1.56 E plus 2. Plus minus. 2.63 E plus 0. 3.72 E plus 1 plus minus. 5.90 E plus 0. 2.69 E plus 0. Plus minus 6.18 E minus 2. 7.30 E minus 1 plus minus 8.88 E minus 2. 1.97 E plus 2 plus minus 6.46 E plus 0. 2.683 E minus 3. 87. Nuke 20020240012. 3.98 E plus 2. Plus minus 8.38 E plus 0. 6.89 E plus 1 plus minus. 9.08 E plus 0. 5.93 E plus 0. Plus minus. 1.64 E minus 1. 2.06 E plus 0 plus minus. 2.62 E minus 1. 4.75 E plus 2 plus minus. 1.24 E plus 1. 2.317 E minus 3. 94. Nuke 2,002,025,001. 2.63 E plus 1 plus minus. 4.78 E minus 1. 2.59 E plus 1 plus minus. 4.18 E plus 0. 1.23 E plus 0. Plus minus 2.72 E minus 2. 7.19 E minus 2. 5.34 E plus 1 plus minus 4.21 E plus 0. 7.244 E minus 3. 2. Nuke 2,002,025,002. 3.71 E plus 1 plus minus. 6.52 E minus 1. 3.79 E plus 1 plus minus. 5.14 E plus 0. 1.73 E plus 0. Plus minus. 3.96 E minus 2. 7.19 E minus 2. 7.67 E plus 1 plus minus 5.18 E plus 0. 7.236 E minus 3. 2. Nuke 20020250003. 3.43 E plus 1. Plus minus. 6.08 E minus 1. 3.40 E plus 1 plus minus. 5.28 E plus 0. 1.60 E plus 0. Plus minus. 3.71 E minus 2. 7.19 E minus 2. 6.99 E plus 1 plus minus 5.31 E plus 0. 7.251 E minus 3. 2. Nuke 20020250004. 3.13 E plus 1. Plus minus. 6.11 E minus 1. 3.15 E plus 1 plus minus. 4.51 E plus 0. 1.46 E plus 0. Plus minus 3.52 E minus 2. 7.19 E minus 2. 6.42 E plus 1 plus minus 4.55 E plus 0. 7.244 E minus 3. 2. Nuke 20020260001. 2.21 E plus 1. Plus minus. 3.96 E minus 1. 2.11 E plus 1 plus minus. 4.46 E plus 0. 1.03 E plus 0. Plus minus 2.99 E minus 2. 4.79 E minus 2. 4.43 E plus 1 plus minus 4.48 E plus 0. 7.265 E minus 3. 2. Nuke 20020260002. 1.88 E plus 1. Plus minus. 4.63 E minus 1. 1.76 E plus 1 plus minus 3.61 E plus 0. 8.82 E minus 1 plus minus 2.58 E minus 2. 4.79 E minus 2 3.73 E plus 1 plus minus 3.64 E plus 0 7.284 E minus 3 2. Nuke 20020270001. 3.70 E plus 1. Plus minus 5.79 E minus 1. 3.57 E plus 1 plus minus 4.98 E plus 0. 1.72 E plus 0. Plus minus 3.96 E minus 2. 7.19 E minus 2 7.44 E plus 1 plus minus 5.01 E plus 0 7.233 E minus 3 2. Nuke 20020270002. 3.23 E plus 1. Plus minus 6.55 E minus 1. 3.11 E plus 1 plus minus 5.38 E plus 0. 1.51 E plus 0. Plus minus 3.51 E minus 2. 7.19 E minus 2 6.49 E plus 1 plus minus 5.42 E plus 0 7.244 E minus 3 2. Nuke 20020270003. 3.83 E plus 1. Plus minus 6.42 E minus 1. 3.76 E plus 1 plus minus 5.95 E plus 0. 1.79 E plus 0. Plus minus 3.61 E minus 2. 7.19 E minus 2 7.77 E plus 1 plus minus 5.99 E plus 0 7.238 E minus 3 2. Nuke 20020270004. 8.39 E plus 1. Plus minus 1.33 E plus 0. 4.24 E plus 1. Plus minus 7.92 E plus 0. 2.36 E plus 0. Plus minus 5.49 E minus 2. 2.66 E minus 1 plus minus 4.44 E minus 2 1.29 E plus 2 plus minus 8.03 E plus 0. 4.362 E minus 3. 55. Nuke 20020270005. 4.23 E plus 1. Plus minus 6.98 E minus 1. 3.90 E plus 1 plus minus 6.67 E plus 0. 1.93 E plus 0. Plus minus 4.46 E minus 2. 7.19 E minus 2 8.32 E plus 1 plus minus 6.71 E plus 0 7.084 E minus 3. 3. Nuke 20020280001. 3.13 E plus 1. Plus minus 5.32 E minus 1. 2.99 E plus 1. Plus minus 4.99 E plus 0. 1.42 E plus 0. Plus minus 3.00 E minus 2. 7.19 E minus 2 6.26 E plus 1 plus minus 5.02 E plus 0 7.043 E minus 3. 4. Nuke 20020280002. 3.00 E plus 1. Plus minus 5.56 E minus 1. 3.11 E plus 1 plus minus 4.96 E plus 0. 1.40 E plus 0. Plus minus 3.55 E minus 2. 7.19 E minus 2 6.25 E plus 1 plus minus 5.00 E plus 0 7.246 E minus 3 2. Nuke 20020280003. 2.58 E plus 1. Plus minus 4.30 E minus 1. 2.58 E plus 1. Plus minus 4.21 E plus 0. 1.13 E plus 0. Plus minus 3.02 E minus 2. 7.19 E minus 2. 5.27 E plus 1 plus minus 4.24 E plus 0. 6.829 E minus 3. 8. Nuke 20020280004. 3.18 E plus 1. Plus minus 5.37 E minus 1. 3.12 E plus 1 plus minus 4.70 E plus 0. 1.48 E plus 0. Plus minus 4.19 E minus 2. 7.19 E minus 2. 6.45 E plus 1 plus minus 4.73 E plus 0. 7.216 E minus 3. 2. Nuke 20020280006. 3.02 E plus 1. Plus minus 5.13 E minus 1. 2.96 E plus 1 plus minus 5.21 E plus 0. 1.40 E plus 0. Plus minus 2.91 E minus 2. 7.19 E minus 2. 6.12 E plus 1 plus minus 5.24 E plus 0. 7.208 E minus 3. 2. Nuke 20020280007. 1.66 E plus 1. Plus minus 3.16 E minus 1. 1.52 E plus 1 plus minus 3.37 E plus 0. 7.76 E minus 1 plus minus 2.14 E minus 2. 7.19 E minus 2. 3.26 E plus 1 plus minus 3.38 E plus 0. 7.256 E minus 3. 2. Nuke 2,002,030,001. 2.22 E plus 1 plus minus 4.81 E minus 1. 2.24 E plus 1 plus minus 4.53 E plus 0. 1.04 E plus 0. Plus minus 3.17 E minus 2. 4.79 E minus 2. 4.56 C plus 1 plus minus 4.56 C plus 0. 7.329 E minus 3. 2. Nuke 2,002,030,002. 2.22 E plus 1 plus minus 6.09 E minus 1. 2.26 E plus 1 plus minus 3.79 E plus 0. 1.04 E plus 0. Plus minus 3.53 E minus 2. 4.79 E minus 2. 4.59 E plus 1 plus minus 3.84 E plus 0. 7.268 E minus 3. 2. Nuke 2,002,030,003. 2.50 E plus 1 plus minus 5.01 E minus 1. 2.51 E plus 1 plus minus 4.01 E plus 0. 1.17 E plus 0. Plus minus 3.21 E minus 2. 4.79 E minus 2. 5.13 E plus 1 plus minus 4.04 E plus 0. 7.313 E minus 3. 2. Nuke 2,002,030,004. 1.94 E plus 1 plus minus 4.85 E minus 1. 1.95 E plus 1 plus minus 4.01 E plus 0. 9.13 E minus 1 plus minus 2.70 E minus 2. 4.79 E minus 2. 3.98 E plus 1 plus minus 4.04 E plus 0. 7.332 E minus 3. 2. Nuke 2,002,030,005. 2.24 E plus 1 plus minus 3.90 E minus 1. 2.04 E plus 1 plus minus 4.43 E plus 0. 1.05 E plus 0. Plus minus 2.48 E minus 2. 4.79 E minus 2 4.38 E plus 1 plus minus 4.45 E plus 0 7.278 E minus 3 2. Nuke 2,002,031,001. 5.62 E plus 1 plus minus 9.49 E minus 1. 4.84 E plus 1 plus minus 1.05 E plus 1. 2.62 E plus 0. Plus minus 5.67 E minus 2. 9.59 E minus 2 1.07 E plus 2 plus minus 1.06 E plus 1 7.249 E minus 3 2. Nuke 2,002,031,002. 3.91 E plus 1 plus minus 7.64 E minus 1. 3.85 E plus 1 plus minus 7.58 E plus 0. 1.83 E plus 0. Plus minus 4.51 E minus 2. 7.19 E minus 2 7.94 E plus 1 plus minus 7.62 E plus 0 7.300 E minus 3 2. Nuke 2,002,031,003. 3.87 E plus 1 plus minus 6.28 E minus 1. 3.67 E plus 1 plus minus 7.79 E plus 0. 1.81 E plus 0. Plus minus 4.23 E minus 2. 7.19 E minus 2 7.72 E plus 1 plus minus 7.82 E plus 0 7.287 E minus 3 2. Nuke 2,002,032,001. 3.86 E plus 1 plus minus 6.76 E minus 1. 3.87 E plus 1 plus minus 6.22 E plus 0. 1.81 E plus 0. Plus minus 4.62 E minus 2. 7.19 E minus 2 7.91 E plus 1 plus minus 6.25 E plus 0 7.293 E minus 3 2. Nuke 2,002,032,002. 3.19 E plus 1 plus minus 5.48 E minus 1. 3.20 E plus 1 plus minus 4.67 E plus 0. 1.50 E plus 0. Plus minus 3.16 E minus 2. 7.19 E minus 2 6.54 E plus 1 plus minus 4.71 E plus 0 7.310 E minus 3 2. Nuke 2,002,033,001. 3.11 E plus 1 plus minus 5.66 E minus 1. 3.21 E plus 1 plus minus 5.07 E plus 0. 1.45 E plus 0. Plus minus 3.75 E minus 2. 7.19 E minus 2 6.46 E plus 1 plus minus 5.11 E plus 0 7.245 E minus 3 2. Nuke 2,002,033,002. 3.11 E plus 1 plus minus 5.01 E minus 1. 3.18 E plus 1 plus minus 6.83 E plus 0. 1.45 E plus 0. Plus minus 3.02 E minus 2. 7.19 E minus 2 6.44 E plus 1 plus minus 6.84 E plus 0 7.285 E minus 3 2. Nuke 2,002,033,003. 3.10 E plus 1 plus minus 5.30 E minus 1. 3.27 E plus 1 plus minus 4.76 E plus 0. 1.45 E plus 0. plus minus 3.06 E minus 2. 7.19 E minus 2 6.51 E plus 1 plus minus 4.79 E plus 0 7.280 E minus 3 2. Nuke 2,002,034,001. 3.85 E plus 1 plus minus 6.22 E minus 1. 3.68 E plus 1 plus minus 5.20 E plus 0. 1.80 E plus 0. Plus minus 4.85 E minus 2. 7.19 E minus 2 7.71 E plus 1 plus minus 5.24 E plus 0 7.279 E minus 3 2. Nuke 2,002,034,002. 3.27 E plus 1 plus minus 6.42 E minus 1. 3.29 E plus 1 plus minus 5.86 E plus 0. 1.53 E plus 0. Plus minus 4.22 E minus 2. 7.19 E minus 2 6.72 E plus 1 plus minus 5.89 E plus 0 7.303 E minus 3 2. Nuke 2,002,035,001. 2.13 E plus 1 plus minus 5.61 E minus 1. 1.86 E plus 1 plus minus 4.07 E plus 0. 9.97 E minus 1 plus minus 3.76 E minus 2. 7.19 E minus 2 4.09 E plus 1 plus minus 4.11 E plus 0 7.278 E minus 3 2. Nuke 2,002,035,002. 3.20 E plus 1 plus minus 8.75 E minus 1. 2.98 E plus 1 plus minus 5.46 E plus 0. 1.49 E plus 0. Plus minus 6.36 E minus 2. 7.19 E minus 2 6.33 E plus 1 plus minus 5.53 E plus 0 7.267 E minus 3 2. 182. Post-conflict environmental assessment. Table D.4 Profile soil samples. Sample code. Nuke 20020281001 Nuke 20020281002 Nuke 20020281003 Nuke 20020281004 Nuke 20020281005 Nuke 20020281006 Nuke 20020281007 Nuke 20020281008 Nuke 20020281009 Nuke 20020281010 Nuke 200202811 Nuke 200202811 Nuke 200202812 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 Nuke 200202813 Nuke 200202831 Nuke 200202832. Sampling date. October 18, 2002, 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 October 19, 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 2002. Coordinates UTM 34T. CP 35 468, 84 445 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 CP 35 795, 84 340 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 CP 35 795, 84 340. Sample type. Sample tool soil, shovel, above penetrator soil, shovel, around penetrator soil, profile template 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 soil, shovel, around penetrator soil, shovel, below penetrator soil, profile template 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 soil, profile template. Depth. 0 to 6 cm, 6 to 10 cm, 10 to 15 cm, 15 to 20 cm, 20 to 25 cm, 25 to 30 cm, 30 to 35 cm, 35 to 40 cm, 40 to 45 cm, 45 to 50 cm, 50 to 55 cm, 55 to 60 cm, 0 to 5 cm, 5 to 10 cm, 10 to 15 cm, 15 to 20 cm, 20 to 25 cm, 25 to 30 cm, 30 to 35 cm, 35 to 40 cm, 40 to 45 cm, 45 to 50 cm, 50 to 55 cm, 55 to 60 cm, 60 to 65 cm. Table D.5 Concentration of uranium isotopes and Dune profile soil samples, mg/kg. D. Dune soil. Sample code U238, mg/kg. U234, mg/kg. U235 mg/kg. U236 mg/kg. U dot mg/kg. U235% due of U238 ratio total U. Nuke 2,002,028 101. 2.31 E plus 3. Plus minus. 4.32 E plus 1. 1.56 E minus 2. Plus minus. 3.10 E minus 3. 4.56 E plus 0. Plus minus. 2.46 E minus 1 6.35 E minus 2 plus minus 9.90 E minus 3 2.31 E plus 3 plus minus 4.32 E plus 1 1.967 E minus 3 101. Nuke 2,002,028 102. 4.52 E plus 4. Plus minus 9.82 E plus 2. 2.96 E minus 1. Plus minus 4.67 E minus 2. 8.96 E plus 1. Plus minus 4.14 E plus 0. 1.22 E plus 0. Plus minus 1.54 E minus 1. 4.53 E plus 4. Plus minus 9.82 E plus 2. 1.974 E minus 3. 100. Nuke 2,002,028 103. 5.15 E plus 3. Plus minus 9.63 E plus 1. 3.05 E minus 2. Plus minus 4.03 E minus 3. 1.02 E plus 1. Plus minus 3.93 E minus 1. 1.47 E minus 1. Plus minus 2.52 E minus 2. 5.16 E plus 3. Plus minus 9.63 E plus 1. 1.976 E minus 3. 100. Nuke 2,002,028 104. 2.28 E plus 2. Plus minus 3.92 E plus 0. 1.73 E minus 3. Plus minus 5.82 E minus 4. 4.68 E minus 1 plus minus 1.31 E minus 2 6.28 E minus 3 plus minus 8.09 E minus 4 2.28 E plus 2 plus minus 3.92 E plus 0. 2.053 E minus 3. 99. Nuke 2,002,028 105. 1.76 E plus 1 plus minus 3.29 E minus 1 2.74 E minus 4 plus minus 5.82 E minus 5 5.20 E minus 2 plus minus 1.29 E minus 3 4.08 E minus 4 plus minus 5.26 E minus 5 1.76 E plus 1 plus minus 3.29 E minus 1 2.958 E minus 3. 82. Nuke 2,002,028 106. 5.74 E plus 0. Plus minus 1.05 E minus 1 1.93 E minus 4 plus minus 3.11 E minus 5 2.84 E minus 2. Plus minus 9.04 E minus 4 7.34 E minus 5 plus minus 1.44 E minus 5 5.77 E plus 0 plus minus 1.05 E minus 1. 4.936 E minus 3. 44. Nuke 2,002,028 107. 5.81 E plus 0. Plus minus 1.64 E minus 1 1.91 E minus 4 plus minus 2.85 E minus 5 2.84 E minus 2 plus minus 1.39 E minus 37.15 E minus 5 plus minus 1.42 E minus 55.84 E plus 0 plus minus 1.64 E minus 1. 4.875 E minus 3. 45. Nuke 2,002,028 108. 4.97 E plus 0. Plus minus 1.61 E minus 1 1.90 E minus 4 plus minus 3.15 E minus 5 2.69 E minus 2. Plus minus 9.74 E minus 4 4.98 E minus 5 plus minus 1.22 E minus 5 5.00 E plus 0 plus minus 1.61 E minus 1. 5.403 E minus 3. 35. Nuke 2,002,028 109. 4.19 E plus 0. Plus minus 7.88 E minus 2. 1.87 E minus 4 plus minus 2.7 E minus 5. 2.57 E minus 2 plus minus 6.80 E minus 4. 4.00 E minus 5 4.22 E plus 0 plus minus hash ref 6.118 E minus 322. Nuke 2,002,028 110. 3.57 E plus 0. Plus minus 7.00 E minus 2. 1.87 E minus 4 plus minus 2.80 E minus 5. 2.54 E minus 2. Plus minus 5.92 E minus 4. 4.00 E minus 5 3.59 E plus 0 plus minus hash ref 7.121 E minus 32. Nuke 2,002,028 111. 3.64 E plus 0. Plus minus 1.92 E minus 1 1.99 E minus 4 plus minus 3.60 E minus 5. 2.64 E minus 2. Plus minus 1.43 E minus 3. 4.00 E minus 5 3.66 E plus 0 plus minus hash ref 7.248 E minus 32. Nuke 2,002,028 112. 3.38 E plus 0. Plus minus 6.66 E minus 2. 1.87 E minus 4 plus minus 3.08 E minus 5. 2.45 E minus 2. Plus minus 7.23 E minus 4. 4.00 E minus 5 3.40 E plus 0 plus minus hash ref 7.232 E minus 32. Nuke 2,002,028 120. 4.66 E plus 3. Plus minus 3.09 E plus 2. 2.82 E minus 2. Plus minus 7.73 E minus 3. 9.23 E plus 0. Plus minus 7.32 E minus 1. 1.29 E minus 1. Plus minus 1.95 E minus 2. 4.67 E plus 3. Plus minus 3.09 E plus 2. 1.974 E minus 3. 100. Nuke 2,002,028 121. 4.93 E plus 2. Plus minus 9.43 E plus 0. 3.34 E minus 3. Plus minus 5.06 E minus 4. 9.89 E minus 1 plus minus 2.52 E minus 2 1.27 E minus 2 plus minus 2.22 E minus 3 4.94 E plus 2 plus minus 9.43 E plus 0. 2.001 E minus 3. 100. Nuke 2,002,028 122. 7.14 E plus 1 plus minus 1.37 E plus 0 5.83 E minus 4 plus minus 1.34 E minus 4. 1.54 E minus 1 plus minus 4.05 E minus 3 1.89 E minus 3 plus minus 2.65 E minus 4 7.16 C plus 1 plus minus 1.37 E plus 0. 2.153 E minus 3. 97. Nuke 2,002,028 123. 4.97 E plus 1 plus minus 7.55 E minus 1 4.28 E minus 4 plus minus 7.1 E minus 5. 1.10 E minus 1 plus minus 3.58 E minus 3 1.27 E minus 3 plus minus 1.69 E minus 4 4.98 E plus 1 plus minus 7.55 E minus 1. 2.210 E minus 3. 96. Nuke 2,002,028 124. 2.03 E plus 1 plus minus 3.41 E minus 1 2.33 E minus 4 plus minus 3.2 E minus 5. 5.04 E minus 2 plus minus 1.42 E minus 3 5.14 E minus 4 plus minus 7.3 E minus 5. 2.04 E plus 1 plus minus 3.41 E minus 1. 2.475 E minus 3. 91. Nuke 2,002,028 125. 6.99 E plus 0. Plus minus 1.09 E minus 1 1.61 E minus 4 plus minus 2.5 E minus 5. 2.65 E minus 2. Plus minus 1.34 E minus 3 1.24 E minus 4 plus minus 1.9 E minus 5. 7.02 E plus 0 plus minus 1.09 E minus 1. 3.780 E minus 3. 66. Nuke 2,002,028 126. 3.95 E plus 0 plus minus 7.09 E minus 2. 1.61 E minus 4 plus minus 2.6 E minus 5. 2.19 E minus 2 plus minus 5.00 E minus 4. 4.1 E minus 5. Plus minus 1.1 E minus 5. 3.97 E plus 0 plus minus 7.09 E minus 2. 5.534 E minus 3. 33. Nuke 2,002,028 127. 3.14 E plus 0. Plus minus 5.50 E minus 2. 1.59 E minus 4 plus minus 3.12 E minus 5. 2.14 E minus 2. Plus minus 4.85 E minus 4. 3.00 E minus 5 3.16 E plus 0 plus minus 5.50 E minus 2 6.785 E minus 3 9. Nuke 2,002,028 128. 3.15 E plus 0. Plus minus 1.25 E minus 1 1.77 E minus 4 plus minus 3.03 E minus 5. 2.26 E minus 2. Plus minus 9.60 E minus 4. 3.00 E minus 5 3.17 E plus 0 plus minus 1.25 E minus 1 7.160 E minus 3 2. Nuke 2,002,028 129. 3.10 E plus 0. Plus minus 5.50 E minus 2. 1.71 E minus 4 plus minus 2.78 E minus 5. 2.24 E minus 2. plus minus 4.70 E minus 4. 3.00 E minus 5 3.12 E plus 0 plus minus 5.50 E minus 2 7.199 E minus 32. Nuke 2,002,028 130. 2.84 E plus 0. Plus minus 6.14 E minus 2. 1.57 E minus 4 plus minus 2.67 E minus 5. 2.06 E minus 2. Plus minus 5.55 E minus 4. 3.00 E minus 5 2.86 E plus 0 plus minus 6.14 E minus 2 7.240 E minus 32. Nuke 2,002,028 131. 2.32 E plus 0. Plus minus 3.91 E minus 2. 1.22 E minus 4. Plus minus 2.44 E minus 5. 1.69 E minus 2. Plus minus 4.21 E minus 4. 3.00 E minus 5 2.34 E plus 0 plus minus 3.91 E minus 2 7.269 E minus 32. Nuke 2,002,028 132. 1.97 E plus 0. Plus minus 4.45 E minus 2. 1.07 E minus 4. Plus minus 2.13 E minus 5. 1.44 E minus 2. Plus minus 3.74 E minus 4. 3.00 E minus 5 1.98 E plus 0 plus minus 4.45 E minus 2 7.263 E minus 32. Depleted uranium in Bosnia and Herzegovina. 183. D. Table D.6 Activity of uranium isotopes and DUN profile soil samples, BQ/kg. Sample code U238, BQ/kg. U234, BQ/kg. U235, BQ/kg. U236, BQ/kg. U. BQ/kg. U235% due of U238 ratio total U. Nuke 2,002,028 101. 2.87 E plus 4. Plus minus 5.38 E plus 2. 3.60 E plus 3. Plus minus 7.15 E plus 2. 3.65 E plus 2. Plus minus 1.97 E plus 1 1.52 E plus 2 plus minus 2.37 E plus 1. 3.28 E plus 4. Plus minus 8.95 E plus 2. 1.967 E minus 3. 101. Nuke 2,002,028 102. 5.63 E plus 5. Plus minus 1.22 E plus 4. 6.85 E plus 4. Plus minus 1.08 E plus 4. 7.17 E plus 3. Plus minus 3.31 E plus 2. 2.93 E plus 3. Plus minus 3.70 E plus 2. 6.41 E plus 5. Plus minus 1.63 E plus 4. 1.974 E minus 3. 100. Nuke 2,002,028 103. 6.40 E plus 4. Plus minus 1.20 E plus 3. 7.05 E plus 3. Plus minus 9.31 E plus 2. 8.17 E plus 2. Plus minus 3.14 E plus 1. 3.53 E plus 2. plus minus 6.03 E plus 1, 7.22 E plus 4, plus minus 1.52 E plus 3, 1.976 E minus 3, 100. Nuke 2,002,028 104. 2.83 E plus 3, plus minus 4.87 E plus 1 3.99 E plus 2, plus minus 1.34 E plus 2, 3.74 E plus 1, plus minus 1.05 E plus 0, 1.51 E plus 1 plus minus 1.94 E plus 0, 3.28 E plus 3, plus minus 1.43 E plus 2, 2.053 E minus 3, 99. Nuke 2,002,028 105. 2.19 E plus 2, plus minus 4.10 E plus 0, 6.33 E plus 1 plus minus 1.34 E plus 1 4.16 E plus 0 plus minus 1.03 E minus 1, 9.79 E minus 1 plus minus 1.26 E minus 1 2.87 E plus 2 plus minus 1.40 E plus 1, 2.958 E minus 3, 82. Nuke 2,002,028 106. 7.14 E plus 1 plus minus 1.30 E plus 0, 4.46 E plus 1 plus minus 7.17 E plus 0, 2.27 E plus 0, plus minus 7.23 E minus 2, 1.76 E minus 1 plus minus 3.46 E minus 2, 1.18 E plus 2 plus minus 7.29 E plus 0, 4.936 E minus 3, 44. Nuke 2,002,028 107. 7.23 E plus 1 plus minus 2.04 E plus 0, 4.40 E plus 1 plus minus 6.58 E plus 0, 2.27 E plus 0, plus minus 1.11 E minus 1, 1.71 E minus 1 plus minus 3.40 E minus 2, 1.19 E plus 2 plus minus 6.89 E plus 0, 4.875 E minus 3, 45. Nuke 2,002,028 108. 6.19 E plus 1 plus minus 2.00 E plus 0, 4.38 E plus 1 plus minus 7.26 E plus 0, 2.16 E plus 0, plus minus 7.79 E minus 2, 1.19 E minus 1 plus minus 2.93 E minus 2 1.08 E plus 2 plus minus 7.53 E plus 0, 5.403 E minus 3, 35. Nuke 2,002,028 109. 5.22 E plus 1 plus minus 9.81 E minus 1, 4.32 E plus 1 plus minus 6.30 E plus 0, 2.05 E plus 0, plus minus 5.44 E minus 2, 9.59 E minus 2 9.75 E plus 1 plus minus hash ref 6.118 E minus 3, 22. Nuke 2,002,028 110. 4.44 E plus 1 plus minus 8.71 E minus 1, 4.33 E plus 1 plus minus 6.46 E plus 0, 2.03 E plus 0, plus minus 4.74 E minus 2, 9.59 E minus 2 8.98 E plus 1 plus minus hash ref 7.121 E minus 3 2 Nuke 2,002,028 111 4.52 E plus 1 plus minus 2.39 E plus 0 4.59 E plus 1 plus minus 8.30 E plus 0 2.11 E plus 0 plus minus 1.14 E minus 1 9.59 E minus 2 9.33 E plus 1 plus minus hash ref 7.248 E minus 3 2 Nuke 2,002,028 112 4.20 E plus 1 plus minus 8.29 E minus 1 4.31 E plus 1 plus minus 7.10 E plus 0 1.96 E plus 0 plus minus 5.79 E minus 2 9.59 E minus 2 8.71 E plus 1 plus minus hash ref 7.232 E minus 3 2 Nuke 2,002,028 120 5.80 E plus 4 plus minus 3.85 E plus 3 6.52 E plus 3 plus minus 1.79 E plus 3 7.39 E plus 2 plus minus 5.86 E plus 1 3.10 E plus 2 plus minus 4.66 E plus 1 6.56 E plus 4 plus minus 4.24 E plus 3 1.974 E minus 3 100 Nuke 2,002,028 121 6.13 E plus 3 plus minus 1.17 E plus 2 7.70 E plus 2 plus minus 1.17 E plus 2 7.91 E plus 1 plus minus 2.01 E plus 0 3.04 E plus 1 plus minus 5.33 E plus 0 7.01 E plus 3 plus minus 1.66 E plus 2 2.001 E minus 3 100 Nuke 2,002,028 122 8.88 E plus 2 plus minus 1.70 E plus 1 1.35 E plus 2 plus minus 3.09 E plus 1 1.23 E plus 1 plus minus 3.24 E minus 1 4.53 E plus 0 plus minus 6.34 E minus 1 1.04 E plus 3 plus minus 3.53 E plus 1 2.153 E minus 3 97 Nuke 2,002,028 123 6.18 E plus 2 plus minus 9.40 E plus 0 9.88 E plus 1 plus minus 1.64 E plus 1 8.80 E plus 0 plus minus 2.87 E minus 1 3.04 E plus 0 plus minus 4.05 E minus 1 7.29 E plus 2 plus minus 1.89 E plus 1 2.210 E minus 3 96 Nuke 2,002,028 124 2.53 E plus 2 plus minus 4.24 E plus 0 5.38 E plus 1 plus minus 7.44 E plus 0 4.03 E plus 0 plus minus 1.14 E minus 1 1.23 E plus 0 plus minus 1.76 E minus 1 3.12 E plus 2 plus minus 8.57 E plus 0. 2.475 E minus 3. 91. Nuke 2,002,028 125. 8.69 E plus 1 plus minus. 1.36 E plus 0. 3.73 E plus 1 plus minus. 5.87 E plus 0. 2.12 E plus 0. Plus minus. 1.07 E minus 1 2.98 E minus 1 plus minus 4.56 E minus 2 1.27 E plus 2 plus minus 6.02 E plus 0. 3.780 E minus 3. 66. Nuke 2,002,028 126. 4.91 E plus 1 plus minus. 8.82 E minus 1. 3.71 E plus 1 plus minus. 5.92 E plus 0. 1.75 E plus 0. Plus minus. 4.00 E minus 2. 9.78 E minus 2 plus minus 2.54 E minus 2. 8.81 E plus 1 plus minus 5.99 E plus 0. 5.534 E minus 3. 33. Nuke 2,002,028 127. 3.90 E plus 1 plus minus. 6.84 E minus 1. 3.68 E plus 1 plus minus. 7.20 E plus 0. 1.71 E plus 0. Plus minus. 3.88 E minus 2. 7.19 E minus 2 7.75 E plus 1 plus minus 7.23 E plus 0 6.785 E minus 3. 9. Nuke 2,002,028 128. 3.91 E plus 1 plus minus. 1.55 E plus 0. 4.09 E plus 1 plus minus. 7.01 E plus 0. 1.81 E plus 0. Plus minus. 7.68 E minus 2. 7.19 E minus 2 8.19 E plus 1 plus minus 7.18 E plus 0 7.160 E minus 3. 2. Nuke 2,002,028 129. 3.86 E plus 1 plus minus. 6.84 E minus 1. 3.95 E plus 1 plus minus. 6.42 E plus 0. 1.79 E plus 0. Plus minus. 3.76 E minus 2. 7.19 E minus 2 7.99 E plus 1 plus minus 6.46 E plus 0 7.199 E minus 3. 2. Nuke 2,002,028 130. 3.53 E plus 1 plus minus. 7.64 E minus 1. 3.63 E plus 1 plus minus. 6.16 E plus 0. 1.65 E plus 0. Plus minus. 4.44 E minus 2. 7.19 E minus 2 7.32 E plus 1 plus minus 6.21 E plus 0 7.240 E minus 3. 2. Nuke 2,002,028 131. 2.89 E plus 1 plus minus. 4.86 E minus 1. 2.83 E plus 1 plus minus. 5.63 E plus 0. 1.35 E plus 0. Plus minus. 3.37 E minus 2. 7.19 E minus 2 5.85 E plus 1 plus minus 5.65 E plus 0 7.269 E minus 3. 2. Nuke 2,002,028 132. 2.45 E plus 1 plus minus. 5.54e-1, 2.46e plus 1 plus minus, 4.92e plus 0, 1.15e plus 0, plus minus, 2.99e minus 2, 7.19e minus 2, 5.03e plus 1 plus minus 4.96e plus 0, 7.263e minus 3, 2. Table D.7 extracted 238U concentrations. UNEP 2002028. 140, 141, 142, 143, 144, 145, 146, 148, 151, 154, 158, 162. Exchangeable. 238U. mg/kg, 12,575.2, 1,683.5. 97.7, 60.0, 53.8, 105.1, 57.4, 19.7, 4.1, 0.9, 0.2, 0.0. K, percent, 4.5, 2.7, 4.4, 9.9, 5.0, 1.7, 2.1, 13.4, 1.8, 1.9, 2.7, 3.8. Carbonates. 238U. mg/kg, 2024.5, 1781.4, 205.2, 173.6, 152.3. 69.2, 34.8, 69.8, 25.5, 5.6, 1.9, K, percent, 4.8, 5.9, 7.0, 1.8, 2.0, 2.2, 3.16, 5.1, 2.1, 3.9, 37.1. Fe, Mn oxides. 238U. mg/kg, 760.2, 460.5, 50.5, 53.8, 59.9, 25.2, 11.3, 23.3, 7.0, 1.5, 0.5, 0.3. K, percent, 9.6, 7.8, 2.6, 4.6, 1.9, 3.3, 6.7, 22.6, 1.8, 2.8, 5.2, 7.1. Organic matter. 238U. mg/kg, 1609.7, 788.2. 34.2, 38.7, 52.6, 20.3, 10.3, 17.5, 5.6, 1.4, 0.7, 0.4. K, percent, 86.7, 2.5, 2.22, 10, 5.9. 14.3, 6.6, 3.7, 6.6, 3.9. Amorphous silicates, 238U. mg/kg, 12.985, 5.038, 0.152, 0.2000, 0.313, 0.236, 0.115, 0.123, 0.091, 0.035, 0.013, 0.002. K, percent, 1.7, 1.8, 2.4, 2.7, 27.9, 14.1, 3.5, 29.0, 89.4, 5.8, 79.0, 26.3. Amorphous silicates, B. 238U. mg/kg, 90.425, 90.463, 2.295, 2.294, 2.944, 0.917, 0.347, 0.729, 0.250, 0.074, 0.057, 0.036. K, percent, 54.0, 43.6, 8.4, 5.8, 1.9, 3.8, 6.3, 15.0, 2.3, 6.5, 13.2, 5.7. Residual. 238 mg/kg, 12.0156.0410.40.103.0.12510.120.0.126.0.1530.131 K, percent, 14.12.8, 2.45.28.13.92.311.53.16.5 Table D.8 Fusion of the residual soil. Nuke 2002-028 140 ARF 141 ARF 142 ARF 143 ARF 144 ARF 145 ARF 146 ARF 148 ARF 151 ARF 154 ARF 158 ARF 162 AIRF 162 IRF 238 mg/kg 3.78 3.01 2.24 2.54 2.20 1.37 1.13 1.32 1.11 0.86 0.94 1.15 0.97 RSD, percent 0.47 0.50 0.78 0.75 0.87 1.05 0.49 0.98 1.33 1.52 0.95 1.95 1.58 Table D.9 Fusion of the starting Nuke 2002-028 140 SSF 141 SSF 142 SSF 143 SSF 144 SSF 145 SSF 146 SSF 148 SSF 151 SSF 154 SSF 158 SSF 162 SSF 238 mg/kg 10,529 7,334 742 559 535.5 211.6 256.9 217.3 90.6 19.4 4.22.5 RSD, percent 0.51 0.32 0.26 0.29 0.36 0.21 0.22 0.23 0.65 0.40 0.99 0.26 184 Post-conflict environmental assessment Appendix C Dew in water E.1 General aspects E. Dew in water. During an 8-10 plane attack using dew ammunition, most of the munitions miss the primary target, for example the tanks or armored personnel carriers, APC, and therefore pass more or less intact into the ground. Once there, the dew penetrators may corrode, gradually dissolve and the depleted uranium may contaminate the groundwater. This contamination is to be understood as a certain contribution to an already existing natural concentration of uranium in natural waters. Wells using groundwater within or close to the sites may be affected, and the total uranium concentration in the water may reach concentrations that are above recommended international limits for uranium in drinking water. As this appendix also relates to information in both Appendix D Dew in soil and Appendix O data on uranium, partial repetition is necessary to allow the reader to follow the subject. E.2 Uranium in groundwater. A French study from a dew test site in southern France recently concluded that dew is fairly immobile. Granson, 2000 and Appendix D. It was found that uranium had moved down the soil profile to a depth of 30 centimeters in approximately 30 years, and is held entirely within the A1 fraction of the soil. Granson, 2001. The mineral horizon is defined as containing less than 17% organic carbon by mass that has formed at or near the soil surface in the zone of leaching or alluviation of organic materials in solution or suspension, or of maximum in situ accumulation of organic matter, or both. The thickness of the A.1 soil horizon depends on the local situation, but it does not usually exceed 30 centimeters. Complementary experimental studies show that the distribution coefficient, Kd equals concentration of U in the soil, solid, divided by the concentration of U in water, is 3,000 in the presence of humic acid colloids, that is uranium moves 3,000 times slower, retardation factor, RF equals 3,000, than the water that percolates through the soil. It concludes, however, that about 10% of the uranium is able to move further down the soil profile and reach the underlying groundwater through the formation of uranium humic acid colloids which aid in the transport of uranium. This could be the cause of somewhat elevated uranium levels, which reach 25 micrograms/L, ppb, in the groundwaters and canal waters of the French DU test site during extreme droughts. The regional maximum concentration does usually not exceed 8 micrograms/L, ppb. Groundwater uranium values at the site in southern France are likely to be higher than in some areas of stream water sample near the Bielasnoka Plateau. Depleted uranium in Bosnia and Herzegovina. 185. E. B. Due to the different rock types in that area. In France, the soil pH is somewhere between 3.5 and 4.5 for the A1 soil fraction, whereas the soil pore water pH for most of the sites in B is expected to be higher due to the presence of carbonate minerals from limestone, which increases the pH. In areas where penetrators are embedded in soil in B, one could conclude that in future years the maximum concentration of uranium in groundwater would not exceed 25 micrograms/L. By comparing the uranium concentrations found at the French DU test site with the acceptable drinking water values, it emerges that the latter values vary according to the different regulating agencies around the world. See also Appendix O. The drinking water standards for public waters set by the WHO is 2 micrograms/L, whereas the U.S. Environmental Protection Agency defined the standard of 30 micrograms/L. Canadian Health has defined the standard of 10 micrograms/L and SSK in Germany states 300 micrograms/L, but in the German territory of Hessen it is set 2 micrograms/L. EU drinking water directives give an indicative limit expressed as a dose of 0.1 millisieverts per year for radioactive substances in water. This corresponds to an average daily water intake with a uranium concentration of 100 micrograms per liter, U-238 plus 234 in equilibrium, but no daughter products. Of note is that many bottled mineral waters have naturally high uranium contents of up to about 100 micrograms/L. The WHO is currently revising their value of 2 micrograms/L because it is thought to be too low. The reference for WHO's new suggested guideline value for uranium in water is 9 micrograms/L, WHO, 2002. Uranium concentrations in groundwater may increase as more of the penetrators corrode and their corrosion products, alteration phase, dissolve. From the observations in the Cranston study mentioned above, it could be concluded that uranium mobility will be retarded if penetrators are trapped in soil. According to UNEP's observations during the last 3 assessments, the majority of the penetrators are most likely buried within a few cm of soil. Where the penetrators had hit rock, they bounce off and lay on the surface as fragments, whereas where they hit asphalt, penetrators were found in superficial holes and sometimes visible from the surface. The capacity for uranium retardation within surface soils and rocks is thus affected by the thickness of soil, its composition and the presence of man-made surface materials, for example asphalt. Further, where groundwaters are oversaturated with respect to calcite, uranium can sorb with the calcite. Catano and Omari, 1971, Carroll and Bruno, 1991, Mies and Benninger, 1993. Finally, it is also important to consider the depth to the groundwater table. The study of the literature on DU data would allow to conclude that 1. Transport of dissolved DU is limited as most of the uranium will stay in the soil. 2. In some cases, under the worst geochemical conditions, dew can be expected to contaminate the groundwater. 3. The concentration of dew in groundwater will depend on thickness and type of soil, type of bedrock, and depth to groundwater, keeping in mind that the naturally arising uranium in the specific groundwater is already a product of these parameters. 4. Since the dissolution kinetics of soapite is still not established, it is difficult to evaluate the volumes of groundwater that may be affected at the dew sites in BH. 5. Similarly, it is not possible to state exactly how large the areas are around a targeted site that can significantly be affected by dew. 6. Further, it is impossible to accurately predict how far from a site dew-contaminated groundwater can be transported in the flow direction of groundwater. Dilution, dispersion as well as retardation of the uranium concentration will take place. 186. Post-conflict environmental assessment. Dew in water. 7. Surface waters are assumed to not be seriously affected by dew widespread or localized contamination, dew dust created due to the impact of penetrators and spread over a large area. 8. Surface waters may be affected by a relevant quantity of penetrators sticking in the surface soil, the bed of the surface water aquifer. The Serbia and Montenegro Dew Assessment, UNEP, 2001, shows that penetrators sticking in soil are heavily corroded and result in different corrosion products. Similar observations were made in BH. In evaluating what is known about soapite dissolution kinetics, it emerged that further study is necessary in order to evaluate the rate of dissolution of this mineral with respect to mineral crystallinity, pH, conductivity A, soil composition and partial pressure of CO. Such too. A study is currently underway at the University of Bristol to evaluate the possible link between contaminated soils and waters with the food chain and the subsequent intake of uranium by people. A study is currently underway in both Kosovo and Serbia as a collaborative effort between the Universities of Middlesex and Bristol and the German Radiation Protection Institute, GSF. At those sites where contamination of dew was found in water, knowledge of local hydrogeology would be useful in order to understand how such contamination is possible. Tap water from a freshwater source at Ustikolina. E.3 Results of the water samples collected. The main objectives of water sampling were 1. The possible contamination of the underground aquifer due to the migration along the soil profile of uranium radioisotopes originating from depleted uranium ammunitions. 2. The presence of any contamination of surface water bodies due to the erosion of contaminated areas, and if the intake of uranium isotopes originating from ammunition could represent radiation exposure of any significance to the local population, and 3. As a secondary objective, to measure and assess the potential heavy metals content at certain sites. In order to distinguish between natural and anthropogenic uranium, 234U/238U and 235U/238U activity ratios can be used. Goldstein et al. 1997, report that these ratios in natural waters range typically from 0.8 to 10 for 234U/238U, while 235U/238U activity ratio is thought to have a relatively uniform value of about 0.045. The high variability of 234U/238U activity ratio is due to the recoil effect which occurs when the recoil energy, given to the 234Th daughter during the 238U decay, breaks the bond between 234Th, and the subsequent daughters 234 pascals and 234U, and the crystal matrix so that the 234U atom is freer and easily leached, thus more ready to enter the solution than the remaining 238U atoms. Muck and De Vries, 2001, considering fixed pH and redox conditions. Values of these ratios below these natural limits may be indicative of an anthropogenic source of uranium in the considered samples. Sanson et al., 2001, 2001b. Depleted uranium in Bosnia and Herzegovina. 187. E. Water samples were collected by the APOT team at the locations reported in Table E.1. Sampling procedures are described in Appendix C. Table E.1 Water samples collection sites. Sample, APOT. Sampling site. BHWO1 BHWO2 BHWO3 BHWO4. Hadsisi, Tank Repair Facility Hadsisi, Tank Repair Facility Hadsisi, Tank Repair Facility Hadsisi, Tank Repair Facility. BHWO5 BHWO6 BHWO7 BHWO8 BHWO9 BHW10 BHW11 BHW12. Lukavika Hadsisi, Barracks Hadsisi, Barracks Han Pijsk, Barracks Han Pijsk, Barracks. Pale, Barracks Vogoska Vogoska. BHW13. Ustokolina, Barracks. BHW14 BHW15 BHW16. BHW17. Ustokolina, Barracks. Foka Bridge, Srbinj, Kalinovic, Water Reservoir. Kalinovic, Ammunition Destruction Site. BHW18 BHW19. Bielasno Kaputo Bielasno Kaputo. Code U820030030001 U820030030002 U820030030003 U820030030004 U820030030005 U820030030006 U820030030007 U820030030008 U820030030009 U820030030010 U820030030011 U820030030013 U820030030014 U820030030015 U820030030016 U820030030017 U820030030018 U820030030019 Coordinates. Sample type 34 TBP 74215, 56365. Water form concrete drainage well 34 TBP 74172, 56387. Stream water 34 TBP 74172/56370. Well water 34 TBP 74395, 56319. Water form concrete drainage well 34 TBP 88560, 55870. Public tap water 34 TBP 75321/54761. Stream water 34 TBP 75351/54720. Tap water 34 TBP 36022, 84309. Tap water 34 TBP 35540, 84380. Stream water 34 TCP 05663, 52318. River water 34 TBP 89407, 65357. River water 34 TBP 90083, 66656. Water reservoir 34 TCP 20059, 28289. Spring water collected from tap 34 TCP 20245, 27886. Spring water collected from tap. 34 TCP 20,390, 20,510 public water from tap. 34 TBP 93344/20,528. Spring water. Bond on the bottom of 34 TBP 91610/18,277 a karst hole used for blasting of ordnance. 34 TBP 65667/46,257. Spring water collected from tap. 34 TBP 66591/45,775. Stream water. 8.3.1 Water sample results. The activity concentrations of 238U, 234U, 235U and the values of 234U/238U and 235U/238U activity ratios measured by APHOT in the water samples are reported in Table E.2. In Table E.3, APHOT reports the concentrations of 238U, 234U, 235U and the values of 234U/238U and 235U/238U concentration ratios calculated on these same samples. HRICP-MAS analyses by species were performed on the same samples. Results are presented in Tables E.4 and D.5. Well water from Herzegovina showed traces of dew. The 234U/238U activity ratios, BQ/BQ, in the water samples collected range from 0.58 plus 0.04 to 2.29 plus 0.37 with a mean value of 1.48 plus 0.47, while the concentration ratios range, mg/mg, from 3.12 E-5 plus 2.88 E-6 to 1.23 E-4 plus 1.02 E-5 with a mean value of 7.96 E05 plus minus 2.53 E05 with a variation coefficient of 32%. The 235U/238U based on ICP-MAS measurements lie in the natural uranium ratio, with the exception of samples BHW01 and BHW03, showing no evidence of dew. The dew percentage of total uranium for BHW01 was measured. 188. Post-conflict environmental assessment. At 14 plus minus 2% and for BHW03 at 73.4 plus minus 1%. In addition, the presence of U-236, 18 plus minus 9 pg/L, could be identified in BHW03 showing clear evidence of the presence of dew. Data reported in both tables E.2 and E.3 indicate that 235U data have high uncertainties as a result of the technique used, alpha spectrometry. This is attributable to the lower 235U activity concentrations in the water. This isotope is more accurately estimated using mass spectrometric techniques, Braby, 1995, rather than an alpha pulse height analysis. On the other hand, the former technique is weaker in determining 234U. Results by mass spectrometry are provided in tables 4 and 5 showing that 235U concentrations were easily measured. The evaluation of the alpha spectrometric results was made only with the activity concentration data on 238U and 234U due to higher sensitivity of this method for these isotopes. UNEP, 2001, Sanson et al., 2001. Comparing the results obtained from the measurements of water samples collected, tables 2 and 3, with the reference values for natural waters, Goldstein et al., 1997, there is evidence of dew contamination of drinking water in only one collected sample at the former Herzegovina tank repair facility, BHW03. The result obtained by mass spectrometry of the U235/U238 ratio confirms the presence of dew in the sample BHW03. Traces of 236U are also detected in this sample. In addition, using this same technique, a small indication of dew was revealed in the water sample BHW01. This contamination may be due to the fact that the drinking wells are located directly in what was the line of attack of the A-10 planes. Consequently, A number of penetrators can be expected to be found buried in the soil in the near proximity to the wells. These penetrators are most likely the contamination source of these wells. However, the dew concentration levels were very low and no adverse health effects can occur. The uranium concentration of the waters collected are consistent with the results obtained from the water samples collected by the UNEP dew mission to Kosovo, UNEP, 2001, and Serbia and Montenegro, UNEP, 2002. Activity concentrations of naturally occurring radionuclides in drinking water vary widely because of the differing background levels, climate and agricultural conditions that prevail. In the UNSEER 2000 report, the 238U activity concentration in drinking water measured in Europe ranges from 5.0 E-4 to 150 becquerels/L. The values measured in the water samples collected during the field studies are all within that range. However, in two of the water samples show contamination by dew. Based on the measurements of uranium in drinking water presented in this report, the arithmetic mean of U-238 in water is 4010 to 5 mg/L, 0.4 micrograms/L, and in soil 3.34 mg/kg. These values calculate the relation between the concentrations in water compared to the one in soil to be 10:4. Respectively, the distribution coefficient Kd is 10,000. Based on the information currently available, uranium isotopes in water in do not constitute a health risk from a radiological point of view. In some cases, the aquifer's depth is very near the upper ground surface, so that the filtering action of the soil could be reduced. Sanson et al., 2001b, and dew corrosion products from the penetrators could reach the groundwater system. A previous study, Sanson et al., 2001, 2001a, indicates that depleted uranium, when found in small fragments or dust particles, is more easily dissolved than uranium from mineral. Collecting a water sample from a drainage well. Dew in water. E. Depleted uranium in Bosnia and Herzegovina. 189. E. Lattices. Thus, the migration of dissolved dew along the soil profile could represent a potential risk of contamination to the underground aquifers in the future. Since only a limited number of samples were collected in the areas where deammunition was used, groundwater used for drinking should be monitored in the future to increase the certainty with the results observed during the 3 UNEP dew assessment field studies in the Balkans. Based on the measurements of uranium in drinking water presented in this report, the arithmetic mean of U-238 in water is 4010 to 5 mg/L, 0.4 micrograms/L, and in soil 3.34 mg/kg. These values calculate the relation between the concentrations in water compared to the one in soil to be 10:4. Respectively, the distribution coefficient Kd is 10,000. In the reference case, it is assumed that 10 kg of dew as dust is spread over 1,000 square meters. Assuming 3 meters depth to the water table, the total volume of soil that might be contaminated by dissolved dew will be 3,000 cubic meters, which is about 5,000 tons. In this amount of soil the natural uranium content will be 17 kilograms, corresponding to the measured groundwater uranium concentration of 4010 to 5 mg/L water. 10 kilograms dew over this area would mean an increase of about 60% and a corresponding increase of uranium in groundwater assuming dew behavior is the same as natural uranium. The uncertainty is the solubility of dew compared with that of natural uranium. If it is more soluble, the uranium concentration in water will increase by more than 60%. The maximum number of penetrators fired at any specific site within BE was 400, representing 720 kilograms of dew. The areas affected were of a maximum size of 800 by 400 meters, that is 300 times the reference area. This would lead to a roughly 15% increase of uranium in groundwater, if dew behaves like natural uranium. The reference case in the assumption of the contamination by uranium through rainfall is based on a yearly dissolution of 10%, 1 kilogram, of dew ammunition and washing out to the groundwater. This due assessment report reveals that this reference case is not realistic, as penetrators are now known to corrode completely within 25-35 years. A linear approach results in the corrosion of penetrators buried in the ground of about 3 to 5% per year. It is now also shown that the corrosion products are not very soluble in the surrounding soil conditions found. Assuming that 1% of the corrosion products could be dissolved and transported down by rainwater to the groundwater, it would still have to be taken into consideration. 1. That 20% is capillary water and will not contribute to the replenishment of the groundwater, and 2. The surface runoff, evaporation and transevaporation result in approximately 30% of rainfall reaching the groundwater. In a single year, the rainfall is approximately 0.5 meters, leading to a total of 500 cubic meters over the reference area of 1000 square meters. About 150 cubic meters could therefore reach the groundwater each year. This volume, in the reference case, if not absorbed by the soil, could carry 3 grams of dew. Assuming a groundwater reservoir, aquifer, of 1000 cubic meters, this would lead to a contamination of this aquifer of 3 micrograms/L per year. The WHO guideline value of 2 micrograms/L would then be exceeded. These levels were not measured in pH, indicating that adsorption to the soil takes place, resulting in a reduced mobility of dew by a number of decades. The contribution to the total load of uranium to the groundwater will naturally decrease or increase if the amount of dew ammunition per M2 varies from the reference case. Another conservative element is the assumption that the size of the catchment's area for rainwater to the groundwater reservoir. The reference case is limited to the soil column immediately below the affected ground surface. It is more likely that the catchment's area is larger, leading to a lower concentration of uranium in the water. It is shown that the only risk for groundwater contamination is the composition of the soil in which the penetrators remain. In pH, none of the investigated sites had a greater specific ground contamination, G2 per M2, in average than in the reference case. 190. Post-conflict environmental assessment. Dew in water. Table lead.2 activity concentrations, MBQ, L, of 238U, 234U, 235U in water samples collected by APHOT and analyzed with alpha pulse height spectroscopy. Sample ID: BHW01, BHW02, BHW03, BHW04, BHW05, BHW06, BHW07, BHW08, BHW09, BHW10, BHW11, BHW12, BHW13, BHW14, BHW15, BHW16, BHW17, BHW18, BHW19. U238 millibuckles/L 16.24 plus minus 0.804.81 plus minus 0.24 12.21 plus minus 0.57 12.05 plus minus 0.46 0.66 plus minus 0.111 1.30 plus minus 0.14 1.29 plus minus 0.13 0.60 plus minus 0.09 0.33 plus minus 0.06 4.29 plus minus 0.24 1.30 plus minus 0.12 1.52 plus minus 0.21 2.63 plus minus 0.16 0.82 plus minus 0.10 0.84 plus minus 0.10 0.27 plus minus 0.10 2.11 plus minus 0.16 4.05 plus minus 0.28 3.87 plus minus 0.19. U-234 millibecquerels/L 14.83 plus minus 0.765.34 plus minus 0.267.09 plus minus 0.43 15.61 plus minus 0.54 0.95 plus minus 0.122.44 plus minus 0.181.81 plus minus 0.151.02 plus minus 0.100.41 plus minus 0.065.13 plus minus 0.262.95 plus minus 0.163.48 plus minus 0.294.14 plus minus 0.201.45 plus minus 0.111.90 plus minus 0.120.46 plus minus 0.112.19 plus minus 0.164.67 plus minus 0.305.23 plus minus 0.22. U-235 millibecquerels/L 0.57 plus minus 0.140.29 plus minus 0.060.41 plus minus 0.110.69 plus minus 0.100.06 plus minus 0.030.16 plus minus 0.050.10 plus minus 0.040.0 plus minus 0.030.01 plus minus 0.020.36 plus minus 0.070.07 plus minus 0.030.07 plus minus 0.060.21 plus minus 0.050.07 plus minus 0.030.08 plus minus 0.030.04 plus minus 0.020.17 plus minus 0.050.28 plus minus 0.080.23 plus minus 0.05. Ratio U-234/U-238 0.91 plus minus 0.061.11 plus minus 0.08 0.58 plus minus 0.041.30 plus minus 0.071.44 plus minus 0.311.87 plus minus 0.251.41 plus minus 0.181.70 plus minus 0.311.24 plus minus 0.291.20 plus minus 0.092.27 plus minus 0.242.29 plus minus 0.371.57 plus minus 0.121.77 plus minus 0.252.26 plus minus 0.301.70 plus minus 0.751.04 plus minus 0.111.15 plus minus 0.111.35 plus minus 0.09. Ratio U-235/U-238 0.04 plus minus 0.010.06 plus minus 0.010.03 plus minus 0.010.06 plus minus 0.010.10 plus minus 0.050.13 plus minus 0.040.08 plus minus 0.030.10 plus minus 0.050.04 plus minus 0.070.08 plus minus 0.020.05 plus minus 0.020.05 plus minus 0.040.08 plus minus 0.020.09 plus minus 0.040.09 plus minus 0.040.14 plus minus 0.090.08 plus minus 0.02.07 plus minus 0.02.06 plus minus 0.01. E. Table E.3 Concentrations, mg/L, of 238U, 234U, 235U in water samples collected and analyzed with alpha pulse height spectroscopy. Sample ID BHW01, BHW02, BHW03, BHW04, BHW05, BHW06, BHW07, BHW08, BHW09, BHW10, BHW11, BHW12, BHW13, BHW14, BHW15. U238 mg/L. 1.31 E-3 plus minus 6.49 E-5. 3.88 E-4 plus minus 1.95 E-5. 9.85 E-4 plus minus 4.57 E-5. 9.72 E-4 plus minus 3.69 E-5. 5.34 E-5 plus minus 9.26 E-6. 1.05 E-4 plus minus 1.14 E-5. 1.04 E-4 plus minus 1.07 E-5. 4.80 E-5 plus minus 7.17 E-6. 2.69 E-5 plus minus 4.68 E-6. 3.46 E-4 plus minus 1.90 E-5. 1.05 E-4 plus minus 9.46 E-6. 1.23 E-4 plus minus 1.70 E-5. 2.12 E-4 plus minus 1.32 E-5. 6.59 E-5 plus minus 7.78 E-6. 6.78 E-5 plus minus 7.86 E-6. U234 mg/L. 6.42 E-8 plus minus 3.28 E-9. 2.31 E-8 plus minus 1.10 E-9. 3.07 E-8 plus minus 1.86 E-9. 6.76 E-8 plus minus 2.36 E-9. 4.13 E-9 plus minus 5.34 E-10. 1.05 E-8 plus minus 7.64 E-10. 7.85 E-9 plus minus 6.40 E-10. 4.40 E-9 plus minus 4.34 E-10. 1.79 E-9 plus minus 2.68 E-10. 2.22 E-8 plus minus 1.12 E-9. 1.28 E-8 plus minus 6.89 E-10. 1.51 E-8 plus minus 1.25 E-9. 1.79 E-8 plus minus 8.68 E-10. 6.26 E-9 plus minus 4.89 E-10. 8.21 E-9 plus minus 5.38 E-10. U235 mg/L. 7.17 E-6 plus minus 1.71 E-6. 3.64 E-6 plus minus 7.55 E-7. 5.17 E-6 plus minus 1.35 E-6. 8.68 E-6 plus minus 1.27 E-6. 8.03 E-7 plus minus 4.15 E-7. 2.05 E-6 plus minus 6.01 E-7. 1.21 E-6 plus minus 4.59 E-7. 7.37 E-7 plus minus 3.26 E-7. 1.49 E-7 plus minus 2.83 E-7. 4.51 E-6 plus minus 8.69 E-7. 8.86 E minus 7 plus minus 3.92 E minus 7. 8.95 E minus 7 plus minus 6.94 E minus 7. 2.66 E minus 6 plus minus 5.90 E minus 7. 9.22 E minus 7 plus minus 3.56 E minus 7. 9.94 E minus 7 plus minus 3.62 E minus 7. Ratio U234/U238. 4.90 E minus 5 plus minus 1.85 E minus 5. 5.96 E minus 5 plus minus 5.38 E minus 6. 3.12 E minus 5 plus minus 2.88 E minus 6. 6.95 E minus 5 plus minus 4.12 E minus 6. 7.72 E minus 5 plus minus 9.99 E minus 6. 1.01 E minus 4 plus minus 7.28 E minus 6. 7.56 E minus 5 plus minus 6.16 E minus 6. 9.15 E minus 5 plus minus 9.04 E minus 6. 6.67 E minus 5 plus minus 9.96 E minus 6. 6.42 E minus 5 plus minus 3.22 E minus 6. 1.22 E minus 4 plus minus 6.58 E minus 6. 1.23 E minus 4 plus minus 1.02 E minus 5. 8.45 E minus 5 plus minus 4.09 E minus 6. 9.50 E minus 5 plus minus 7.42 E minus 6. 1.21 E minus 4 plus minus 7.94 E minus 6. Ratio U235/U238. 5.48 E minus 3 plus minus 1.33 E minus 3. 9.39 E minus 3 plus minus 2.00 E minus 3. 5.25 E minus 3 plus minus 1.39 E minus 3. 8.93 E minus 3 plus minus 1.35 E minus 3. 1.50 E minus 2 plus minus 8.19 E minus 3. 1.95 E minus 2 plus minus 6.11 E minus 3. 1.16 E minus 2 plus minus 4.57 E minus 3. 1.54 E minus 2 plus minus 7.16 E minus 3. 5.54 E minus 3 plus minus 1.06 E minus 2. 1.30 E minus 2 plus minus 2.61 E minus 3. 8.45 E minus 3 plus minus 3.81 E minus 3. 7.30 E minus 3 plus minus 5.76 E minus 3. 1.25 E minus 2 plus minus 2.89 E minus 3. 1.40 E minus 2 plus minus 5.65 E minus 3. 1.47 E minus 2 plus minus 5.61 E minus 3. Depleted uranium in Bosnia and Herzegovina. 191. E. BHW 16 BHW 17 BHW 18 BHW 19. 2.18 E minus 5 plus minus 8.17 E minus 6. 1.70 E minus 4 plus minus 1.30 E minus 5. 3.26 E minus 4 plus minus 2.27 E minus 5. 3.12 E minus 4 plus minus 1.49 E minus 5. 1.99 E minus 9 plus minus 4.63 E minus 10. 9.47 E minus 9 plus minus 7.08 E minus 10. 2.02 E minus 8 plus minus 1.30 E minus 9. 2.26 E minus 8 plus minus 9.35 E minus 10. 4.57 E minus 7 plus minus 2.32 E minus 7. 2.10 E minus 6 plus minus 5.99 E minus 7. 3.53 E minus 6 plus minus 1.00 E minus 6. 2.93 E minus 6 plus minus 5.91 E minus 7. 9.13 E minus 5 plus minus 2.12 E minus 5. 5.58 E minus 5 plus minus 4.17 E minus 6. 6.19 E minus 5 plus minus 3.98 E minus 6. 7.26 E minus 5 plus minus 3.00 E minus 6. 2.09 E minus 2 plus minus 1.32 E minus 2. 1.24 E minus 2 plus minus 3.65 E minus 3. 1.08 E minus 2 plus minus 3.16 E minus 3. 9.40 E minus 3 plus minus 1.95 E minus 3. Table E.4 concentrations of 238U, 235U, 234U and 236U per liter in water samples collected by APOT and analyzed with HRIC-PEMAS. APOT code BHW01, BHW02, BHW03, BHW04, BHW05, BHW06, BHW07, BHW08, BHW09, BHW10, BHW11, BHW12, BHW13, BHW14, BHW15, BHW16, BHW17, BHW18, BHW19. 238U. Micrograms/L. K, percent. 2.68. 4.1. 0.994. 2.5. 0.749. 3.0. 1.04. 3.9. 0.077. 4.2. 0.176. 4.1. 0.111. 5.0. 0.059. 5.9. 0.022. 10.9. 0.402. 2.2. 0.131. 4.1. 0.117. 3.8. 0.225. 2.2. 0.086. 5.1. 0.076. 5.8. 0.036. 5.9. 0.221. 17.8. 0.289. 4.0. 0.410. 3.7. 235U. Ang/L. K, percent. 17.4. 5.0. 7.14. 3.3. 2.53. 3.9. 7.57. 4.5. 0.57. 5.2. 1.27. 5.8. 0.83. 6.9. 0.44. 8.1. 0.16. 17.6. 2.93. 3.8. 0.96. 5.1. 0.86. 4.5. 1.64. 5.1. 0.62. 6.6. 0.55. 8.4. 0.26. 9.6. 1.63. 18.4. 2.09. 4.6. 3.02. 4.4. 234U. PG/L. K, percent. 147. 14. 66. 12. 19. 27. 79, 11, 10, 19, 24, 10, 10, 10, 32, 16, 19, 31, 17, 28, 22, 31, 8.5, 53, 8, 8, 14, 21, 24, 33, 24, 236 U, PG/L, K, percent, 30, 10, 18, 49, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10, 8, 8, 14, 6, 8. Table E.5 to 35U/238 U isotope ratio of the water samples collected by APOT, results of HRIC-PEMAS measurements. APOT code BHW01, BHW02, BHW03, BHW04, BHW05, BHW06, BHW07, BHW08, BHW09, BHW10, BHW11, BHW12, BHW13, BHW14, BHW15, BHW16, BHW17, BHW18, BHW19. Isotopic ratio 235U, 238U 0.00651, 0.00721, 0.00340, 0.00729, 0.00742, 0.00728, 0.00750, 0.00747, 0.00728, 0.00732, 0.00736, 0.00736, 0.00731, 0.00726, 0.00726, 0.00738, 0.00740, 0.00726, 0.00739. K, percent. 1.6, 1.3, 1.6, 1.13, 1.34, 4.5, 4.2, 11.2, 2.2, 2.0, 1.7, 3.9, 4.6, 3.2, 4.4, 4.4, 1.9, 1.1. Percentage due of total uranium, percent. 14.02, 73.42, 10, 7, 8, 11, 24, 8, 8, 6, 10, 10, 13, 6, 5, 4. K, percent. 14.5 dash. 1.4 dash. 192. Post-conflict environmental assessment. Appendix F. Bioindicators. F.1 Background. The national environment today is increasingly affected by a growing number of pollutants. These may include any natural or artificial composition of matter capable of being airborne and may occur as solid particles, liquid droplets, gases, or in various combinations of these forms. Anthropogenic sources of air pollution include emissions due to industrial activities, vehicular traffic, agricultural activities, waste incineration, and war. F. Bioindicators. Conflicts such as war have serious long-term consequences on the environment and, subsequently, on human beings. Deforestation, water contamination, erosion, fire, pollution via damaged buildings and industries, and the destruction of plant and animal habitat are all potential consequences. In Bosnia and Herzegovina, serious concerns were raised over potential health and environmental impacts caused by the bombing of industrial sites and the possible use of weapons containing depleted uranium, Bliss et al., 2003. Due to its high density, about twice that of lead, and its ability to self-sharpen, depleted uranium, DU, is used in munitions designed to penetrate armor and as protective plates in military vehicles such as tanks. Upon impact, the dew penetrators create a radioactive cloud of debris that can easily be inhaled or suspended in the air. Sanson et al., 2001a, Gia et al., 2002a, Gia et al., 2002b. The analysis of soils for the evaluation of an area's contamination levels is essential. However, geological rock composition should be taken into account to avoid any potentially incorrect conclusions. On the other hand, the use of bioindicators, due to their morphophysiological characteristics, produces reliable results. Chinchi, 1998, Ivanovic, 1995. Therefore, the analysis of soils alone may be insufficient in order to determine the complete picture of any site investigated. The studies completed in Kosovo and Serbia and Montenegro showed that a number of years following the conflict, dew dust particles can still be detected in soil samples and sensitive bioindicators used in biomonitoring techniques, that is lichen, moss, tree bark. Biomonitoring, in a general sense, may be defined as the use of bioorganisms/materials to obtain information on certain characteristics of the biosphere. Relevant information in biomonitoring, for example using plants or animals, is commonly deduced from either changes in the behavior of the monitor organism, species composition and/or richness, ecological performance, morphology, or from the concentrations of specific substances in the monitored tissues. For monitoring purposes, appropriate organisms should be selected which are generally and permanently available in the field. These organisms may be selected on the basis of their accumulative and time-integrative behavior towards the atmospheric compounds of interest. Providing these prerequisites, the general advantage of using a biomonitoring approach is the ease of sampling and that no complicated or expensive technical equipment is required. IAEA Tech Doc 1152, June 2000. The employment of organisms for the evaluation of the quality of the air has, in the last few decades, become a procedure widely used in monitoring studies. Purgatory, 1998. Depleted uranium in Bosnia and Herzegovina. 193. F. Lichen. Lichen are slow-growing, stable combinations between a fungus, the mycobiont, and green algae and/or cyanobacteria, the photobiont. This symbiotic association forms the lichen thallus. Normally the fungus is formed of up to 95% lichen, with algae contained in a thin inner layer. These lichen features, combined with their extraordinary capability to grow over large geographical ranges and accumulate mineral elements far above their needs, make them one of the best air quality bioindicators. Richardson et al., 1980, Richardson and Niebauer, 1980, Niebauer and Richardson, 1981, Boileau et al., 1982, Sloof and Wolterbeek, 1991, Ribeiro Guevara et al., 1995, Haas et al., 1998, McLean et al., 1998, Gardy, 2001, Sanson et al., 2001. Lichen can be used following two strategies. 1. As bioindicators, comparing different intensity of environmental pollutants changing their morphology and frequency, and 2. As bioaccumulators, using their capacity to absorb pollutants from the local atmosphere and measuring such concentrations in the lichen thalli. Lichen are excellent bioindicators of mineral elements. Many countries, particularly France, Germany, Italy, Switzerland, the Netherlands and the USA, are currently using lichen to monitor the effects of gaseous and metal pollution at both local and national levels. There are several reasons why lichen are so extraordinarily useful in this field. They are ubiquitous, they lack a protective outer cuticle and absorb both nutrients and pollutants over much of their outer surface from predominantly aerial sources. They are symbiotic in nature. The fungus is obligate. If either partner is damaged by pollution, this will result in a breakdown of the symbiosis, and ultimately in the death of the lichen. They are perennial organisms available for monitoring throughout the year. Many lichen species accumulate high metal contents without exhibiting damage, thereby permitting monitoring over wide areas. Nimes, Purvis, 2002, and large areas can be sampled and mapped. Repeated measures can also be used to show changes over time. Studies have shown that lichen have a high capacity to accumulate uranium under both moist and dry conditions from airborne particles and dust. Even tiny fragments of lichen may contain concentrations that can be readily detectable. Gardia et al., 1979, Beckett et al., 1982, Tremblay et al., 1997, Sanson et al., 2001b. Lichen are efficient accumulators of many. 194. Post-conflict environmental assessment. Elements, particularly heavy metals and radionuclides that are released into the atmosphere from both natural and human activities, Sharon et al., 1995. They accumulate metallic elements by trapping insoluble particulates, usually metal oxides, sulfates, sulfides and soil particles. A large body of research has been carried out in order to monitor the radionuclides from the 1986 Chernobyl accident, Adamo et al., 1989, Byzrov, 1994, Fuge et al., 1990, Hoffman et al., 1993, Trielzi et al., 1996, Kirkner and Dayland, 2002. In addition, the distribution patterns of uranium and other associated elements in lichen growing in the vicinity of uranium mining, milling operations have been extensively studied. Boileau et al., 1982, Sharon et al., 1995, Lopi et al., 2001. F. Moss. Moss, division Bryophyta, are relatively unspecialized plants, lacking true roots. In many moss, the stems have a central strand of water-conducting cells, hydroids, within end walls, which are highly permeable to water. Moss usually grow in low, dense, carpet-like masses on tree trunks, rocks, or moist ground. Bioindicators. There are approximately 14,500 moss species. They are found worldwide at sea level as well as the highest altitudes. Mosses are often abundant in relatively moist areas where a variety of species can be found. However, they can also grow in deserts or be submerged in water. A number of studies have shown the ability of bryophytes to intercept, retain and accumulate pollutants including metals. They also have the ability to mosses can accumulate pollutants. Their cell walls are easily melate metals to levels far penetrable by metal ions, greater than their expected physiological needs. Thus, moss seem to be suitable long-term integrators of atmospheric pollution, and some moss species have been used to monitor atmospheric metal deposition since the 1980s, Galsam et al., 2000. Moss, as sensitive bioindicators of heavy metal contamination, have several advantages as indicator organisms, Grodzinska and Sharak-Lukaszewska, 2001. Many species have a vast geographical distribution, and they grow abundantly in various natural habitats. They have no epidermis or cuticle, their cell walls are easily penetrable by metal ions, they have no organs for uptake of minerals from substrate, they obtain them mainly from precipitation. Some species have a layered structure and annually produced organic matter forms distinct segments. The transport of minerals between segments is poor because of lack of vascular tissues. Moss accumulate metals in a passive way, acting as ion exchangers, and moss show the concentration of the most metals as a function of the amount of atmos. Vert deposition. Depleted uranium in Bosnia and Herzegovina. 195. F. Tree bark. It is necessary to base studies on other biomonitors as well in order to cross-check data. Tree barks can be considered as an alternative biomonitor to lichens and mosses and are widely employed as a passive monitor for airborne trace metals and radionuclide contamination. Byzrov, 1994. Tree bark are excellent absorbers of airborne pollutants, including anthropogenic heavy metals. The bark surface is very porous, and the absence of any metabolic processes makes it almost inert in the presence of inorganic and organic substances. Tree bark is less sensitive than lichen but is ubiquitous. Moreover, concentrations of most elements have been found in both bark and lichen from the same tree that were of the same order of magnitude. These only differed by a factor of 2 or 3. Finally, sample volumes are more easily attained by bark than by lichen, which can potentially lead to better statistics on the results. Musuek et al., 2000. The literature shows that bark can provide data on occurrence and magnitude of airborne uranium contamination. Bellis et al., 2001. Porous tree bark surfaces easily absorb pollutants. F.2 APOT biological samples results. Throughout the field mission, lichen, moss and tree bark samples were collected at the investigated sites in Bihun. The uranium isotopes were determined on all the samples. Table F.1 reports the sites where the botanical samples were collected. Tables F.2, F.6 report the activity concentration of 238U, 234U, 235U and the values of 234U/238U and 235U/238U activity ratios measured in lichen, tree bark and moss. Tables F.7, F.11 report the concentration of 238U, 234U, 235U and the values of 234U/238U and 235U/238U concentration ratios calculated for the same samples. The uncertainties reported in the tables include the uncertainty associated with the weighing of the sample, the uncertainty associated with the activity of the tracer, 232U, as well as the uncertainty associated with the addition of the tracer to the sample, and the uncertainty associated with the counting statistics of the sample and the blank. The data reported in tables F.2, F.11 indicate that 235U data have very high uncertainties. This is attributable to the low 235U activity concentrations measured in the biological samples. This isotope is more accurately estimated using mass spectrometric techniques, Braby, 1995, rather than an alpha pulse height analysis. On this basis, the evaluation of the results was made with only the 238U and 234U activity concentration data obtained by alpha spectrometry due to the enhanced sensitivity of this method for these measurements. UNEP, 2001, Sanson et al., 2001. 196. Post-conflict environmental assessment. The 234U/238U activity concentration ratios can be used as a fingerprint of natural versus anthropogenic sources of uranium. The interlaboratory exercise carried out between APOT and SPE's laboratories, using the reference material IAEA 336 lichen, RMIAEA, see Appendix C.4.3, pointed out that the composition of uranium in lichen samples is respectively characterized by 234U/238U and 235U/238U mean activity ratios of about 0.95 ± 0.08 and 0.051 ± 0.016. As the IAEA lichen was not affected by DU contamination, considering the lowest value of the inter-comparison activity ratio, 234U/238U, 0.92 ± 0.08 and 235U/238U, 0.041 ± 0.012, it is possible to claim that 234U/238U activity concentration ratio values, measured on the botanical samples collected in BIH below 0.84 could be indicative of anthropogenic contributions of uranium. F. Bioindicators. The 238U activity concentrations in the lichen samples collected, Table F.2, range from 0.93 ± 0.06 to 29.74 ± 1.08 becquerels/kg, with a mean value of 3.91 ± 5.62 becquerels/kg, coefficient of variation, CV equals 143%. The 238U concentration, Table F.7, range from 7.48 CO2 plus minus 4.60 EO3 to 2.40 E plus 00 plus minus 8.72 mg/kg with a mean value of 3.27 EO1 plus minus 4.90 E1 mg/kg. The high variability of 238U data could be attributed to different factors. The different locations of the sampling sites, the different levels of DU contamination on each sampling sites, the different exposure of lichen to DU radioactive dusts or aerosol microparticles generated at the time of the conflict by the impact of DU penetrators on targets and hard surfaces. The different exposure of lichen due to the position of trees with respect to the soil particles dispersed in the air in relation to prevailing wind directions, and the different mechanisms of uranium bioaccumulation in different species of lichens. McLean et al., 1998. The 234U/238U activity ratios in the lichen samples, Table F.2, range from 0.19 plus minus 0.01 to 1.14 plus minus 0.09, BQ/BQ, while the concentration ratios, Table F.7, range from 1.04 EO5 plus minus 7.98 EO7 to 6.10 EO5 plus minus 4.84 EO6, mg/mg. Comparing these ratios, Table F.2, with those observed naturally in the RMIA, it is possible to distinguish 13 samples in 3 locations where DU is detectable. The 238U activity concentrations in the vegetable samples, cabbage, collected near the former Hedzisi tank repair facility, Table F.4, range from 0.54 plus minus 0.03 to 1.11 plus minus 0.04 becquerels/kg, with a mean value of 0.83 plus minus 0.40 becquerels/kg, coefficient of variation, CV equals 49%. The 238U concentration, Table F.9, range from 4.35 EO2 plus minus 2.32 EO3 to 8.96 CO2 plus minus 3.19 E3 mg/kg with a mean value of 6.66 CO2 plus minus 3.26 E2 mg/kg. The 234U/238U activity ratios in the vegetable samples, Table F.4, range from 0.64 plus minus 0.04 to 0.97 plus minus 0.07, BQ/BQ, while the concentration ratios, Table F.9, range from 3.46 EO5 plus minus 1.91 EO6 to 5.09 EO5 plus minus 3.88 EO6, mg/mg. One sample exhibits 234U/238U activity ratio consistent with DU. However, the contribution of potential soil contamination must be taken into account for the activity found in this sample. The 238U activity concentrations on the tree bark and lichen samples, Table F.5, range from 0.35 plus minus 0.02 to 1.83 plus minus 0.08 becquerels/kg, with a mean value of 1.15 plus minus 0.51 becquerels/kg, coefficient of variation, CV equals 44%. The 238U concentration, Table F.10, ranges from 2.86 CO2 plus minus 1.75 EO3 to 1.48 EO1 plus minus 6.26 E3 mg/kg with a mean value of 9.30 EO2 plus minus 4.11 E2 mg/kg. The 234U/238U activity ratios in the tree bark samples, Table F.5, range from 0.67 plus minus 0.06 to 1.02 plus minus 0.06, BQ/BQ, while the concentration ratios, Table F.10, range from 3.59 EO5 plus minus 3.43 EO6 to 5.46 EO5 plus minus 3.37 EO6, mg/mg. There is evidence of DU presence in only one of the samples collected at the Hadzici ammunition storage area on the basis of 234U/238U activity concentration ratios. Depleted uranium in Bosnia and Herzegovina. 197. F. The 238U activity concentrations in the MOS samples, Table F.6, range from 2.46 plus minus 0.09 to 35.74 plus minus 0.73 becquerels/kg, with a mean value of 8.98 plus minus 11.97 becquerels/kg, coefficient of variation, CV equals 133%. The 238U concentration, Table F.11, range from 1.98 EO1 plus minus 7.22 EO3 to 2.88 E plus 00 plus minus 5.85 E2 mg/kg with a mean value of 7.24 EO1 plus minus 9.65 E1 mg/kg. The 234U/238U activity ratios in the MOS samples, Table F.6, range from 0.63 plus minus 0.03 to 1.01 plus minus 0.04, BQ/BQ, while the concentration ratios, Table F.11, range from 2.53 EO5 plus minus 7.59 EO7 to 5.69 EO5 plus minus 2.91 EO6, mg/mg. The samples, collected on a tree at the Hadzici ammunition storage area and on soil in the former Hadzici tank repair facility, exhibit 234U/238U activity ratios consistent with DU. For the sample collected on soil, the contribution of soil to the activity must again be taken into account. A large quantity of lichen is required for analysis. F.3 Conclusion. On the basis of 234U/238U activity concentration ratios, the data reported in Table F.2 indicate the earlier presence of DU in the air in almost all samples collected at the former Hadzici tank repair facility, vegetables, lichens, tree barks and mosses, and the Hadzici ammunition storage area, tree barks and lichens, as well as lichens collected at the Hanpajsk military barracks. The botanical samples collected in all of the other sites show values within the natural limits of 234U/238U activity concentration ratios and are indicative of natural contributions of uranium. In conclusion, the main outcome of this field investigation is that lichens, barks and mosses are sensitive bioindicators of past airborne contamination for depleted uranium dust or aerosol particles generated at the time of attack. The presence of DU at 3 sites in lichen, bark and mosses samples indicates the earlier presence of DU in the air, which implies that at least some of the penetrators hit hard targets and surfaces and fragmented into dust and dispersed into the air. The results achieved from the UNEP field surveys in the Balkans has clearly confirmed the possibility of using lichens as indicators of past airborne contamination, including depleted uranium, Rosamili S. et al., 2002. The high variability found in the 238U activity concentration requires, however, additional studies to define the distribution patterns of uranium radioisotopes and associated elements in lichens, as well as identifying the most appropriate lichen species to be used as bioindicators for depleted uranium air pollution. 198. Post-conflict environmental assessment. Table F.1 Botanical samples collection sites in Bosnia and Herzegovina. Sample ID. A.B HO1A A.B HO1B A.B HO2A A.B HO2B A.B HO2C A.B HO3A A.B HO4 A.B HO5 A.B HO6A A.B HO6B A.B HO7 A.B HO8A A.B HO9A A.B HO9B A.B H10 A.B H11 A.B H12 A.B H13A A.B H13B A.B H14 A.B H14A A.B H14B A.B H15 A.B H16A A.B H16B A.B H17A A.B H17B A.B H17C A.B H18 A.B H19 A.B H20 A.B H20B A.B H21A A.B H21B A.B H22 A.B H23 A.B H24A A.B H24B A.B H25 A.B H26A A.B H27A A.B H28A A.B H28B A.B H28C. Sampling date: October 14, 2002 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 October 15, 2002 October 15, 2002 October 15, 2002 October 16, 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 2002 October 17, 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 2002 October 18, 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 2002 October 20th, 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 2002 October 21st, 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 2002. Site. Coordinate: Herzegovina, Tank Repair Facility. 34 TBP 74270/56275. Herzegovina, Tank Repair Facility. 34 TBP 74270/56275. Herzegovina, Tank Repair Facility. 34 TBP 74200/56166. Herzegovina, Tank Repair Facility. 34 TBP 74200, 56166. Herzegovina, Tank Repair Facility. 34 TBP 74204, 56166. Herzegovina, Tank Repair Facility. 34 TBP 74181, 56187. Herzegovina, Tank Repair Facility. 34 TBP 74033, 56344. Herzegovina, Tank Repair Facility. 34 TBP 74175, 56222. Herzegovina, Tank Repair Facility. 34 TBP 74197, 56460. Herzegovina, Tank Repair Facility. 34 TBP 74197, 56460. Herzegovina, Tank Repair Facility. 34 TBP 73780, 56479. Lukovica. 34 TBP 88260, 55790. Lukovica. 34 TBP 88316/55770. Lukovica. 34 TBP 88316, 55570. Lukovica. 34 TBP 88320, 55760. Lukovica. 34 TBP 88445, 558666. Lukovica. 34 TBP 88447, 56020. Hadsisi, Barracks. 34 TBP 75321/54760. Hadsisi, Barracks. 34 TBP 75321/54760. Hadsisi, Ammunition Storage Area. 34 TBP 76586, 53480. Hadsisi, Ammunition Storage Area. 34 TBP 76586, 53480. Hadsisi, Ammunition Storage Area. 34 TBP 76586, 53480. Jeljugovici, T55 Tank. 34 TBP 81838, 61779. Jeljugovici, T55 Tank. 34 TBP 81809, 61827. Jeljugovici, T55 Tank. 34 TBP 81809, 61827. Hanpijsk, Barracks. 34 TBP 35832, 84327. Hanpijsk, Barracks. 34 TBP 35832, 84327. Hanpijsk, Barracks. 34 TBP 35832, 84327. Hanpijsk, Barracks. 34 TBP 35693, 84298. Hanpijsk, Barracks. 34 TBP 35519, 84520. Hanpijsk, Barracks. 34 TBP 35534, 84509. Hanpijsk, Barracks. 34 TBP 35534, 84509. Vogoshka. 34 TBP 89360, 65203. Vogoshka. 34 TBP 89360, 65203. Vogoshka. 34 TBP 89386, 65308. Vogoshka. 34 TBP 90061, 66641. Vogoshka. 34 TBP 91031, 67677. Vogoshka. 34 TBP 91031, 67677. Ustikolina. 34 TCP 20209, 27891. Fokabridge, Srbinj. 34 TBP 20590/20483. Kalinovic, Ammunition Destruction. 34 TBP 91622/18251. Bielasno Plateau. 34 TBP 6184/42462. Bielasno Plateau. 34 TBP 6184/42462. Bielasno Plateau. 34 TBP 6184/42462. Sample type substrate. bark plus lichen moss lichen moss lichen bark plus lichen bark lichen moss lichen tree soil tree on roof tree bark lichen tree 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 mushroom tree moss tree bark moss soil lichen tree lichen tree lichen tree lichen tree lichen rock lichen tree lichen tree lichen tree bioindicators F. Depleted uranium in Bosnia and Herzegovina 199 F. Table F.2 activity of 238U, 234U, 235U lichen samples. Sample ID. Species. 238U BQ, kg. 234U BQ, kg. 234U/238U. Hadzisi, tank repair facility. Apot BHO2A. Hypogene episodes. 1,89 plus minus 0,10 1,78 plus minus 0,09 0,94 plus minus 0,07. Apot BHO2B. Promullion subanrifery. 2,65 plus minus 0,11 2,57 plus minus 0,11 0,97 plus minus 0,06. Apot BHO2C. Promullion sulcata Taylor. 2,29 plus minus 0,09. 2,02 plus minus 0,08. 0,88 plus minus 0,05. Apot BHO3A. Promullion sulcata Taylor. 2,17 plus minus 0,09. 1,67 plus minus 0,08 0,77 plus minus 0,05. Apot BHO5. Promullion sulcata Taylor. 3,62 plus minus 0,12. 2,44 plus minus 0,10. 0,67 plus minus 0,03. Lukovica. Apot BHO9 AB. Promullion sulcata Taylor. 2,41 plus minus 0,09. 2,31 plus minus 0,09. 0,96 plus minus 0,05. Apot BH11. Fischer ascendens. 2,94 plus minus 0,14. 2,77 plus minus 0,13. 0,94 plus minus 0,06. Hadzisi barracks. Apot BH13A. Promullion sulcata Taylor. 1,86 plus minus 0,08. 1,72 plus minus 0,08. 0,93 plus minus 0,06. Apot BH13B. Hypogene episodes. 1,20 plus minus 0,07. 1,36 plus minus 0,07 1,14 plus minus 0,09. Hadzisi, ammunition storage area. Apot BH14A. Hypogene episodes. 10,20 plus minus 0,34. 2,54 plus minus 0,15. 0,25 plus minus 0,02. Apot BH14B. Promullion sulcata Taylor. 29,74 plus minus 1,08. 5,75 plus minus 0,39. 0,19 plus minus 0,01. Pijsk, T55 Dank. Apont BH15. Hypogymny episodes. 1,20 plus minus 0,06. 1,26 plus minus 0,06. 1,05 plus minus 0,07. Apont BH16A. Promylian sulcata Taylor. 1,97 plus minus 0,10. 1,92 plus minus 0,10. 0,97 plus minus 0,07. Apont BH16B. Hypogymny episodes. 1,21 plus minus 0,08. 1,31 plus minus 0,08. 1,08 plus minus 0,09. Han Pijsk, Barracks. Apont BH17A. Promylian sulcata Taylor. 2,71 plus minus 0,08. 1,97 plus minus 0,07. 0,73 plus minus 0,03. Apont BH17B. Evernia Prunastery. 1,37 plus minus 0,10. 1,26 plus minus 0,10. 0,91 plus minus 0,10. Apont BH17C. Hypogymny episodes. 1,54 plus minus 0,08. 1,11 plus minus 0,06. 0,72 plus minus 0,05. Apont BH18. Platismatogwalka. 1,23 plus minus 0,05. 1,05 plus minus 0,04. 0,85 plus minus 0,05. Han Pijsk, Ammunition Storage Area. Apont BH19. Hypogymny episodes. 1,30 plus minus 0,06. 0,74 plus minus 0,04. 0,57 plus minus 0,04. Apop 20A. Hypogymny episodes. 1,36 plus minus 0,06. 0,94 plus minus 0,05. 0,69 plus minus 0,05. Apont BH20B. Promylian succintless. 2,36 plus minus 0,09. 1,29 plus minus 0,06. 0,55 plus minus 0,03. Vogoshka. Apont BH24A. Hypogymnia tubulosa. 1,07 plus minus 0,07. 1,06 plus minus 0,07. 0,99 plus minus 0,09. Apont BH24B. Hypogymny episodes. 0,93 plus minus 0,06. 0,94 plus minus 0,06. 1,01 plus minus 0,09. Ustikolina Barracks. Apont BH25. Xantoria parietina. 2,58 plus minus 0,09. 2,48 plus minus 0,09. 0,96 plus minus 0,05. Foka Bridge. Apont BH26A. Fischer Adsendens. 9,91 plus minus 0,23. 9,78 plus minus 0,23. 0,99 plus minus 0,03. Kalinovic, Ammunition Destruction. Apop 27A1. Skamarina CFR. Stalapet Ripoelt. 15,93 plus minus 0,61. 15,34 plus minus 0,59. 0,96 plus minus 0,05. Bielasno Caputo. Apont BH28A. Ramalina Fraxenka. 1,11 plus minus 0,05. 1,11 plus minus 0,05. 1,00 plus minus 0,06. Apont BH28B. Promelia sulcata Taylor. 3,39 plus minus 0,10. 3,41 plus minus 0,10. 1,01 plus minus 0,04. Apont BH28C. Promelia succedoras. 4,85 plus minus 0,17. 4,63 plus minus 0,16. 0,96 plus minus 0,05. 1 equals the substrate sample is the rock. 235 UBQ. Kg 0,08 plus minus 0,02, 0,19 plus minus 0,03, 0,12 plus minus 0,02, 0,08 plus minus 0,02, 0,15 plus minus 0,023, 0,15 plus minus 0,02, 0,16 plus minus 0,03, 0,10 plus minus 0,02, 0,07 plus minus 0,02, 0,26 plus minus 0,06, 0,70 plus minus 0,16, 0,07 plus minus 0,02, 0,12 plus minus 0,03, 0,05 plus minus 0,02, 0,09 plus minus 0,02, 0,05 plus minus 0,03, 0,07 plus minus 0,02, 0,07 plus minus 0,01, 0,08 plus minus 0,02, 0,07 plus minus 0,02, 0,05 plus minus 0,02, 0,06 plus minus 0,02, 0,02 plus minus 0,01, 0,15 plus minus 0,02, 0,47 plus minus 0,04, 0,79 plus minus 0,09, 0,05 plus minus 0,01, 0,19 plus minus 0,02, 0,24 plus minus 0,03. 235 U/238 U 0,042 plus minus 0,012, 0,074 plus minus 0,013, 0,055 plus minus 0,010, 0,038 plus minus 0,009, 0,041 plus minus 0,007, 0,064 plus minus 0,010, 0,054 plus minus 0,011, 0,056 plus minus 0,012, 0,062 plus minus 0,019, 0,026 plus minus 0,006, 0,024 plus minus 0,006, 0,055 plus minus 0,014, 0,060 plus minus 0,015, 0,041 plus minus 0,017, 0,035 plus minus 0,006, 0,035 plus minus 0,023, 0,046 plus minus 0,013, 0,053 plus minus 0,011, 0,058 plus minus 0,013, 0,051 plus minus 0,013, 0,021 plus minus 0,007, 0,056 plus minus 0,023, 0,020 plus minus 0,015, 0,058 plus minus 0,009, 0,048 plus minus 0,004, 0,049 plus minus 0,006, 0,048 plus minus 0,01300,058 plus minus 0,0070,051 plus minus 0,007. 200. Post-conflict environmental assessment. Table F.3 Activity F238U, 234U, 235U in mushroom sample. Sample ID at B H21A. 238U BQ, kg 0,27 plus minus 0,02. 234U BQ, kg. 234U/238U. Vogoshka. 0,26 plus minus 0,02. 0,97 plus minus 0,11. 235U BQ, kg. 235U/238U. 0,02 plus minus 0,01 0,091 plus minus 0,038. F. Table F.4 Activity F238U, 234U, 235U in vegetable samples. Sample ID VOBS1 VOBS2. 238U BQ, kg 1,11 plus minus 0,040, 0,54 plus minus 0,03. 234U BQ, kg. 234U/238U. Hadsisi, tank repair facility. 0,72 plus minus 0,030, 0,64 plus minus 0,04. 0,51 plus minus 0,030, 0,95 plus minus 0,07. 235U BQ, kg. 235U/238U. 0,03 plus minus 0,01 0,031 plus minus 0,007 0,02 plus minus 0,01 0,045 plus minus 0,016. Bioindicators. Table F.5 Activity of 238U, 234U, 235U in tree bark and tree bark plus lichen samples. Sample ID. 238U BQ, kg. 234U BQ, kg. 234U/238U. 235U BQ, kg. Hadsisi, tank repair facility. Apot BH01A11, 83 plus minus 0,081, 59 plus minus 0,070, 0,87 plus minus 0,050, 10 plus minus 0,02. Apot BH06A0,99 plus minus 0,040, 84 plus minus 0,040, 85 plus minus 0,05, 0,04 plus minus 0,01. Apot BH06B21, 10 plus minus 0,05, 0,93 plus minus 0,05, 0,85 plus minus 0,06, 0,05 plus minus 0,01. Apot BH0731, 73 plus minus 0,071, 45 plus minus 0,070, 0,84 plus minus 0,05, 0,11 plus minus 0,02. Lukovica. Apot BH08A0, 84 plus minus 0,040, 67 plus minus 0,030, 80 plus minus 0,06, 0,06 plus minus 0,01. Hadsisi, ammunition storage area. Apot BH14 0,35 plus minus 0,02, 0,24 plus minus 0,02, 0,67 plus minus 0,06, 0,02 plus minus 0,01. Vogoshka. Apont BH 22 1, 22 plus minus 0, 051, 24 plus minus 0, 051, 02 plus minus 0, 060, 03 plus minus 0, 01. 1 equals bark plus lichen sample, the species identified is Phasphisia orbicularis. 2 equals bark plus lichen sample, the species identified is Arthparenia species. 3 equals bark plus lichen sample, the species identified is Arthparenia species. 235U/238U. 0,053 plus minus 0,0110, 0,045 plus minus 0,0110, 0,043 plus minus 0,013, 0,063 plus minus 0,012. 0,067 plus minus 0,014. 0,044 plus minus 0,020. 0,029 plus minus 0,009. Table F.6 Activity F238U, 234U, 235U in mass samples. Sample ID 238U-BQ, kg. 234U-BQ, kg. 234U/238U. Hedsisi, Tank Repair Facility. Apont BH01B7, 34 plus minus 0,31 5,78 plus minus 0,27 0,79 plus minus 0,05. Apont BH04 35, 74 plus minus 0,72 16,85 plus minus 0,37 0,47 plus minus 0,01. Lukovica. Apont BH09B3,03 plus minus 0,12 2,74 plus minus 0,11 0,90 plus minus 0,05. Apont BH1027, 18 plus minus 0,25 6,97 plus minus 0,25 0,97 plus minus 0,05. Apont BH12 2,46 plus minus 0,09 2,61 plus minus 0,091 06 plus minus 0,05. Vogoshka. Apont BH21B3,01 plus minus 0,15 2,86 plus minus 0,14 0,95 plus minus 0,07. Apont BH23 4,08 plus minus 0,13 4,23 plus minus 0,13 1,04 plus minus 0,05. 1 equals the substrate sample is the soil, 2 equals the substrate sample is the roof of a building. 235U-BQ, kg. 235U/238U. 0,29 plus minus 0,06 0,039 plus minus 0,008 1,11 plus minus 0,063 0,031 plus minus 0,002. 0,14 plus minus 0,030, 0,36 plus minus 0,05 0,15 plus minus 0,02. 0,046 plus minus 0,009 0,050 plus minus 0,007 0,060 plus minus 0,009. 0,20 plus minus 0,04 0,067 plus minus 0,015 0,24 plus minus 0,03 0,060 plus minus 0,008. Depleted uranium in Bosnia and Herzegovina. 201. F. Table F.7 Concentration of 238U, 234U, 235U in lichen samples. Sample ID. Species. 238 UMG, kg. 234 UMG, kg. 234U/238U. Hedsisi, Tank Repair Facility. Applet Boat 2A. Applet Boat 2B. Applet Boat 2C. Applet Boat 3A. Applet Boat 5. Hypogeny episodes. Promelian Subinreferee. Promelian Sulcata Taylor. Promelian Sulcata Taylor. Promelian Sulcata Taylor. 1,52 EO1 plus minus 7,76 EO3. 2,13 EO1 plus minus 8,93 EO3. 1,85 EO1 plus minus 7,34 EO3. 1,75 EO1 plus minus 7,22 EO3. 2,92 EO1 plus minus 1,01 EO2. 7,70 EO6 plus minus 4,02 EO7. 1,11 EO5 plus minus 4,71 EO7. 8,77 EO6 plus minus 3,64 EO7. 7,22 EO6 plus minus 3,29 EO7. 1,06 EO5 plus minus 4,14 EO7. 5,06 EO5 plus minus 3,69 EO6. 5,21 EO5 plus minus 3,10 EO6. 4,74 EO5 plus minus 2,72 EO6. 4,12 EO5 plus minus 2,53 EO6. 3,62 EO5 plus minus 1,89 EO6. Lukavica. Applet Boat 9A. Applet 11. Promelian Sulcata Taylor. Fischer Adscendens. 1,94 EO1 plus minus 7,08 EO3. 2,37 EO1 plus minus 1,11 EO2. 10,00 EO6 plus minus 3,70 EO7. 1,20 EO5 plus minus 5,72 EO7. 5,15 EO5 plus minus 2,68 EO6. 5,06 EO5 plus minus 3,37 EO6. Hadzisi Barracks. Applet 13A. Applet 13B. Promelian Sulcata Taylor. Hypogeny episodes. 1,50 EO1 plus minus 6,59 EO3. 9,69 EO2 plus minus 5,58 EO3. 7,46 EO6 plus minus 3,37 EO7. 5,91 EO6 plus minus 3,22 EO7. 4,97 EO5 plus minus 3,13 EO6. 6,10 EO5 plus minus 4,84 EO6. Hadzisi, Ammunition Storage Area. Applet 14A. Applet 14B. Hypogeny episodes. Promelian Sulcata Taylor. 8,22 EO1 plus minus 2,72 EO2. 2,40 E plus 00 plus minus 8,70 EO2. 1,10 EO5 plus minus 6,32 EO7. 2,49 EO5 plus minus 1,69 EO6. 1,34 EO5 plus minus 8,87 EO7. 1,04 EO5 plus minus 7,98 EO7. Pijsk, T55 Dank. Applet 15. Applet 16A. Applet 16B. Hypogeny episodes. Promelian Sulcata Taylor. Hypogeny episodes. 9,65 EO2 plus minus 4,63 EO3. 1,59 EO1 plus minus 8,15 EO3. 9,75 EO2 plus minus 6,11 EO3. 5,46 CO6 plus minus 2,56 CO7. 8,32 EO6 plus minus 4,30 EO7. 5,66 CO6 plus minus 3,43 EO7. 5,66 CO5 plus minus 3,80 EO6. 5,23 EO5 plus minus 3,80 EO6. 5,80 EO5 plus minus 5,06 EO6. Hanpijsk, Barracks. APOP 17A. APOP 17B. APOP 17C. APOP 18. Promelia sulcata Taylor. Evernia prunastery. Hypogymnia episodes. Platismata glauca. 2,19 EO1 plus minus 6,81 EO3. 1,11 EO1 plus minus 8,25 EO3. 1,24 EO1 plus minus 6,12 EO3. 9,90 EO2 plus minus 3,92 EO3. 8,54 EO6 plus minus 2,97 EO7. 5,44 EO6 plus minus 4,22 EO7. 4,81 EO6 plus minus 2,72 EO7. 4,54 EO6 plus minus 1,91 EO7. 3,91 EO5 plus minus 1,82 EO6. 4,91 EO5 plus minus 5,29 EO6. 3,88 EO5 plus minus 2,92 EO6. 4,58 EO5 plus minus 2,65 EO6. Hanpijsk, Ammunition Storage Area. APOP 19. APOP 20A. APOP 20B. Hypogymnia episodes. Hypogymnia episodes. Promelia succintus. 1,05 EO1 plus minus 4,63 EO3. 1,10 EO1 plus minus 5,11 EO3. 1,90 EO1 plus minus 7,63 EO3. 3,22 EO6 plus minus 1,79 EO7. 4,07 EO6 plus minus 2,21 EO7. 5,57 EO6 plus minus 2,82 EO7. 3,06 EO5 plus minus 2,17 EO6. 3,71 EO5 plus minus 2,65 EO6. 2,93 EO5 plus minus 1,89 EO6. Vogoshka. APOP 24A. APOP 24B. Hypogymnia tubulosa. Hypogymnia episodes. 8,63 EO2 plus minus 5,75 EO3. 7,48 EO2 plus minus 4,60 EO3. 4,59 EO6 plus minus 3,07 EO7. 4,06 EO6 plus minus 2,48 EO7. 5,32 EO5 plus minus 5,02 EO6. 5,42 EO5 plus minus 4,70 EO6. Ustikalina Barracks. APOP 25. Xantoria parietina. 2,08 CO1 plus minus 7,26 CO3. 1,07 EO5 plus minus 3,79 EO7. 5,16 EO5 plus minus 2,56 CO6. Foka Bridge. APOP 26A. Fischer Adsendens. 7,99 EO1 plus minus 1,85 EO2. 4,23 EO5 plus minus 9,83 EO7. 5,30 EO5 plus minus 1,74 EO6. Kalinovic, Ammunition Destruction. APOP 27A1. Scamarina CFR. Stella. Petripoelt. 1,28 E plus 00 plus minus 4,92 EO2. 6,64 EO5 plus minus 2,56 EO6. 5,17 Neo5 plus minus 2,81 Neo6. Bielasnoka Plateau. Apit 28A. Romalina Fraksinka. 8,95 VO2 plus minus 4,12 VO3. Apit 28B. Promelia sulcata Taylor. 2,73 EO1 plus minus 8,14 EO3. Apod. Promelia. BH28C sulcata succedalis. 3,91 EO1 plus minus 1,36 CO2. 1 equals the substrate sample is the rock. 4,83 EO6 plus minus 2,22 EO7. 1,48 EO5 plus minus 4,40 EO7. 2,01 EO5 plus minus 7,05 EO7. 5,40 EO5 plus minus 3,52 EO6. 5,41 EO5 plus minus 2,28 EO6. 5,13 EO5 plus minus 2,54 EO6. 235 UMG, kg. 9,83 EO4 plus minus 2,88 EO4. 2,44 EO3 plus minus 4,29 EO4. 1,56 EO3 plus minus 2,84 EO4. 1,03 EO3 plus minus 2,43 EO4. 1,87 EO3 plus minus 2,91 EO4. 1,93 EO3 plus minus 2,86 EO4. 1,97 EO3 plus minus 4,11 EO4. 1,30 EO3 plus minus 2,70 EO4. 9,26 EO4 plus minus 2,73 EO4. 3,26 EO3 plus minus 7,46 EO4. 8,81 EO3 plus minus 2,07 EO3. 8,20 EO4 plus minus 2,09 EO4. 1,49 EO3 plus minus 3,69 EO4. 6,24 EO4 plus minus 2,54 EO4. 1,17 EO3 plus minus 2,03 EO4. 5,97 EO4 plus minus 3,92 EO4. 8,92 EO4 plus minus 2,51 EO4. 8,18 EO4 plus minus 1,64 EO4. 9,39 EO4 plus minus 2,01 EO4. 8,74 EO4 plus minus 2,12 EO4. 6,11 EO4 plus minus 1,96 EO4. 7,51 EO4 plus minus 2,98 EO4. 2,35 EO4 plus minus 1,71 EO4. 1,88 EO3 plus minus 2,74 EO4. 5,90 EO3 plus minus 4,77 EO4. 9,84 EO3 plus minus 1,18 EO3. 6,62 EO4 plus minus 1,74 EO4. 2,44 EO3 plus minus 2,91 EO4. 3,07 EO3 plus minus 4,05 EO4. 235U/238U. 6,46 EO3 plus minus 1,92 EO3. 1,14 EO2 plus minus 2,07 EO3. 8,45 EO3 plus minus 1,57 EO3. 5,89 EO3 plus minus 1,41 EO3. 6,40 EO3 plus minus 1,02 EO3. 9,97 EO3 plus minus 1,52 EO3. 8,30 EO3 plus minus 1,77 EO3. 8,62 EO3 plus minus 1,84 EO3. 9,56 CO3 plus minus 2,87 EO3. 3,97 EO3 plus minus 9,17 EO4. 3,67 EO3 plus minus 8,72 EO4. 8,49 EO3 plus minus 2,20 EO3. 9,38 EO3 plus minus 2,37 EO3. 6,40 EO3 plus minus 2,64 EO3. 5,36 EO3 plus minus 9,44 EO4. 5,40 EO3 plus minus 3,57 EO3. 7,20 EO3 plus minus 2,06 EO3. 8,26 EO3 plus minus 1,69 EO3. 8,92 EO3 plus minus 1,95 EO3. 7,98 EO3 plus minus 1,97 EO3. 3,21 EO3 plus minus 1,04 EO3. 8,71 EO3 plus minus 3,51 EO3. 3,14 EO3 plus minus 2,30 EO3. 9,02 EO3 plus minus 1,35 EO3. 7,38 EO3 plus minus 6,21 EO4. 7,66 EO3 plus minus 9,64 EO4. 7,40 EO3 plus minus 1,97 EO3. 8,95 EO3 plus minus 1,10 EO3. 7,85 EO3 plus minus 1,07 EO3. 202. Post-conflict environmental assessment. Table F.8 concentration of 238U, 234U, 235U in mushroom sample. Sample ID at pot B H21A. 238 UMG, kg. 2,16 EO2 plus minus 1,72 EO3. 234 UMG, kg. 234U/238U. Vogoshka. 1,13 EO6 plus minus 9,12 EO8. 5,23 EO5 plus minus 5,93 EO6. 235 UMG, kg. 3,05 EO4 plus minus 1,25 EO4. 235U/238U. 1,41 EO2 plus minus 5,89 EO3. F. Bioindicators. Table F.9 concentration of 238U, 234U, 235U in vegetable samples. Sample ID. VOBS1 VOBS2. 238 UMG, kg. 8,96 CO2 plus minus 3,19 EO3. 4,35 EO2 plus minus 2,32 EO3. 234 UMG, kg. 234U/238U. Hadsisi, tank repair facility. 3,10 EO6 plus minus 1,31 EO7. 3,46 EO5 plus minus 1,91 EO6. 2,21 EO6 plus minus 1,21 EO7. 5,08 EO5 plus minus 3,88 EO6. 235 UMG, kg. 4,29 EO4 plus minus 1,01 EO4. 3,02 EO4 plus minus 1,04 EO4. 235U/238U. 4,79 EO3 plus minus 1,14 EO3. 6,94 EO3 plus minus 2,43 EO3. Table F.10. Concentration of 238U, 234U, 235U in tree bark and tree bark plus lichen samples. Sample ID. 238 UMG, kg. 234 UMG, kg. 234U/238U. Head tank repair facility. Apatbo 1A1. Apatbo 6A. Apatbo 6B2. Apatbo 73. 1,48 plus minus 6,26 CO3. 7,96 CO2 plus minus 3,40 EO3. 8,88 EO2 plus minus 4,30 EO3. 1,40 EO1 plus minus 5,96 CO3. 6,90 EO6 plus minus 3,09 EO7. 3,65 EO6 plus minus 1,66 EO7. 4,05 EO6 plus minus 2,10 EO7. 6,28 EO6 plus minus 2,87 EO7. 4,67 EO5 plus minus 2,88 EO6. 4,58 EO5 plus minus 2,86 EO6. 4,55 EO5 plus minus 3,23 EO6. 4,50 EO5 plus minus 2,81 EO6. Lukavica. Apot BHO8A. 6,81 EO2 plus minus 3,20 EO3. 2,92 EO6 plus minus 1,50 EO7. 4,28 EO5 plus minus 2,99 EO6. Head ammunition storage area. Apot BH14. 2,86 CO2 plus minus 1,75 EO3. 1,03 EO6 plus minus 7,52 EO8. 3,59 EO5 plus minus 3,42 EO6. Vogoshka. Apot BH22. 9,83 EO2 plus minus 4,30 EO3. 5,37 EO6 plus minus 2,33 EO7. 5,46 EO5 plus minus 3,37 EO6. 1 equals bark plus lichen sample, the species identified is Phasphia orbicularis. 2 equals bark plus lichen sample, the species identified is Arthroporhenia species. 3 equals bark plus lichen sample, the species identified is Arthroporhenia species. 235 UMG, kg. 1,22 EO3 plus minus 2,56 EO4. 5,61 EO4 plus minus 1,32 EO4. 5,98 EO4 plus minus 1,81 EO4. 1,36 EO3 plus minus 2,54 EO4. 7,02 EO4 plus minus 1,47 EO4. 1,96 EO4 plus minus 8,65 EO5. 4,38 EO4 plus minus 1,34 EO4. 235 U/238 U. 8,25 EO3 plus minus 1,77 EO3. 7,05 EO3 plus minus 1,69 EO3. 6,74 EO3 plus minus 2,06 EO3. 9,72 EO3 plus minus 1,86 EO3. 1,03 EO2 plus minus 2,21 EO3. 6,86 EO3 plus minus 3,05 EO3. 4,46 EO3 plus minus 1,38 EO3. Table F.11 Concentration of 238U, 234U, 235U in mass samples. Sample ID. 238 UMG, kg. 234 UMG, kg. 234U/238U. Head tank repair facility. Apot BH01B. Apotbo 41. 5,92 EO1 plus minus 2,54 EO2. 2,88 E plus 00 plus minus 5,85 EO2. 2,50 EO5 plus minus 1,16 EO6. 7,29 EO5 plus minus 1,61 EO6. 4,23 EO5 plus minus 2,67 EO6. 2,53 EO5 plus minus 7,59 EO7. Lukovica. Apot BH09B. Apot 10-2. Apot BH12. 2,45 EO1 plus minus 9,48 EO3. 5,79 EO1 plus minus 2,04 EO2. 1,98 EO1 plus minus 7,22 EO3. 1,18 EO5 plus minus 4,70 EO7. 3,02 EO5 plus minus 1,07 EO6. 1,13 EO5 plus minus 4,03 EO7. 4,84 EO5 plus minus 2,70 EO6. 5,21 EO5 plus minus 2,60 EO6. 5,69 EO5 plus minus 2,91 EO6. Vogoshka. Apot BH21B. 2,43 EO1 plus minus 1,19 EO2. 1,24 EO5 plus minus 6,19 EO7. Apot BH23. 3,29 EO1 plus minus 1,06 EO2. 1,83 EO5 plus minus 5,84 EO7. 1 equals the substrate sample is the soil, 2 equals the substrate sample is the roof of a building. 5,10 EO5 plus minus 3,56 EO6. 5,56 EO5 plus minus 2,53 EO6. 235 UMG, kg. 3,59 EO3 plus minus 7,49 EO4. 1,39 EO2 plus minus 7,91 EO4. 1,74 EO3 plus minus 3,20 EO4. 4,49 EO3 plus minus 6,01 EO4. 1,84 EO3 plus minus 2,81 EO4. 2,51 EO3 plus minus 5,36 EO4. 3,05 EO3 plus minus 3,84 EO4. 235 U/238 U. 6,05 EO3 plus minus 1,29 EO3. 4,81 EO3 plus minus 2,91 EO4. 7,11 EO3 plus minus 1,34 EO3. 7,76 EO3 plus minus 1,07 EO3. 9,30 EO3 plus minus 1,46 EO3. 1,03 EO2 plus minus 2,26 EO3. 9,29 EO3 plus minus 1,21 EO3. Depleted uranium in Bosnia and Herzegovina. 203. G. Appendix G. Do in air. G.1 General aspects. Normal concentrations and radiation doses. Uranium series radionuclides are permanently present in air as a result of resuspension of soil particles, exhalation of radon-222 into the air, and its subsequent decay products to so-called radon daughters. A dust loading of 50 micrograms M3 is generally assumed. With a 238 U concentration in soil of 10 to 50 becquerels kg1, the corresponding and estimated concentration of this nuclide in air is expected to be 0.5 to 2.5 microbecquerels M3. Observed values of uranium concentration in air vary widely. Concentrations of uranium in sea air may be an order of magnitude lower than in continental or industrial areas. Reported values of 238 U concentration are 0.925 microbecquerels M3 in the United States and 0.02 to 18 microbecquerels M3 in Europe, UNSEER, 2000. The given reference value is 1 microgram M3 of 238U, which corresponds to 810 to 5 micrograms 238U per M3 air or 0.08 nanograms M3. Most natural levels of uranium are in the range of 0.1 to 10 micrograms M3, 100 ml. 10 to 5 micrograms M3 or 0.01 to 1 nanogram M3. Concentrations of 235U in air are much lower, that is 0.04 micrograms M3 in the United States, UNSEER, 2000. For this radionuclide, the given reference value is 0.05 micrograms M3. As 234U quickly enters into radioactive equilibrium with 238U, the UNSEER 2000 report recommends using 1 microgram M3 as a reference value for 234U concentration in air. The effective dose caused by inhalation of uranium and its radioactive daughter products as they are present in air is estimated to be 4.7, 5.6 and 5.4 microsieverts per year for infants, children and adults. Accordingly, age-weighted effective dose is 5.4 microsieverts per year. The major part is from 210 petabits plus 210 Po, 98%. From 238U alone it is 0.02 microsieverts per year, from 234U 0.03 microsieverts per year. If all U-238 daughters except radon and its daughter product are included, the dose is 0.3 microsieverts per year. The dose from 235U and its daughter products can be neglected. The concentration ratios 234U/238U and 235U/238U. The two uranium isotopes 234U and 238U are in the same decay chain, that is the 238U series C Appendix O. And if not disturbed by any selective chemical or physical effect they should be in radioactive equilibrium. In case of equilibrium, natural uranium contains 99.2745% of 238U by weight and 0.0054% of 234U, which in terms of activity corresponds to about 12.4 becquerels each per mg of natural uranium. However, it has been observed that by chemical effects, different leaching rate, and physical effects, alpha recoil, as reported in the WHO study Depleted Uranium, Sources, Exposures and Health Effects, WHO, 2001, the ratio can vary by a factor of 1.7 in favor of 234U, that is there is an excess of 234U in the dust in air. However, the real variation of the 234U and 238U ratio in air at a given place or region reflects the variation of the ratio in soil at that location, as is discussed below. In the case of depleted uranium, the concentration of 234U decreases somewhat more than 235U. If the concentration of 235U decreases from 0.72% to 0.20% by weight, that is a factor of 3.6, the concentration of 234U decreases from 0.0054% to 0.0010%, that is a factor of 5.4. If 2 is mixed with natural uranium in varying proportions, the mass ratio as well as the activity ratio will vary accordingly. Assuming that in a sample containing some 2 the mass proportion of 2 is X and the part of natural uranium is 1X. The mass ratio M for 234U/238U is given from the formula. 204. Post-conflict environmental assessment. M equals 1x, middle. 0.0054 plus x middle. 0.001. 1x, middle. 99.2745 plus x middle. 99.8, G.1. The activity ratio R is given by R equals M middle. 2.31 middle. 105/12.4. G.2. For x equals 0 the R value is 1, for x equals 0.5 the R value is 0.6 and for x equals 1 the R value is 0.19, etc. Corresponding formulas also apply for 235U/238U ratio. In that case, If the mass proportion of DU is X and the part of natural uranium is 1X, the mass ratio M for 235U/238U is given from the formula G M equals 1X, middle dot 0.72 plus X middle dot 0.2, 1X, middle dot 99.2745 plus X middle dot 99.8, G dot 3. DU in air. The activity ratio R is given by R equals M middle dot 80/12.4. G dot 4. For X equals 0 the R value is 0.047, for X equals 0.5 the R value is 0.03 and for X equals 1 the R value is 0.013, etc. The percentage of DU in the air samples with measured mass concentration of 234U and 238U. 234 Care and C238 Air in PG M3 can be estimated as DU percent equals 100 middle dot 0.000054 to 234 C, 238 C, 0.000044. G.5. 4. Measured mass concentration of 235U and 238U in air. 235 Care and C238 Air in PG M3. This formula becomes DU percent equals 100 middle dot 0.00725 to 235 C, 238 C, 0.00525. G.6. Depleted uranium in air. By taking measurements and subsequent chemical analyses on dust that has been sampled with air filters, it is possible to estimate the concentration of total uranium in air, as well as the concentration of 238U, 235U and 234U. By using the previous formulas, it is also possible to estimate the quantity of DU in the sample. How much DU could possibly be expected in air in normal and extreme conditions if there is DU dust contamination of the ground? What is the relation to the beta, gamma measurement directly on the ground surface? However, from a health point of view, it is the concentration of uranium as such that is of interest. Relation 1. The normal situation. Assuming that there is some correlation between the concentration of uranium in air pollution, dust, and that of the soil, the following applies. A concentration of uranium in air of 8-10 to 5 mg M3 and a normal dust concentration of 50 mg M3 result in 1.6 mg uranium, kg dust, which corresponds with the concentration in soil of 1 to 4 mg 238 U per kg of soil. Relation 2. DU contaminated ground surface. Assuming 10 kg of DU dust is distributed over the reference area of 1000 square meters, that is the reference case in this report, the corresponding area contamination would be 10 grams M2. The detection limit with comma instruments used would be 0.01 times the reference value, that is 0.1 grams M2. If some absorption occurs and the activity is distributed in the upper 1 mm of soil, the detection limit would be 10 times higher, that is 1 gram M2. Depleted uranium in Bosnia and Herzegovina. 205. G. Resuspension is normally divided into two types, natural, wind-driven, and anthropogenic, vehicular movement, agricultural activities, etc. Wind-driven resuspension assumes that the only disturbance to the surface is a result of natural weathering, while anthropogenic or mechanical resuspension includes mechanical disturbances by pedestrians or vehicles and agricultural operations. 10 grams M2 in 1 mm depth corresponds to 8 grams DU per kg soil. Assuming that the first m of soil is the part that chiefly contributes to dust in the air, the concentration in normal dusty air would be 400 nanograms DU per M3 of air, 50 micrograms M3 middle. 8 nanograms per microgram soil, dust, corresponding to 5 millibecquerels M3 in air, or roughly 5,000 times higher than normal. This distribution model can be considered as representative for a short time period, days, weeks, following the contaminating event. This air concentration would result in an annual effective dose of less than 1 millisievert, about 0.5 millisieverts, caused by continuous inhalation of that air for a full year, and is therefore insignificant. The Wilkins et al., 1994, report for this type of estimation recommends using the dust concentration of 100 micrograms M3 as a reasonably cautious dust loading, but does not change the assessments stated above. For the worst case, assuming desert conditions with vehicular movement and intensive agricultural activities, the dust concentration can reach 30,000 micrograms M3 based on measurements from Maralinga and EMU nuclear test sites in Australia, Haywood and Smith, 1990, which quoted values from 370 to 65,000 micrograms M3 for sitting in or near a moving vehicle. A mid-range value can be used for estimates assumed, as the no persons will spend their entire working day close to the vehicles. In that case, the dew concentration in air can be 0.24 mg M3, 30,000 micrograms M3 middle. 8 nanograms per microgram soil, dust. This value is roughly equal to the recommended limit by the U.S. National Institute for Occupational Safety and Health, NIOSH, for insoluble uranium of 0.2 mg M3 for chronic occupational exposure, and is approximately 3 times lower than a limit 0.6 mg M3 for short-term exposure. When NIOSH occupational guidelines are converted for exposure of the general public, they are 0.05 mg M3 for chronic exposure and 0.15 mg M3 for short-term exposure. For soluble uranium, the levels are 0.5 mg M3 and 10 mg M3, respectively, NIOSH, 1994. Considering that people would be in similar conditions no more than one working day, 8 hours, the total intake of resuspended due to a male heavy worker outdoors would be at the level of 2.1 mg. This intake corresponds to a committed effective dose at a level 0.26 millisieverts, see Appendix O, that is approximately 2.5 times higher than the total effective dose 110 microsieverts per year caused by all uranium daughters in the body from ingestion and inhalation, except inhaled radon daughters. In the worst case, assuming desert conditions and normal living conditions, dust concentration can be at a level of 2,000 micrograms M3. This value is based on measurements from the Maralinga and EMU nuclear test sites in Australia, Haywood and Smith, 1990, for children playing. In that case, the dew concentration in air could be 16 micrograms M3, 2,000 micrograms M3 middle. 8 nanograms per microgram soil, dust, or 2 times higher than stated by the U.S. Agency for Toxic Substances and Disease Registry, ACSDR, as a minimal risk level, MRL, for chronic inhalation exposure of 8 micrograms M3, ACSDR, 1999. The intake of dew can be estimated by using the formula, UK, 2002. Intake dew equals, care middle. In middle. 1 accrete, plus, care middle. In middle. Accrete middle. I/O, G.7. Where care is the integrated air concentration due to wind-driven or anthropogenic resuspension. 206. Post-conflict environmental assessment. N is the inhalation rate, as recommended by the International Commission on Radiological Protection, ICRP, 1994, see Table G.1. For the best estimate, the outdoor worker rate is used. For the worst case, the heavy worker rate is used. Accrete is the indoor occupancy, assumed to be 50%, that is the outdoor worker value from Habit Surveys, Robinson, 1996. For a 1-year-old infant, 10-year-old child and adult housewife accrete is assumed to be 0.9, UK, 2002. I, O is the indoor-outdoor concentration ratio. It is known that small particles can penetrate effectively into buildings, and the degree of equilibrium between indoor and outdoor air is dependent on particle size. For this report, a value of 0.5 is chosen on the basis of a dose conversion factor suggested in Brown, 1989. G. DO in air. Table G.1 Generalized inhalation rates, 24-hour averages. Group infant, 1-year-old, child, 10 years old, adult housewife heavy worker outdoor worker. Inhalation rate, M3S1, 6.02 E-5 1.76 E-4 2.04 E-4 3.10 E-4 2.92 E-4. A worst case calculation for total DO intake in the first year following initial deposit is shown in Table G.2. While undertaking these calculations, it was assumed that the DO had been dispersed in the upper 1 cm soil layer. Concentration of DO in topsoil box equals 0.71 grams kg1, which corresponds to an initial concentration of 0.8 grams kg1 in a layer of 0 to 1 cm with allowance for the averaged value of vertical migration coefficient for the first year equal to 0.89. Dust loading, 2000 micrograms M3. Table G.2 Intakes of DO for all age groups calculated using the worst case of dust loading approach. Exposed age group infant child adult, female, adult, male outdoor worker. DO intake, mg 1.54.45.09.8. The maximum value of DO intake in the first year after contamination is equal to 10 mg for adult, male outdoor worker, which corresponds to a committed effective dose at a level of 1.2 mSv. This value, a shade higher than the dose limit for members of the public, 1 mSv/year, refers to exposure to artificial sources, EU, 1996. For a housewife remaining 90% of the time indoors, the corresponding dose is about 0.6 mSv. On the other hand, the aforementioned situation is very conservative and hardly realistic. Depleted uranium in Bosnia and Herzegovina. 207. G. Relation 3. DO contaminated ground and distributed to a depth of 10 cm. Evidently, DO dust may have been distributed to a deeper layer than 10 mm. If it was distributed to a depth of 100 mm, the concentration of DO in soil would be 10 times less. Assuming the same amount of DO, 10 kg over 1,000 square meters, and the same pattern of suspension of dust from ground, the resulting DO concentration in air would be 10 times less and the actual detection limit would be 10 times the assumed ground contamination, 10 grams M2. In this case, all values introduced in relation to assessments should be reduced by a factor of 10, and problems related to DO intake by dust with suspension, both for professional workers and for the population, will not arise. This distribution model can be considered as more probable and representative following a long time period, 7 years, since the contaminating event. Conclusions. 1. Normal uranium concentration in air is 1 microgram M3, 8-10 to 5 micrograms M3, 0.08 nanograms M3 respectively, plus-minus factor of 10 upwards and downwards. 2. Resulting effective doses by inhalation are 0.02 to 0.03 microsieverts per year from 238U and 234U respectively. 3. The ratio 234U/238U in air can normally vary as a result of natural causes, depending on the corresponding ratio in the soil at the location investigated. 4. From measurements, it is possible to estimate the proportion of possible DO in a sample by assessing the activity ratio 234U/238U if it is lower than 1. However, many uncertainties exist and a non-indicative value of 234U/238U does not necessarily imply that no DO is present in the air. 5. The ratio 235U/238U cannot be influenced by any physical or chemical process in nature, it is thus expected to be constant and independent of the origin of the sample. Any statistically significant difference from the natural ratio must be attributed to the existence of artificially processed uranium. 6. If field measurements show no indication of DU contamination on the ground surface, there can still be an easily detectable concentration of DU in air if the DU on the ground is superficial. However, this could only be detected by using extremely sensitive and sophisticated analytical methods. On the other hand, if there is no detectable air contamination, there can still be a ground contamination above the reference level, 10 grams per m2. This would occur if the nearby ground does not contribute significantly to the dust and air at the area under investigation. 7. From the radiation dose viewpoint, it is concluded that in normal conditions the DU intake and effective doses from airborne uranium are very small, even if the concentration is several hundred times higher than normal. Heavy metal risks are also insignificant in these cases. 8. For the worst, and unrealistic, case assuming desert conditions with vehicular movement, etc., the DU concentration in air can approach the limits for chronic occupational exposure and exceed the limit for short-term exposure of the general public. 9. In the same worst case assuming desert conditions and normal living conditions, DU concentration can be higher than a minimal risk level, MRL, for chronic inhalation exposure of uranium as a toxic metal. 208. Post-conflict environmental assessment. G.2. Air measurement results. Sampling sites. Air samples were collected at a number of sites in B during the mission, Table G.3. Table G.3 Air filter samples collection sites in Bosnia and Herzegovina. G. DU in air. Code. Sampling site. Coordinates UTM34T. Sampled volume, N3. New code 2023201. Hadsisi, 1. BP 74 353, 56 272. 100.6. New code 2023202. Hadsisi, 1. BP 74 185, 56 407. 100.1. New code 2023203. Hadsisi, 1. BP 74096, 56 339. 96.8. New code 2023204. Hadsisi, 1. BP 74098, 56 338. 98.3. New code 2024201. Hadsisi, 1. BP 74041, 56 365. 131.6. New code 2024202. Hadsisi, 1. BP 74024, 56 372. 131.9. New code 2024203. Hadsisi, 1, inside a former workshop. BP 74030, 56 340. 61.0. New code 2024204. Hadsisi, 1, inside a former workshop. BP 73920, 56 398. 126.5. New code 2024205. Hadsisi, 1. BP 73915, 56 543. 67.5. New code 2025201. Lukovica, Barracks. BP 88332, 55 825. 113.0. New code 2025202. Lukovica, Barracks. BP 88623, 55 691. 103.1. New code 2025203. Lukovica, Barracks. BP 88536, 55 932. 85.3. NUCO 2025204. Lukovica, Barracks. BP 88 473, 55 844. 85.3. NUCO 2026201. Hadsisi, 2. BP 75 265, 54 739. 79.7. NUCO 2026202. Hadsisi, 2. BP 75 430, 54 668. 63.7. NUCO 2027201. Hanpijsk, Barracks. CP 36070, 84 360. 138.4. NUCO 2027202. Hanpijsk, Barracks. CP 35890, 84 308. 136.4. NUCO 2027203. Hanpijsk, Barracks. CP 35679, 84 362. 133.9. NUCO 2027204. Hanpijsk, Barracks. CP 35542, 84 386. 131.9. NUCO 2028201. Hanpijsk, Barracks. CP 35546, 84 432. 75.6. NUCO 2028202. Hanpijsk, Barracks, Inside Storage Barn. CP 35546, 84 429. 67.7. NUCO 2029201. Vogoska, 3. BP 88 893, 64 964. 99.9. NUCO 2029202. Vogoska, 3. BP 89 132, 65 128. 98.3. NUCO 2030201. Foka Bridge, Srbinj. CP 2545, 2476. 96.1. 1. Tank Repair Facility 2, Barracks 1 km from Ammunition Storage Area 3, Ammunition Production Site. To note: on the first day at the former Hadsisi Tank Repair Facility, 2 air filter samplers were placed in selected positions 150 meters, sample NUCO 2023202, and 300 meters, 023201, respectively away from the areas known to have been attacked with DU ammunition, see map in Chapter 7.1. This was done in order to try to sample the average uranium concentration at a certain distance from the areas that had been hit directly by DU bullets. A further 2 air filter samplers were placed at the cobblestone square yard at the center of the site. This yard and the adjacent workshops had been intensely hit by DU ammunition. 1 air filter sampler, 023203, was placed 1.6 meters above the ground surface, whereas the sampler, 023204, was placed at 0.9 meters, in order to study the effect of DU at different heights. On the second day at the former Hadsisi Tank Repair Facility, 2 air filters samplers, samples NUCO 2024201 and NUCO 2024202, were placed in the middle of the intensely attacked cobblestone square yard. A further 2 samplers, NUCO 2024203 and Depleted Uranium in Bosnia and Herzegovina. 209. G. NUCO 2024204, were placed inside 2 different buildings near the yard. DU contamination was found inside one of these buildings, NUCO 2024204. Finally, 1 air filter sample, NUCO 2024205, was collected at the location of the former tank parking lot in the westernmost part of the site. The tanks parked there had been strongly attacked by A-10 planes. 160 DU contamination points were found on this parking lot. On the first of 2 days at the Hanpajsk Artillery Storage and Barracks, 4 air filter samplers were arranged roughly 150 meters apart in a parallel line to the main road leading from the entrance of the campus to the forest. See map in Chapter 7.7. On the second day at the Hanpajsk Artillery Storage and Barracks, an air filter sampler continues to run while the UNEP 1 sampler, sample NUCO 2 team takes a lunch break. 028201, was placed on the west side of the entrance to one of the intensely attacked storage barns, and another sampler, NUCO 2028202, was placed inside the building. Both these samples showed traces of DU. Air samples were also collected at Lukovica, Vogoska, Foka Bridge, Srbinj, and the Hadzisi Army Barracks. Analyzes. The 234U/238U and 235U/238U mass concentration ratios depend on the extent of the enrichment process, which caused depletion in the lighter uranium isotopes and can be used to distinguish natural from anthropogenic uranium. By measurements of dust collected by air filters and by analyzing the uranium concentrations in the filters, the total uranium concentration in air, as well the isotopic concentrations of 234U, 235U and 238U, can be determined. The analyses of the uranium isotopes in the samples collected were made at SPI's laboratory by ICPMAS, see Appendix C. Methodology and Quality Control. The minimum detection limits for the 235U and for 238U, using ICPMAS, is well below the concentrations of these nuclides in the air. The 235U/238U mass ratio is constantly equal to 0.007, and there is no physicochemical phenomenon occurring in nature that can cause any variation in this value. Consequently, any statistically significant difference from the naturally expected ratio must be attributed to technologically treated uranium. The conclusion on the existence of DU contamination in the air or not was based on the 235U/238U activity ratio that varies from 0.0452, 0% DU, to 0.0129, 100% DU. 210. Post-conflict environmental assessment. Results and discussions. Results from the air filter analyses made on the samples from the UNEP mission are presented in tables G.4, G.7. The total uranium concentrations measured in the air varies from 9.7 to 3600 pg/m3. DU was detected in air samples collected at 2 sites, Hadzisi Tank Repair Facility, and the Hanpajsk Artillery Storage and Barracks. Uranium was also detected on air filters collected at other sites where filter samples were taken during the mission, however, no DU was found in these samples. At the Hadzisi Tank Repair Facility during the first day, 4 air samplers, samples NUCO 0023201, 023202, 023203, and 023204, were placed in randomly selected positions. Only one of these air samplers in the Hadzisi cobblestone yard samples had an indication of DU contamination, 023201. This sample was collected at the eastern corner of the facility. The percentage of DU over the total uranium is estimated to be 9%, but the statistical uncertainty of this measurement is rather high, 41% and K equals 1. We cannot therefore conclude with any certainty the existence of DU. 5 samples were taken during the second day, NUCO 2024201 to 024205, which all detected the presence of DU. Samples 024201 and 024202 were collected from samplers placed on the densely attacked cobblestone square yard in the center of the site. Many penetrators, fragments and hot spots were detected in this area. However, special care was taken during the measurements to avoid any resuspension due to human activities, digging, walking, etc. The highest DU percentage was detected in this area. Sample 024023 was collected within a large workshop building bordering the aforementioned cobblestone square. No DU contamination was detected by field measurements. Sample O24204 was collected inside the neighboring workshop west of the square. 3 contamination points were found in the building using field measurements. Samplers were placed in a parallel line at Hanpajsk. Sample O24205 was collected on the tank parking lot in the northwest part of the facility where tanks had been parked at the time of attack. A large number of contamination points, 160, were detected in this area. DU in air. G. Depleted uranium in Bosnia and Herzegovina. 211. G. At the Hanpajsk artillery storage and barracks, the maximum 238U concentration, 3.6 nanograms/m3, was detected in an air sample collected inside one of the attacked storage barns, sample NuCO 2028202. Of the total uranium concentrations, 99.6% of it is attributed to DU. The 238U concentration in the air just outside the barrack, sample NuCO 2028201, was 54.9 pg/m3 and 90.4% of this is attributed to DU. For an air sample collected the day before, NuCO 2027204, and 46 meters away from this point, the concentration of 238U in air was approximately 2.5 times lower, 22.1 pg/m3. The content of DU in this sample was 43%. The differences between the measurements inside and outside the barrack can be explained by a disparity in density of soil and floor contamination inside the structure, as well as discrepan size in the resuspension factors are outside of and inside the building. One of the causes for the distinctions in the resuspension factors could be the different speed of ground wind inside and outside and between different sampling days. See Appendix I. On the second day, special care was taken not to disrupt the area while the sampling was in progress, and to ensure natural results. The samplers were shut down when anyone approached the area. The air samples which were collected at distances. No DU was detected in air at Lukovica. Over 200 meters from the affected area showed no presence of DU. Cumulative probability distribution of uranium concentration in air samples collected in B is shown in figure G.1. This figure shows that the major number of measurements, 17 of 24, can be found in the range of concentrations from 10 to 60 pg/m3. This range of data with high scale of reliability, R2 is equal 0.96, is subject to the log normal law with a median value of figure G.1 cumulative distribution of 238U concentrations in air samples. 212. Post-conflict environmental assessment. 238U concentration in air equal to 35 pg/m3 and the standard deviation S, 0.7. Some of the results fall out of this distribution. These are the samples with heightened DU concentrations, green circuits, and all 4 samples from Lukovica, Site 7.2. Lukovica, however, showed rather high contents of natural uranium, red squares. The doses due to the existence of DU in the air at the measured levels are negligible, as demonstrated by the following facts. G. The total uranium concentrations in places where DU contamination in the open air were detected were in the range of values expected due to natural sources. The specific activity of depleted uranium is less than the specific activity of naturally occurring uranium. DU in air. The committed effective dose due to the existence of DU in air is calculated on the worst-case scenario assuming that a person works continuously for 1 year, 8 hours for 250 days, in the place where the maximum concentration of DU was detected, 1 nanogram/m3, Hadzisi tank repair facility, is in the order of 0.3 microsieverts per year. One also has to consider that the air samples were collected under dry, warm weather conditions and moderate wind speed. At higher wind speeds, dew concentrations in air may be higher. In damp, rainy weather, dew particles are washed out from the air and deposited onto the ground. However, dew concentrations in air at the sites investigated will never be high enough that any resulting doses will be significant. Conclusions. Dew was detected in air samples collected from two sites, Hatsisi Tank Repair Facility, and the Inhan Pajsk Artillery Storage and Barracks. The total uranium concentrations in places where dew contamination in the open air were detected are comparable with the values expected due to natural origin. The radiological significance of the contamination is negligible, 3 orders of magnitude less than that expected due to other naturally occurring sources. There is no widespread dew contamination in the air. No dew contamination was detected in samples collected over 100 meters away from heavily attacked areas. Dose estimations must be based on the air concentration measurement and not on models alone, which lead to great uncertainties because of the numerous unknown parameters involved in such estimations. The clarification and verification of the mechanisms causing the existence of dew in air seems to be an interesting scientific problem and should be subject for further research. It may be interesting for researchers to try to further clarify the mechanisms that explain the air contamination as related to the ground contamination. However, it does not influence the conclusions on possible future risks because there is no possible natural way that there will be any increased risk from air contamination. The results presented in this report are 3 orders of magnitude below those doses which would justify an immediate clarification. Table G.4 shows the measured isotopic composition of the dissolved filters, filter blank plus aerosol. The RSD values, 1 sigma, are the relative standard deviations of the ICP-MIS measurements. Table G.5 shows the isotope concentrations of the aerosols, which result after subtraction of the filter blank. The U-238 concentration of the dissolved filter blank plus aerosol, was measured quantitatively, and the U-235, U-234 and U-236 concentrations were calculated by using the isotopic compositions from Table G.4. The uranium isotope concentrations of the filter blank were similarly analyzed. The average U-238 concentration of the filter blank was 2.68 nanograms/filter, K equals 4.6%. The average U-235 and U-234 concentrations of the filter blank were calculated by using the natural composition of 0.71% for U-235. There was no significant difference between depleted uranium in Bosnia and Herzegovina. 213. G. The natural and the measured isotopic composition, and the measured composition of 0.011% for U-234, the measured isotopic composition deviated significantly from the natural composition. The K values, 1 sigma, are the combined procedure errors. The isotope concentrations per M3 air were calculated with the values from Table G.5 and the sampled volume from Table G.3. The procedure error for the sampled volume was estimated to be 6%, including uncertainties of calibration, variable atmospheric pressure and measurements at different altitudes. The K values, 1 sigma, are the combined procedure errors. The percentage of dew was calculated from the measured 235U/238U isotope ratio, filter blank plus aerosol, and corrected by the ratio of the U-238 concentration in the aerosol to the concentration in the dissolved filter blank plus aerosol. The K values, 1 sigma, are the combined procedure errors. High detection limits for dew, percent, were obtained in some samples due to the low U concentrations and the small differences between the U concentrations of the samples in the filter blank. Table G.4 uranium isotopic compositions of the dissolved filter blank plus aerosol. Code Nu Code 2. 023 201 023 202 023 203 023 204 024 201 024 202 024 203 024 204 024 205 025 201 025 202 025 203 025 204 026 201 026 202 027 201 027 202 027 203 027 204 028 201 028 202 029 201 029 202 030 201 238 U. Percentage, mass percent, 99.305 99.291 99.282 99.273 99.688 99.762 99.328 99.423 99.381 99.279 99.277 99.267 99.268 99.284 99.287 99.29 to 99.287 99.290 99.388 99.560 99.789 99.31 to 99.289 99.265 RSD, percent. 0.47 0.97 1.10 0.25 0.42 0.38 0.55 0.66 1.30 0.08 0.27 0.24 1.06 1.14 1.59 0.25 0.38 1.37 1.75 0.83 0.92 1.13 0.90 0.59 235 U. Percentage, mass percent, 0.688 0.698 0.707 0.717 0.307 0.234 0.662 0.569 0.611 0.715 0.716 0.726 0.725 0.707 0.704 0.701 0.705 0.701 0.602 0.434 0.207 0.680 0.701 0.725 RSD, percent. 1.78 0.86 1.52 2.32 0.83 0.47 1.64 0.90 1.23 0.35 1.32 1.51 1.22 0.99 2.85 1.07 2.84 1.00 1.47 2.02 1.38 2.16 2.20 1.89 234 U. Percentage, mass percent, 0.00710 0.0105 0.0109 0.0099 0.002 0.001 0.0095 0.0078 0.0072 0.0059 0.0067 0.0066 0.0069 0.0088 0.0087 0.0068 0.0068 0.0083 0.0087 0.0053 0.0009 0.0077 0.0104 0.0100 RSD, percent. 11.15.192.53 10.6 13.39.60 20.81.99 17.15.115.2 8.63 12.29.01 11.32.77 12.24.44 14.6 10.27.75 20.3 19.54.09 236 U. Percentage, mass percent, 0.002 0.002 0.002 0.002 0.0022 0.0026 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.002 0.0027 0.002 0.002 0.002 RSD percent 6.364.083.61 Table G.5 Isotope concentrations of the aerosols. Code Nu Code 2. 023201 023202 023203 023204 024201 024202 024203 024204 024205 025201 025202 025203 238U. Eng/filter, 4.80.1.04138.22.004.133.114.08 K, percent, 4.8.9 14.1 13.21.5 7.5 4.15.2 1.91.73.2 235U. Eng/filter, 0.033 0.012 0.007 0.008 0.136 0.311 0.012 0.020 0.017 0.102 0.171 0.078 K. Percent. 5.3 10.0 16.2 15.2 2.5 2.0 10.0 6.2 7.9 2.3 2.5 3.9 234U. PG/filter 0.24 0.17 0.10 0.08 0.84 1.56 0.15 0.24 0.12 0.71 1.48 0.59 K. Percent. 33.5 31.3 40.2 69.2 22.5 16.5 66.9 22.9 66.5 15.9 13.5 19.9 236U. PG/filter 0.2 0.2 0.2 0.2 1.1 03.67 0.2 0.2 0.2 0.3 0.5 0.3 K. Percent. Dash 11.9 10.9 214 Post-conflict environmental assessment. 025 204 026 201 026 202 027 201 027 202 027 203 027 204 028 201 028 202 029 201 029 202 030 201 9.27 1.62 1.605 0.093 2.17 2.924.15 243.4 1.37 1.023.73 2.58.99.14.05.67.25.24.01.4 11.4 0.068 0.012 0.011 0.036 0.025 0.015 0.015 0.011 0.492 0.009 0.007 0.028 3.4 10.1 12.9 4.6 7.7 8.5 8.8 11.3 2.5 15.1 17.1 5.6 0.53 0.09 0.08 0.24 0.13 0.11 0.19 0.07 1.81 0.10 0.09 0.35 24.4 59.6 69.4 23.6 52.4 40.1 44.5 76.4 14.8 89.7 19.9 Table G.6 Isotope concentrations of uranium in the air 0.2 0.2 0.2 0.2 0.2 0.2 0.2 0.26.70 0.2 0.2 0.2 10.7 dash G Do in air Code Nu Code 2 023 201 023 202 023 203 023 204 024 201 024 202 024 203 024 204 024 205 025 201 025 202 025 203 025 204 026 201 026 202 027 201 027 202 027 203 027 204 028 201 028 202 029 201 029 202 030 201 238 U PG/M3 47.7 17.09.68 10.536 1104 832.8 32.6 46.1 125 229 125 109 20.3 25.1 36.8 25.3 16.2 22.1 54.9 3596 13.7 10.4 38.8 K percent 7.2 10.7 15.3 14.5 6.2 6.29.6 7.3 7.9 6.3 6.2 6.8 6.5 10.8 10.9 7.2 8.2 9.4 7.9 7.2 12.8 15.2 7.4 235 U PG/M3 0.33 0.12 0.07 0.08 1.03 2.36 0.20 0.16 0.24 0.90 1.66 0.92 0.80 0.14 0.18 0.26 0.18 0.11 0.11 0.14 7.26 0.09 0.07 0.29 K Percent. 8.0 11.7 17.2 16.3 6.56.3 11.7 8.6 9.96.4 6.57.1 6.9 11.7 14.37.5 9.8 10.4 10.7 12.8 6.5 16.2 18.2 8.2 234U FG/M3 2.371.691.060.806.38 11.82.531.911.846.25 14.36.956.26 1.08 1.29 1.70 0.940 1.47 0.90 26.81 0.963 3.68 K, percent, 34.0 31.9 40.7 69.4 23.2 17.6 67.2 23.6 66.8 17.0 14.8 20.8 25.2 59.9 69.7 24.4 52.7 40.5 44.9 76.7 16.0 89.9 20.8 236U FG/M3 2222 8.33 27.8 222 1.09 99.0222 K, percent, dash 13.4 12.4 25.0 12.3 dash Table G.7 Isotopic ratio 235U/238U of the dissolved filters, filter blank plus aerosol, and calculated percentage of DO in the aerosol. Code new code 2. 023201 023202 023203 023204 024201 024202 024203 024204 024205 025201 025202 025203 025204 026201 026202 027201 027 202 027 203 027 204 028 201 028 202 029 201 029 202 030 201 Isotope ratio 235U, 238U Filter plus aerosol 0.00694 0.00704 0.00713 0.00724 0.00309 0.00235 0.00668 0.00573 0.00616 0.00721 0.00723 0.00733 0.00731 0.00713 0.00710 0.00708 0.00712 0.00708 0.00607 0.00437 0.00208 0.006 686 0.00707 0.00731 K, percent 1.87 0.47 1.942 0.44 1.00 0.22 1.39 0.31 1.28 0.29 1.23 1.52 0.98 0.28 1.71 1.142 2.82 1.06 0.48 1.34 0.75 2.5, 2.74, 2.54, 2.28. Do of U total, percent, aerosol. 9.3, 17, 27, 25, 83.8, 95.2, 25.6, 47.7, 38.8, 3, 2, 3, 4, 17, 17, 7, 11, 15, 43.0, 90.4, 99.6, 22, 27, 10. K, percent. 41.6 dash. 0.74, 0.10, 16.21, 0.177.21. 2.46, 2.03, 0.30 dash. Depleted uranium in Bosnia and Herzegovina. 215. H. Appendix H. Analysis of DU penetrators, fragments and jackets. During the UNEP mission to Bosnia and Herzegovina, B. 3 unbroken penetrators and 1 full bullet, penetrator still sticking in its jacket, were collected for further studies and analyses of the specific composition of the DU, as well as of the uranium oxide layer covering the surfaces. A number of penetrators and fragments were found during field investigations but not collected for analysis. Those found on the surface were collected and handed over to the competent local governmental organization, Federal Administration for Radiation Protection and Radioactive Security, for safe storage. Similar studies were carried out on penetrators and fragments collected during the previous Kosovo and Serbia and Montenegro missions, UNEP, 2001, 2002. H.1 Studies on DU penetrator material collected during earlier missions. Studies on the soil samples collected during the 2000 UNEP mission to Kosovo revealed that some of the soil samples contained traces of 236U, a non-natural uranium isotope formed when uranium is used as nuclear reactor fuel, UNEP, 2001. This indicated that some of the depleted uranium came from reprocessed uranium. This finding was confirmed by smear test analyses of prepared from found penetrators and jackets and, at a later stage, by analyses carried out on material from 4 of the penetrators and fragments collected. The presence of 236U in the penetrators triggered further studies of transuranic elements in the penetrators. These additional studies shows that the penetrators also contained trace amounts of plutonium. The plutonium concentration was very low, near the detection limit, and could be considered as DU impurity. In 2000, the Bristol University Laboratory also analyzed some of the penetrators for other elements formed in nuclear reactors, such as 99Tc, 237Np, 241M, 243M and 244Cm. However, the concentrations of these elements were all below their respective detection limits. The analysis and studies on penetrators collected during the mission to Serbia and Montenegro showed very similar results for the isotopic composition of uranium and the presence of plutonium. Neptunium, 237Np, measurements were below the detection limit. Due to the longer time spent in the soil, these penetrators showed much heavier signs of corrosion than those from Kosovo. H.2 Studies of the penetrators collected in Bosnia. Similar studies were also conducted on penetrators collected during the UNEP mission to Bosnia. These analyses and studies were performed at SP's laboratory in Switzerland. Isotopic analyses. Using ICP mass spectrometry, analyses were performed of the isotopic composition of DU in the penetrators. Analyses showed a rather constant isotopic composition for the uranium isotopes 238U, 235U, 234U and 236U, tables H.5 and H.6. All 3 samples analyzed contain 236U, which shows that the depleted uranium was contaminated by reprocessed uranium. The mean value for the 235U/238U isotopic ratio of the DU penetrators was 0.00198 plus minus 0.00001, and the 216. Post-conflict environmental assessment. 236U concentration was 0.0028 plus minus 0.0002%. These values are almost identical to those analyzed from the 2 previous UNEP missions. In addition, this matches the isotopic uranium composition for DUIN weapons published in U.S. military and non-confidential literature. The content of the transuranic elements plutonium-239-240 in DU was analyzed by radiochemical procedures, followed by alpha spectrometric measurements. To determine the contents of neptunium-237, radiochemical separation methods were also used, followed by analysis with high-resolution ICP mass spectrometry, HRICP-MAS. The radiochemical analysis shows that the concentration of plutonium in the penetrators is very low, tables H.7 and H.8. The range analyzed was from 0.0050 to 0.0878 BQ/G, which corresponds to 2.2 E-12 to 38.2 E-12 G/G. This is equivalent to the very low content of roughly 1 pu atom per 100 billion uranium atoms. Again, the results confirm the findings on penetrators from the two previous UNEP missions as well as information provided by the U.S. DOE open literature, DOE, 2000. The radiochemical analysis shows that the concentration of neptunium-237 in the DU penetrators is from less than 0.004 to 0.0162 BQ/G, which corresponds to less than 1.5 E-10 to 6.2 E-10 G/G. These results establish that the DU found in the Balkans region at some point during its fabrication process came in contact with reprocessed uranium. However, the concentration of the contaminating nuclides is so low, that their contribution to the total radiation dose of DU for all intake paths is insignificant and can be neglected. H. Penetrators. Studies of corrosion. Studies of the corrosion on the DU penetrators began by weighing and measuring them in the same state as when they were collected in the field, and again after removing the surface layer of soil and uranium oxide by both mechanical and mild chemical cleaning. After lying in the ground for over 7 years, the penetrators were heavily corroded and intensive pitting, corrosion attack producing small holes, of the DU surface had taken place. According to U.S. military literature, a penetrator's original weight is tilde 292 grams. Thus, the penetrators studied had lost 66 to 93 grams due to corrosion. Penetrator corrosion products were removed from the surface and analyzed in the laboratory. These findings differ from the results of penetrator studies from Kosovo, which were only slightly corroded after 1.5 years in the ground. These new findings show that the level of corrosion increases dramatically with time. Once corrosion starts, the exposed surface tends to increase and the pitting effect will thus accelerate. Penetrators laying on the ground surface were much less corroded than those buried below the ground surface. Bearing in mind the state of the penetrators when they were found, UNEP established the losses to be 2 to 5 grams in Kosovo after 1.5 years, 11 to 38 grams in Serbia and Montenegro after 2.5 years, and 66 to 93 grams in BiH over 7 years after the conflict, not corrected for loss of weight due to formation of DU dust during the depleted uranium in Bosnia and Herzegovina. 217. H. Impact. In conclusion, based on these findings, no more penetrators consisting of metallic DU will be found in the Balkans grounds after 25 to 35 years. Instead of metallic penetrators, contaminated spots in the ground will be found containing DU decomposition products. Transuranic elements. Both 236U and plutonium in the penetrators originate from the reprocessing of nuclear fuel. In order to be used in a nuclear reactor, the concentration of 235U. Once cleaned, signs of pitting from corrosion become much more visible. And uranium needs to be enriched from 0.7 to about 4%. Once the reactor fuel is spent, the removed fuel still contains a quantity of 235U. During the chemical reprocessing of spent reactor fuel, transuranic mints and fission products can be separated from the uranium. The 235U can again be concentrated up to 4% through enrichment of this reprocessed uranium, and the uranium is again used as recycled reactor fuel. However, during the reprocessing step, a small part of the transuranic elements and fission products will remain in the uranium fraction. If this reprocessed reactor uranium is enriched, both the enriched reactor fuel as well as the DU will contain small amounts of these transuranium nuclides. Some of the transuranics may even contaminate the technical equipment of the enrichment plant. No. 2000. Consequently, uranium that is later processed in the plant will be contaminated with tiny traces of transuranics, even if it is received directly from uranium mines. In January 2000, the U.S. Army reported that investigations on DU use as tank armor had shown that it did contain some transuranics. U.S. Army Material Command, 2000. The concentrations were very low. The average 239/240 proactivity concentration was 85 becquerels/kg and the highest found was 130 becquerels/kg. Since the uranium for both DU armor and ammunition likely originates from the same source, contaminations in the same range can be expected in both armor and ammunition. However, the plutonium activity concentration in the collected penetrators from Kosovo, Serbia and Montenegro and now from BiH was in the board range from less than 0.8 to a maximum of 87.8 becquerels/kg, with a mean value around 18 becquerels/kg. The analytical procedures chosen to determine the concentration of 237 Np in DU penetrators resulted in very low detection limits. For 237 Np, a maximum concentration of 16.2 becquerels/kg, or 6.2 E10 grams/g respectively could be measured in the penetrators analyzed from BiH. Table H.1 Sample Identification. Code NUCO 2024401 NUCO 2028401 NUCO 2028402 NUCO 2028403. Coordinates UTM 34T. BP 74050, 56362, Hatsisi Tank Repair Facility. CP 35468, 84445, Hanpajsk Barracks. CP 35795, 84340, Hanpajsk Barracks. CP 35716, 84384, Hanpajsk Barracks. Sample. Penetrator, sticking in cobblestone pavement. Penetrator in soil in depth of 7 cm. Penetrator with jacket in depth of 3 cm. Penetrator in soil in depth of 5 cm. 218. Post-conflict environmental assessment. Table H.2 Mass of the penetrators as collected. Code NUCO 2024401 NUCO 2028401 NUCO 2028402 NUCO 2028403. Sample penetrator. Weight, G, 213.99 246.46 414.15 242.91. H. Table H.3 Penetrator mass after mechanical surface cleaning, scraping. Code NUCO 2024401 NUCO 2028401 NUCO 2028402 NUCO 2028403. Sample. Penetrator. Weight after mechanical cleaning, G, 207.35 224.85 412.65 235.39. Loss of weight, G. 6.64 21.611 507.52. Penetrators. Table H.4 Penetrator mass and dimension after weak chemical cleaning. Code. Sample. Weight after chemical cleaning, G. Loss of weight, G. Diameter smallest, largest. Length. NUCO 2024401 Penetrator. 198.80, 8.55, 14.5 to 15.2, 78. NuCO 2028 401 penetrator, 212.73, 12.12, 12.2 to 15.8, 83. NuCO 2028 402 penetrator, 409.80, 2.85. NuCO 2028 403 penetrator, 225.66, 9.73, 13.6 to 15.9, 74. Table H.5 Isotopic compositions of uranium: 238U, 235U, 234U, 236U. Nuke 2002 percentage RSD percentage RSD percentage RSD percentage RSD, mass percent, percent, mass percent, percent, mass percent, percent, mass percent, percent. 024 401 0199.7980.54, 0.199, 0.610 0.0007119.6, 0.0029, 9.0. 028 401 0199.799 0.21 0.197 0.28 0.0006 0.00275.0, 028 403 0199.799 1.06 0.198 1.05 0.000597.9 0.00287.9. Table H.6 Isotopic ratio 235U, 238U. Nuke 2002. 024 401 0102 401 0102 403 Isotope ratio 235U, 238U. 0.00199 0.00197 0.00198 K, percent. 0.6 0.7 0.8 Do of total U, percent. 100.2 100.5 100.4 K, percent. 0.2 0.2 0.3 Table H.7 Plutonium N, BQ/G. Code. NuCO 2024 401 NuCO 2028 401 NuCO 2028 403. Sample. Penetrator Pu239/Pu240, BQ/G. 0.0878. 0.0175 0.00503. RSD, percent. 51411. Depleted uranium in Bosnia and Herzegovina. 219. H. Table H.8 Plutonium N, G/G, calculated as Pu239. Code NuCO 2024 401. Sample penetrator. Pu239, G/G. 38.2 E-12. RSD, percent. 5. NuCO 2028 401. Penetrator. 7.6 E-12. 14. NuCO 2028 403. Penetrator. 2.2 E-12. 11. Table H.9 Neptunium N, BQ/G. Code. Sample. NP237, BQ/G. RSD, percent. NuCO 2024 401. Penetrator. 0.0162. 15. NuCO 2028 401. Penetrator. 0.0040. 62. New code 2028403. Penetrator 0.004. Table H.10 Neptunium N, G/G. Code. Sample. NP 237, G/G. RSD, %. New code 2024401. Penetrator 6.20 E-10. 15. New code 2028401. Penetrator 1.52 E-10. 62. New code 2028403. Penetrator 1.5 E-10. 220. Post-conflict environmental assessment. Appendix I. Influence of resuspension and deposition processes on the DU and I. Surface contamination. Resuspension, deposition. I.1 General information. In a zero-dimensional model, that is there is no dependence on spatial coordinates, the temporal evolution of airborne, mass or activity, concentration is given in the solution of the mass balance equation. dCT/dt equals T, TCT. I.1. Where, T, and T, are the instantaneous values of resuspension and deposition rates, S1, respectively. At times, an additional term is added on the right-hand side of this equation describing long-term memory resuspension processes, Williams, 1992. Equation, I.1, describes the fraction of contaminant removed from or added to the surface per unit time. Shortly following the contamination event, the time term can be ignored and, in this case, assuming of resuspension and deposition rates are independent from time, formula, I.1, can be written as dCT/dt equals, CT. I.2. For subsequent calculations it is convenient to use the interrelation between resuspension flux density J, Gm2S1, and resuspension rate as J equals I.3. Where is the surface contamination density, Gm2? Equation, I.3, gives a principal opportunity to estimate the value of the resuspension flux density J by using the measurements results for resuspension rate and the surface contamination density. The method for estimating the resuspension flux density J is called eddy correlation technique. This technique consists of counting all particles crossing a reference area, from both below and above, during a certain time period and determining the net flux density in this manner. It is important that this method not depend on the validity of the gradient transfer approach, ICP 1, 1996. It should also be noted that this methodology is extremely difficult and has no wide application. A simpler and the more frequently used approach is the concept of resuspension factor. The resuspension factor R is defined by the ratio of airborne contamination concentration C, in Gm3, at some height above a surface of the ground and surface contamination density, in Gm2, that is, R equals C/I.4. Depleted uranium in Bosnia and Herzegovina. 221. I. Using the formulas, I.3, and I.4, it is possible to represent the expression for resuspension rate as equals JR, C. I.5. The deposition flux density J can thus be estimated by using information about the deposition velocity and airborne contamination concentration C. J equals C. I.6. On the other hand, the deposition flux density J is connected with deposition rate by the ratio similar to the formula, I.3. J equals I.7. Using the given formula, and also formulas, I.6, and I.4, we obtain equals R. I.8. After substituting the values for calculation the resuspension and deposition rates using the aforementioned formulas, equation, I.2, becomes dCT/dt equals JR, RCT. I.9. Which has the solution CT equals C0x-RT plus J/1x-RT. I.N. It follows from this equation, that at the constant product R with increased time t, the concentration of contaminants in air will approach equilibrium conditions equal to the ratio of resuspension flux density J to deposition velocity, that is at t. C equals J/I.11. Practical use of equation, I.10, is very difficult. However, by using experimental data on resuspension flux density J and deposition velocity to estimate air contamination, formula, I.11, is sufficient. Therefore, the most applicable way for a similar calculation is to use formula, I.4, in which the resuspension factor R appears dependent on the period of time after initial soil contamination, as well as from soil surface activity, ground wind speed, particle size and other parameters. CT equals TRT. I.12. Some variable estimates included in formula, I.12, as well as the analysis of certain parameters influencing these variables, are described below. Soil surface activity. It is appropriate to assume that only soil particles close to the surface can be resuspended. This makes the specific soil activity soil one of the most important parameters. Various models are used for forecasting vertical migration of radionuclides into the ground, depending on the time after initial contamination. One such model is the generic undisturbed soil model, Brown, 1995. This compartmental soil model is based on the migration in soil for a limited number of elements, particularly poo, Cs and senior the rate of movement of these elements. 222. Post-conflict environmental assessment. Resuspension, deposition into the soil is slow, although there is significant variation between the results of the various observations owing to differences in soil composition and annual rainfall. The soil model consists of 4 compartments or boxes, the 0 to 1 cm box, 1 to 5 cm box, 5 to 15 cm box and 15 to 30 cm box. There are rate constants to express transfer between and losses from boxes. Resuspension is assumed to occur only from the top 1 cm of soil, that is the upper box in the generic soil model, UK, 2002. The mass of dew at time 0 can be calculated in the top box by using the assumptions accepted in the report, UK, 2002. By using the reference case from the UNEP Dew Dusk Assessment Report, UNEP/UNCHS, 1999, for the initial soil contamination it is assumed that 10 grams dew M2 is uniformly distributed in the 0 to 1 cm box, the volume of the top box, with dimensions 1 meter by 1 meter by 0.01 meters, equals 0.01 cubic meters. 10 grams of dew are deposited on the box, therefore density of dew in the top box equals 1 kilogram M3. Assumed density of soil, generic dry soil, equals 1.25 grams cm3 equals 1.25 by 10 to 3 kilograms M3. Concentration of dew in the top box is equal to 0.8 grams kg1, that is G of dew in 1 kg of soil. Using the Brown model, the concentrations of dew in the top soil box are presented on figure I.1. For comparative purposes, results of similar calculations based on the generalization of experimental data on soil contamination as a result of Chernobyl accident are also shown of the figure, ICP1. It is shown in the report, ICP1, 1996, that the surface activity concentration follows almost exactly a T0.5 dependence, without radioactive decay. It can be seen from this figure that for a period of approximately 7 years, time since 2 attacks, the topsoil contamination can be approximately 15 to 30% of the original levels of pollution. Figure I.1 Soil surface activity as a function of time after initial contamination, calculated by Brown and ICP1 models. I. Depleted uranium in Bosnia and Herzegovina. 223. I. Size particles and deposition velocity. The deposition velocity for a particle with a diameter of more than 10 micrometers depends on its weight, the Archimedean buoyant force and aerodynamic resistance restricting the movement of a particle. Falling aerosol particles quickly reach such constant speed, sedimentation velocity, at which aerodynamic resistance of air becomes equal to the effective weight of a particle, that is to its weight minus the Archimedean buoyant force. 3 microair g equals 6d3, air. Where microair d air, neglecting air. Viscosity of air, Pa s, diameter of particle, m, sedimentation velocity, ms1, specific weight of particle, in m3, specific weight of air, in m3. As contrasted to we shall receive st equals d2, 18 microair, equals d2g, 18 microair. I.13, I.14. Where density of air, kgm3, g, acceleration of gravity, ms2. Equation, I.14, is applicable only for small and constant speeds of particles and their small dimensions when the Reynolds number is in the range of 0 to 1, Stokes formula. For major Reynolds numbers it is necessary to enter allowances into equation, I.14, for example the Klyachko equation, Idalchik, 1975. Figure I.2 dependence of deposition velocity from particle size. 224. Post-conflict environmental assessment. Resuspension, deposition. Thus, for large particles, the deposition velocity is dominated by particle sedimentation, whereas for very small particles, the deposition velocity is dominated by Brownian diffusion. For atmospheric particles in the report, ICP 1, 1996, it is recommended to use a minimum deposition velocity of 0.001 meters s1. In that case, the reliance of deposition velocity on particle sizes can look like relationships presented in Fig.I.2. On a generalization basis of experimental data in the ICP 1 report, ICP 1, 1996, it follows that a typical airborne cumulative mass size distribution during natural resuspension has the mass median aerodynamic diameter of 4.3 micrometers, the geometric standard deviation g of 4.0 and the total mass concentration of 57 micrograms m3. Analyzing data of air contamination as a result of the Chernobyl accident, the report, ICP 1, 1996, asserts that the given total mass concentration correlates favorably with the value of resuspension flux density J at the level of 3.710 to 7 grams m2s1. This corresponds to an average deposition velocity value of 0.0065 meters s1 and to a particle size of about 14 micrometers. Wind observations show that wind speed statistics follow eyeball distributions. Total effects of nonlinear phenomena based on skew probability distributions like the one shown will be largely determined by a few strong events. In view of the very nonlinear dependence of resuspension on wind speed, a few strong wind events could dominate resuspension. It is therefore of critical importance to have wind speed statistics for estimating the probability of such events. ICP 1, 1996. Importantly, as natural resuspension is closely related to wind erosion, this link provides access to much literature and data on the processes of wind soil erosion. One of the relationships connecting resuspension flux density J with wind speed at the soil surface U is the Gillette relation, Gillette, 1977. J equals U5 asterisk. I.15. Where the empirical constant is equals 310 to 6 kilograms S4 M7. This reliance is depicted in Fig.I.3. Figure I.3 reliance of resuspension flux density J on wind speed at the soil surface U. I. Depleted uranium in Bosnia and Herzegovina. 225. I. As this figure indicates, resuspension by wind shear is a highly nonlinear event, therefore considerable fractions of the annual resuspension yield can be produced within short time periods by gusts and dust storms, ICP 1, 1996. Data on observable values of deposition flux density J at the level of 9.2 to 16 micrograms M2S1 are submitted in the UNEP1 report. Similar values, ranging between 0.6 to 16 micrograms M2S1, are reported for Karacalpakia, Kuksa, 1994. Wind erosion rates around Lake Harel average 2 to 3 mm per year over the last 30 years are equivalent to 0.10 to 0.15 mg M2S1, UNEP1, 1996. It follows that high erosion rates immediately after a primary deposition could effectively resuspend all contamination that would still be at the very top of the soil at that time. In a situation where there is a due surface contamination density of 10 grams M2 and a contamination depth of 1 cm, specific soil activity at the surface 7 years after the initial contamination can be 0.16 grams due in 1 kg soil. Topsoil times reduction coefficient of 0.2 is used, see Fig.I.1. In the case for semi-arid and windy conditions, the resuspension flux density J of dew at the level of 0.003 to 0.024 micrograms M2S1 occurs. Applying formula, I.11, it is obtained that at a deposition velocity at a level of 0.0065 meters S1 the concentration of dew in air can be roughly 0.4 to 3.7 micrograms M3. The higher value is approximately 2 times lower than derived by the U.S. Agency for Toxic Substances and Disease Registries, ATSR, minimal risk level, MRL, for chronic inhalation exposure of 8 micrograms M3, ATSR, 1999. Resuspension factor for natural conditions. As previously discussed, the resuspension factor R is defined by the ratio of airborne contamination concentration C and surface contamination density. In practice, there are no homogeneously contaminated surfaces, and in that case the airborne concentration is a sum of the local resuspended contamination and contamination carried from upwind resuspension, minus that carried away by the wind, UK, 2002. A large uncertainty exists in the values of resuspension factor R in the short time after initial contamination. In this period of time, the resuspension factor can range from 10.9 to 10 to 5 meters minus 1, Lindsley, 1978. PNNO analyzed air concentrations of resuspended dew in the contaminated area of the North Compound after the 1991 Doha fire, Osagwi, 2000. PNNO estimated air concentrations for each of the periods of the recovery effort assuming resuspension factors. Thus, it was taken into account that the density of the dew oxides was 4.5 grams cm3, the average surface contamination was 0.383 grams m2, and a reasonable estimate for wind speed was considered to be 7 meters s1. It was revealed that before any cleanup activity the resuspension factor R by wind erosion was 110 to 4 meters minus 1, and it reduced to 110 to 5 meters minus 1 after completing the cleanup operations, Osagwi, 2000. In Hanover 12 to 22 days after primary deposition following the Chernobyl accident, resuspension rates in the range 210.6 to 210 to 5 meters minus 1 were found, depending on wind speed. Hollander, 1994. To assess the time dependence of the resuspension factor, Garland has suggested the following formula, Garland, 1979, 1982. RT equals 1.210 minus 6T minus 1. I.16. Where T is the time after initial deposition in days, another dependence resuspension factor for time, built by integrating data on Chernobyl accident, is presented, UNEP1, 1996. RT equals 2.0910 minus 4T minus 1.67. I.17. Both of these dependencies are shown on Fig.I.4. 226. Post-conflict environmental assessment. According to the UNEP1 report, UNEP1, 1996, the exponent value minus 1.67 in formula, I.17, is very reasonable considering the surface activity concentration decay proportional to T0.5, see Fig.I.1, which would have to be added to the exponent of -1.07 expected from theory, Reeks, 1988. Thus, using the technique from this report is preferable as it also takes into account the time history of the soil contamination density of the top layer. Figure I.4 Dependence of resuspension factor R from the time after initial soil contamination. I. Resuspension, deposition. From figure 1.4 it is evident that with increasing time the resuspension factor R is constantly reduced and for t equals 10,000 days becomes at a level of 1010 and even less. It does not fully correspond to the measurement data which were conducted on experimental sites through a considerable space of time, Unspaw, 1975, Lindsley, 1978, Muller, 1999. To eliminate this discrepancy, UK, 2002, a time dependence of the resuspension factor R is suggested in the formulas for estimating and increasing the additional long-term resuspension term of B equal to 10 to 9 meters minus 1. In that case the formula, I.17, can be rewritten as RT equals 2.0910 minus 4T minus 1.67 plus 110 minus 9. I.18. Allowance for this concept is added on Fig.I.4 in the curve titled IC1 plus 10.9. Substituting into equation, I.7, to estimate the deposition rate from equation, I.8, we obtain J equals R. I.19. By integrating the equation, I.19, with time, assuming constancy with time, surface contamination density and deposition velocity, the integral deposition flux density J was estimated as a function of time after initial soil contamination. Results from these calculations are depicted in Fig.I.5. Thus, it was calculated that the deposition velocity is 0.0065 meters s1, the initial due surface contamination density minus 0.8 grams kg1 and time dependence of resuspension factor R can be described by equations, I.17, or, I.18. Depleted uranium in Bosnia and Herzegovina. 227. I. Figure I.5 integrated due deposition flux density as a function of time after the initial soil contamination. Figure I.5 shows that, for reference case conditions, the integrated level of surface contamination, UNEP/UNCS, 1999, as a result of resuspension processes 7 years after contamination will not exceed 13 to 14 mg N2, that is only 1.6% from the level of initial soil contamination. It is also possible to remark that in the 1996 ICP-1 report, the dependence of the resuspension factor R from the soil humidity obtained during experimental work in areas contaminated after Chernobyl is presented as R equals R0x-RSH. I.20. Where R0, the resuspension factor R for dry soil, M1, the constant, which value in the report, ICP-1, 1996, is equals 0.6. Non-dimensional value. RSH, the relative soil humidity, percent. Assessments by using equation, I.20, show that a change of relative soil humidity from 9% to 1% results in the resuspension factor R increase of 120 times. Resuspension factor for anthropogenic activity. In addition to natural resuspension, the resuspension factor R as a result of anthropogenic activity essentially depends on a period of time following initial soil contamination. In the first days following contamination of military machinery by dew, the resuspension factor R appropriate to vigorous working on a contaminated surface is assumed to be 0.001 meters minus 1. Fish, 1967, Mitchell, 1967. 228. Post-conflict environmental assessment. The report, The Effect, 2001, affirms that for UK conditions as a result of moderate mechanical activity, regular disturbance of the surface by vehicles or pedestrians, a resuspension factor of 10 to 5 meters minus 1 may be more applicable. For a worst case, desert conditions and high mechanical activity, it is recommended to use the resuspension factor R at a level of 1.210 to 4 meters minus 1. This value was chosen on the basis of the measurements which were made on the Maralinga test site, 0.3 meters from a moving vehicle. The resuspension factors in these measurements were reported to range from 5.010 to 7 meters minus 1 to 1.0 by 10 to 3 meters minus 1. In a situation where a long time has elapsed since initial contamination, to assess the value of the resuspension factor R stipulated by anthropogenic activity, equations, I.16, I.18, introducing padding multipliers can be used. 10. For population in desert conditions, 100, for professionals, for example tractor drivers, in desert conditions and high mechanical activity. To note, these values are in reasonable accord with results of calculations using equation, I.20. Dust loading approach. Another method commonly used in environmental assessments is to consider dust loading, Wilkins, 1994, UK, 2002. This approach assumes that contaminant activity concentrations in airborne dust at a particular location is the same as that in the surface layer of soil. C equals soil say. I.21. Where C, the estimated concentration of the contaminant in air, GM3. Soil, the concentration of the contaminant in soil, GKG1, that is G of contaminant in 1 kilogram soil. SE, the equivalent soil concentration or dust loading in air, KGM3. Still, problems exist in using the dust loading approach. First, the soil concentration is expressed in terms of GKG1. However, as a rule, the results of measurements are generally reported as GM2 and knowledge of the depth of contamination is required. A short time after contamination, it is difficult to define what the real depth of the surface soil layer is and how this depth will change with time. The normal average value of dust load say is 50 micrograms M3. In real conditions this value can be, Wilkins, 1994. In the range of 5 to 50 micrograms M3 in non-urban areas, and, between 100 to 800 micrograms M3 in large industrial areas. The report, UK, 2001, states that for UK conditions, and soldiers carrying out a range of activities, say equals 50 micrograms M3 can be used as a reasonably cautious value for dust loading. For desert conditions and intensive vehicular movement, this report recommends to use dust load say equals 30 mg M3. This value is based on measurements from the Maralinga and Emu nuclear test sites in Australia, which quoted values of say from 0.37 to 65 mg M3 for sitting in or near a moving vehicle. Finally, the worst case assumes desert conditions and normal living conditions of a population and recommends to use dust load say equals 2 mg M3, based on measurements from Maralinga and Emu nuclear test sites for children playing. Comparison of calculated values of mid-annual dew concentrations in air is estimated using a technique of the resuspension factor R or dust loading approach as given in Fig.I.6. At its construction, initial soil contamination by dew at the level of 10 grams M2 was used according to a reference case. Depleted uranium in Bosnia and Herzegovina. 229. Resuspension, deposition. I. Figure I.6 comparison of mid-annual dew concentrations in air estimated using a technique of resuspension factor R or dust loading approach. This figure shows that in the first years following initial soil contamination, the technique based on the dust loading approach gives values of dew concentrations in air which are almost 10 times lower than estimated by using the resuspension factor R procedure. However, after a period of 5 years, the results of both techniques practically coincide. Conclusions. The most convenient way for the assessment of air contamination by the processes of a secondary dust formation is the use of resuspension factors which are dependent on the period of time after initial soil contamination. A decrease of contamination of the top layer of soil, 0 to 1 cm, in time can, in 7 years, be at a level of 15 to 30% from the initial contamination. Natural resuspension can be characterized by the particle sizes about 14 micrometers, particles deposition velocity of 0.0065 meters s1 and resuspension flux density at the level of 3.710 to 7 grams m2 s1. In the case of semi-arid and windy conditions, the resuspension flux density by dew can reach 0.003 to 0.024 micrograms m2s1 7 years after the initial soil contamination at a level of 10 grams dew per 1 square meter. Design values of the resuspension factor 7 year after the initial soil contamination can be in the range 0.5 to 1.4, 10 to 9 meters minus 1, depending on the applied estimation model. For reference case conditions, the integrated level of surface contamination as a result of resuspension processes 7 years after contamination will not exceed 13 to 14 milligrams m2, that is only 0.13 to 0.14% from the level of initial soil contamination. In the first years following initial soil contamination, the technique based on the dust loading approach gives values of dew concentrations in air which are almost 10 times lower than estimated by using the resuspension factor R procedure. However, after a period of 5 years, the results of both techniques practically coincide. 230. Post-conflict environmental assessment. I.2 Resuspension factors and analysis. Estimations of resuspension factors were completed using equation I.12, with air contamination data from Appendix G and soil contamination data from Appendix J of the 24 air samples collected, 21 outdoor samples and 3 samples inside buildings. Samples NUCO 2024-201, NUCO 2024-202 and NUCO 2028-202, were selected. As formation processes for secondary air pollution outside and inside buildings can be different, and considering the complexities in assessing floor contamination inside buildings, see below, it was decided to conduct separate estimations of the resuspension factors for these cases. Outdoors resuspension factors. By analyzing the coordinates of air and soil sampling locations, it is possible to observe that, as a rule, these points do not coincide. In this respect, it is necessary to choose which point of soil sample splitting is best compared to an air sampling point. To solve this problem, it was decided to average soil samples, including a weighting factor for each separate measurement, and consider the remoteness of the soil sampling point position from the air sampling position. The change was obtained from measured concentrations of uranium isotopes in a layer of 0 to 5 centimeters, except for samples NUCO 2024-011 and NUCO 2024-011, selected in a 0 to 3 centimeters layer, to their concentration in the layer of soil of 0 to 1 centimeter at the moment of initial fallout. It was assumed that the portion of activity of uranium isotopes in the soil sample stipulated by the presence of dew was completely transferred to a layer of 0 to 1 centimeter. For the presence of natural uranium in any recalculations, it was assumed that the concentration of uranium isotopes in a layer of 0 to 1 centimeter is proportional to their measured concentration in a layer 0.3 or 0 to 5 centimeters. Results of these calculations are presented in the tab. I.1. The cumulative distribution of estimated average values of outdoors resuspension factors are, the last column of the table I.1, are presented on Fig. I.7. The median of this distribution is 8.5 10 to 10 meters minus 1 with a confidence interval of this value in the range of 0.28 to 2.5, 10 to 9 meters minus 1. Of note. Table I.1 estimated values of outdoors resuspension factors, M1. Air sample code. Sampling site. Interval of distances, M. Resuspension factors estimated by U238, U235, U234. Average. NUCO 2023-201. Hadsisi, 1. 98 to 602. 3.44 E minus 10. 6.12 E minus 10. 7.53 E minus 10. 5.70 E minus 10. New code 2023202. Hadsisi, 1. 36 to 399. 9.56 E minus 11. 1.89 E minus 10. 4.75 E minus 10. 2.53 E minus 10. New code 2023203. Hadsisi, 1. 35 to 402. 3.90 E minus 11. 9.07 E minus 11. 2.64 E minus 10. 1.31 E minus 10. New code 2023204. Hadsisi, 1. 33 to 399. 4.36 E minus 11. 1.06 E minus 10. 2.02 E minus 10. 1.17 E minus 10. New code 2024201. Hadsisi, 1. 26 to 462. 8.28 E minus 10. 8.83 E minus 10. 1.17 E minus 9. 1.03 E minus 9. New code 2024202. Hadsisi, 1. 14 to 481. 2.45 E minus 9. 2.05 E minus 9. 2.18 E minus 9. 2.10 E minus 9. New code 2024205. Hadsisi, 1. 79 to 662. 2.45 E minus 10. 3.72 E minus 10. 5.25 E minus 10. 3.81 E minus 10. New code 2025201 Lukovica, Barracks 113 to 314 4.02 E minus 9. 4.00 E minus 9. 3.74 E minus 9. 3.92 E minus 9. New code 2025202 Lukovica, Barracks 21 to 415. 6.73 E minus 9. 6.73 E minus 9. 7.87 E minus 9. 7.11 E minus 9. New code 2025203 Lukovica, Barracks 50 to 341. 3.82 E minus 9. 3.89 E minus 9. 3.93 E minus 9. 3.88 E minus 9. New code 2025204 Lukovica, Barracks 67 to 255. 3.36 E minus 9. 3.41 E minus 9. 3.58 E minus 9. 3.45 E minus 9. New code 2026201. Hadsisi, 2. 60 to 1874.92 E minus 10. 4.93 E minus 10. 5.34 E minus 10. 5.06 E minus 10. New code 2026202. Hadsisi, 2. 45 to 17046.50 E minus 10. 6.76 E minus 10. 6.81 E minus 10. 6.69 E minus 10. New code 2027201 Han Pijsk, Barracks 111 to 608 1.23 E minus 9. 1.22 E minus 9. 1.09 E minus 9. 1.18 E minus 9. New code 2027202 Han Pijsk, Barracks 79 to 444. 8.60 E minus 10. 8.62 E minus 10. 6.11 E minus 10. 7.78 E minus 10. New code 2027203 Han Pijsk, barracks 12 to 399. 4.90 E-10. 4.82 E-10. 4.72 E-10. 4.81 E-10. New code 2027 204 Han-Pijsk, barracks 76 to 537. 7.16 E-10. 5.00 E-10. 8.84 E-10. 7.00 E-10. New code 2028 201 Han-Pijsk, barracks 79 to 547. 1.78 E-9. 6.35 E-10. 5.43 E-10. 9.85 E-10. New code 2029 201. Vogoska, 3. 37 to 3586.10 E-10. 5.49 E-10. 5.79 E-10. New code 2029 202. Vogoska, 3. 85 to 3301 4.37 E-10. 4.03 E-10. 7.42 E-10. 5.27 E-10. New code 2030 201 Foka Bridge, Srbinj, 16 to 203. 1.19 E-9. 1.22 E-9. 2.09 E-9. 1.50 E-9. 1. Tank Repair Facility 2, Barracks near Ammunition Storage Area 3, Ammunition Production Site. Depleted uranium in Bosnia and Herzegovina. 231. Resuspension, deposition. I. Figure I.7 Cumulative distribution of results of the estimated outdoor resuspension factor R. Is that this value is in the good agreement with results of assessment of resuspension factors R by using the equation, I.18. Resuspension factors inside the bomb storage barn, Han-Pijsk. The assessment of resuspension factors are inside the attacked storage barn, Han-Pijsk artillery storage and barracks site, was made using the following data. The density of dew contamination on the concrete floor inside the attacked storage barn was 0.7 grams m2, see Appendix J. The isotopic composition of uranium on the floor corresponds to the measurement results of the scratch sample, NUCO 2028302. The isotopic composition of uranium in the air inside this barn corresponds to the measurement results from the air filter sample, NUCO 2028202. The results of these estimates are presented in Table I.2. Table I.2 input data and the results of estimation of resuspension factors are inside the storage barn, M1. Parameter dew on concrete floor, GM2 dew in air inside the barrack, GM3 resuspension factor R, M1. 232. 234 U 4.718 6 2.618 14 5.61 E 9. 235 U 1.318 3 7.26 E 12 5.26 E 9. 236 U 2.04 E 5 9.90 E 14 4.86 E 9. 238 U 6.90 E 13.60 E 9 5.21 E 9. Post-conflict environmental assessment. An analysis of this table shows that the results using data for different uranium nuclides are very similar. The average value of resuspension factors R inside the attacked storage barn is 5.2 10 to 9 meters minus 1. That value is approximately 7 times higher than the average value for outdoor resuspension factors R, see Table I.1. Differences can perhaps be explained by the current design of this barn as there are major apertures near the floor and wind speed at the floor surface could be much higher than outdoors. Surface contamination as a result of resuspension and deposition processes. Military machinery has been stored in the barn for some time, but only once the building was repaired following the attack. Therefore, any contamination on the surface would be due to resuspension and deposition. 2 smear samples were collected from the surface of a cannon inside this barn, samples code NUCO 2028303 and NSISMRO 703, results, see Appendix J. A further smear sample, sample code NUCO 2028304, was taken from the wooden box surface. The input data and results of the estimation ratios of surface to floor due residues 7 years after initial contamination are presented in Table I.3. Table I.3 input data and the results of estimation the ratio of surface to floor due contamination inside the storage barn. Parameter 234U, 235U, 236U, 238U. Due on concrete floor, GM2. 4.718-6 1.318-32.04E-56.90E-1. Due on the smear samples, MgCM2. NSISMRO 703. 3.10E-10. 1.10E-5. NUCO 2028303. 4.00E-11 1.20E-8 1.66E-10 5.90E-6. NUCO 2028304. 1.73E-10 5.40E-8 7.23E-10 2.67E-5. Due on the analyzed surface 1, GM2. NSISMRO 703. 1.55E-8. 5.50E-4. NUCO 2028303. 2.00E-9 6.00E-7 8.30E-9 2.95E-4. NUCO 2028304. 8.65E-9 2.70E-6 3.62E-8 1.34E-3. The ratio of surface to floor due contamination, percent. NSISMRO 703. 0.324. 0.080. NUCO 2028303. 0.042. 0.043. 0.041. 0.043. NUCO 2028304. 0.181. 0.196. 0.178. 0.193. 1. Taking into account that the part of taken out activity by using the smear sampling method is near 20% from the surface contamination density. This table shows that the range of results of this contamination ratio is 0.04 to 0.32%. This value is in the good agreement with results of theoretical assessments that were presented in Figure I.5. Conclusions. 1. The introduced analysis model for the effects of resuspension and deposition processes on due air and surface contamination has shown a good correlation with supervising results from the different sites. 2. Estimated on analysis of experimental data, the value of outdoor resuspension factors are a 7.310 to 10 meters minus 1 with a confidence interval in the range 0.23 to 2.3, 10 to 9 meters minus 1. This value is in good agreement with assessment results for this factor by mathematical models. 3. The average value of resuspension factors R inside the storage barn is 5.210 to 9 meters minus 1. This value is approximately 7 times higher than the average value for outdoor resuspension factors R. 4. The ratio of contamination density of the surfaces, polluted due to the deposition process of resuspended particles, to floor due contamination density 7 years after initial contamination is in the range 0.04 to 0.32%. This range is in good agreement with results from theoretical assessments. Depleted uranium in Bosnia and Herzegovina. 233. Resuspension, deposition. I. J. Appendix J. Do in surface deposits and special studies on surfaces. J.1 Do in surface deposits. Background. When penetrators impact on the ground surface, a portion of its dew mass is transformed into aerosols or fine particles and thrown into the surrounding air. The quantity of dew dispersed into the air mainly depends on the hardness of the surface where the impact takes place. The quantity dispersed is greater on hard surface impacts than on softer surfaces. Consequently, aerial dispersion of small dew quantities is expected after impact on soft soil, soil without stones, higher quantities on hard ground surfaces, stony soil, rock, concrete, asphalt, and the highest quantities when the impact occurs on the heavy armor of a tank or APC. These aerosols and fine particles are normally deposited in measurable quantities on the surrounding ground or on other surfaces within about 100 meters from impact. After initial deposit, it is possible that fine dew dust particles are resuspended into the atmosphere together with soil dust by wind or human activities, leading to secondary air contamination. These particles are then deposited once more on the surrounding ground and other surfaces. If the deposition takes place on surfaces other than soil that are exposed to rain and other meteorological phenomena, the surface deposit will be partly washed off. Surface deposits on soil will penetrate into the topsoil layer with time. If the deposition of dew aerosols and fine particles takes place on surfaces which are not affected by rain and other meteorological phenomena, for example inside a building, surface deposits will accumulate and remain undisturbed over a longer time and can later be collected and analyzed by taking smear or scratch samples. Measurements of surface deposits. During the mission to Bosnia and Herzegovina, special samples were taken inside a wooden storage barn at the Honpijsk artillery storage and barracks site. Inside this building, shot holes on the concrete floor indicated that the building had been attacked and hit by dew rounds. After the attacks, the dew-contaminated building was repaired and used once again to store army material, such as cannons and instruments in wooden boxes. However, the detailed history of the building's management is not known. One scratch sample was taken from the edge of the concrete floor against the wall, a second one was collected from the horizontal surface of a wooden beam at a height of about 1 meter above the floor surface. 2 smear samples were taken from smooth, painted horizontal surfaces of army material that had been stored in the barn, one from a cannon, another from a wooden box. The description of the samples and the analyses of results are summarized in tables J.1 to J.7. The scratch sample from the rough concrete floor surface consisted of sand and dust. Dew content of uranium in scratch samples exceeded 99%. 234. Post-conflict environmental assessment. 23.8 grams of the material was collected from a surface of 420 square centimeters. The uranium concentration of the material was 1.89 mg per gram, representing a surface contamination of 107 micrograms U/cm2, or 1.07 grams/m2. This uranium concentration is approximately 1000 times higher than the natural uranium content of soil. The isotope composition shows that the uranium consists to almost 100% of dew. The scratch sample from the rough surface on a wooden beam consisted of sand and dust. 2.38 grams of the material was collected from a surface of 200 square centimeters. The uranium concentration of the material was 92 micrograms/g, representing a surface contamination of 1.1 micrograms U/cm2 or 11 milligrams/m2. This uranium concentration is approximately 100 times higher than the natural uranium content of soil. The isotope composition again shows that the uranium consists of almost 100% depleted uranium. These 2 scratch samples mainly represent the primary deposition of debris and dust from the impact of the dew penetrators on the concrete floor inside the building. It is unlikely that this coarse, sandy material was resuspended inside the building at a later time. The measuring results for these samples show that inside a building, the primary surface contamination from impacts of dew penetrators can, as expected, be higher than in the open field. As it is indoors, no influence of weathering effects can occur and the initial superficial contamination will remain preserved at the ground surface, if the floor is not cleaned. Both smear samples from smooth painted surfaces consisted of fine brown dust. The measured loose surface contamination from the cannon was 5.9 nanograms U/cm2, or 59 micrograms/m2. The measured loose surface contamination from the wooden box was 27 nanograms U/cm2, or 270 micrograms/m2. The isotope composition for both smear samples shows that the uranium consists of almost 100% depleted uranium. J. Special studies. Smear samples from the surface of stored supplies consisted primarily of resuspended particles, secondary deposition. These two smear samples represent the secondary deposition of resuspended contaminated dust, resulting from the impact of the dew penetrators on the concrete floor inside the building. Because the detailed history of the building management is unknown, it is indeed not possible to discern the length of time elapsed since the dust was deposited on the sampled surfaces. Measurement results from these samples show that, inside a building, the secondary deposition of resuspended dust from contaminated ground surfaces can lead to a dew contamination of objects' surfaces that were brought into the building only after the attack. Indeed, the dew concentration was found to be about 1,000 times less than the primary. Depleted uranium in Bosnia and Herzegovina. 235. J. Contamination on the ground surface. There is no influence from weathering effects, and the superficial contamination will accumulate and remain preserved on the surface of the objects for a long time. Table J.1 Special samples from Hunpijsk. Sample code coordinates UTM 3014 UCO 2028301 CP 35550, 84425 NUCO 2028302 CP 35550, 84425 NUCO 2028303 CP 35550, 84425 NUCO 2028004 CP 35550, 84425. Sample description. Scratch sample of dust, 8 by 25 cm, on beam inside storage barn. Scratch sample of dust, 6 by 70 cm, on concrete floor inside storage barn. Smear sample on horizontal area, 10 by 40 cm, of cannon inside storage barn. Smear sample, 24 by 40 cm, on wooden box inside storage barn. Table J.2 Scratch samples, isotope concentration of uranium per sample mass. Nuc 2000-2028. 301-302. 238 U. G/kg. K, %. 0.0917. 1.9. 1.89. 1.8. 235 U. mg/kg, K, %. 0.187. 3.6. 3.77. 11.0. 234 U. Micrograms/kg, K, %. 0.66. 23. 13.1. 35. 236 U. Micrograms/kg, K, %. 2.6. 17. 56. 15. Table J.3 Scratch samples, isotope concentration of uranium per surface unit. Nuc. 238 U. 2000-2028, micrograms/cm2, K, %. 301. 1.09. 1.9. 302. 107. 1.8. 235 U. Ang/cm2, K, %. 2.23. 3.6. 214. 11.0. 234 pg/cm2, K, %. 7.90. 23. 741. 35. 236 U. pg/cm2, K, %. 30.8. 17. 3158. 15. Table J.4 Scratch samples, percentage due of total uranium. Nuke 2002-028. 301 302. Isotopic ratio 235 U, 238 U. 0.00203. 0.00199. K, %. 1.52.0. Percentage due of total uranium, %. 99.4 100.2. K, %. 0.60.8. Table J.5 Smear samples, isotope concentration of uranium per sample. 238 U. Nuke 2002-028 micrograms/smear sample. K, %. 303. 2.37. 1.5. 304. 25.6. 1.5. 235 U. Ang/smear sample. K, %. 4.75. 2.9. 52.1. 8.8. 234 U. pg/smear sample. K, %. 15.9. 11. 166. 16. 236 U. pg/smear sample. K, %. 66.3. 12. 694. 12. Table J.6 Smear samples, isotope concentration of uranium per surface unit. Nuke 238 U. 2002-028 micrograms/cm2, K, %. 303. 0.0059. 1.5. 304. 0.0267. 1.5. 235 U. Ang/cm2, K, %. 0.012. 2.9. 0.054. 8.8. 234 U. pg/cm2, K, %. 0.040. 11. 0.173. 16. 236 U. pg/cm2, K, %. 0.166. 12. 0.723. 12. Table J.7 Smear samples, percentage due of total uranium. Nuke 2002-028. 303 304. Isotope ratio 235 U, 238 U. 0.00200. 0.00202. K, %. 0.75 0.99. Percentage due of total uranium, %. 100.099.6. K, %. 0.28 0.38. 236. Post-conflict environmental assessment. J.2 Special studies on surfaces. Inspector device measurements. Dust in the air and settling over surfaces, both inside and outside, mainly contains radioactive decay products from naturally occurring uranium and thorium in soil. In addition, the dust can include the radionuclides from nuclear weapons tests in the atmosphere, from nuclear accidents, for example, the Chernobyl accident in 1986, and from the airborne release of nuclear installations. Soil-derived radionuclides are present in air in variable amounts, depending on local soil, wind, and moisture conditions. Using assessments, a dust loading of 50 micrograms M3 was assumed and applied to typical concentrations of natural radionuclides in soil. Some portion of the solid matter in air may not come from the soil, but from organic matter, building dust, smoke, and fly ash from coal burning, UNSEER, 2000. Measurements of radioactive surface contamination using the inspector device were produced on 13 sites during the mission. 175 measurements were made in total. Some information about these measurements is reported in Table J.8. J. Special Studies. Table J.8 Surface contamination measurements produced. Number of samples with count rates, CPS, in the interval. Site 0.1, 0.10.20.20.30.30.30.50.30.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50.50. 110.50.51.0. 110. 10-100. Sarajevo. 2. Hadzisi 1. 16. 6. 6. 1. 1. 1. 1. Lukovica, Barracks. 11. 12. Hadzisi 2. 4. 4. 3. 1. Hadzisi, Barracks. 1. 1. Jeliyugovici 3. 4. 2. 1. Hanpijsk, Barracks. 14. 10. 4. 7. 5. 8. 1. Pelkaran, Barracks. 1. Vogoska 4. 5. 6. 3. 1. 1. Kalinovic 5. 1. 1. Kalinovic 6. 1. 2. 1. Foka, Srbinj, Bridge. 4. 7. 4. 1. Bielasno Caputo. 3. 3. Total. 61. 52. 27. 13. 8. 9. 2. 1. Tank Repair Facility 2, Barracks 1 km from Ammunition Storage Area 3, T-55 Tank Position 4, Ammunition Production Site 5, Ammunition Destruction Site 6, Water Reservoir. Greater than 100 to 1. 3. Total. 234 23 12 2 750. 116 24 16. 6 175. The cumulative distribution of these results on the total activity is shown in Figure J.1. This figure illustrates that the main part of the results stay in the range of 0.041.0 CPS. The results with count rates less than 0.04 CPS are not significant values. On the other hand, the results with count rates over 1.0 CPS fall into cases of measurements of a surface contamination or inside the bombed barracks, or near fragments of dew penetrators outdoors. Following the elimination of these extreme values, the remaining results were segregated into two groups. In one were included the results from sites where dew penetrator fragments were found, Hadzisi Tank Repair Facility, Hadzisi Ammunition Storage Area and Hanpijsk Artillery Storage and Barracks. The second group included those sites in which the presence of dew was not revealed. The cumulative distribution of measuring results of beta surface contamination for these two groups is shown on Figure J.2. Depleted uranium in Bosnia and Herzegovina. 237. J. Figure J.1 Cumulative distribution of measurement results of beta surface contamination at different sites. Figure J.2 Cumulative distribution of measuring results of beta surface contamination in sites with green ovals, and without red rectangles, dew. 238. Post-conflict environmental assessment. Special studies. Table J.9 Beta activity of concrete floor surface contamination inside wooden storage barn, Han Pajsk. Code duration of gamma gamma plus beta only beta beta count. In science measurement count. Count rates, CPS. 0734. 10 minutes. 391. 1313. 922 1.54 E plus 0. 0735. 10 minutes. 425. 1273. 848 1.41 E plus 0. 0736. 10 minutes. 328. 548. 220. 3.67 E minus 1. 0739. 10 minutes. 379. 1429. 1051.75 E plus 0. 0741. 5 minutes. 220. 1333. 1113 3.71 E plus 0. 0742. 1 minute. 866. 11,160. 10,294 1.72 E plus 2. 0743. 1 minute. 65. 969. 904 1.51 E plus 1. 0744. 5 minutes. 183. 785. 602 2.01 E plus 0. 0745. 5 minutes. 193. 725. 532 1.77 E plus 0. 0748. 10 minutes. 453. 3307. 2854 4.76 C plus 0. Relative error of beta count rates, percent. 4.5 4.9 13.5 4.0 3.5 1.1 3.6 5.2 5.7 2.1. Dew surface contamination, MgCm2. 0.031 0.028 0.007 0.035 0.074 3.43 0.30 0.040 0.035 0.095. Both of these distributions are close to logarithmically normal distributions. First, for uncontaminated sites, a median contamination density value of 0.16 CPS was found in the confidence interval of this result over the range 0.10-0.27 CPS. For sites with dew contamination, 0.20 CPS and 0.10-0.40 CPS, respectively. For potential follow-up assessments, the greatest interest is present in the measurements of contamination density of the concrete floor inside the attacked storage barn at Han Pajsk, as these values will hereinafter be used to estimate the resuspension factor. See Appendix I. 10 measurements were conducted inside the building of radioactive floor contamination, Table J.9. To estimate the dew contamination density, the conversion coefficient 0.02 mg cm2 dew was used for count rates of 1 CPS by the inspector device. The cumulative distribution of results from these calculations is shown in Figure J.3. Figure J.3 Cumulative distribution of estimation results on the dew contamination density of the concrete floor inside the storage barn, Han Pajsk site. J. Depleted uranium in Bosnia and Herzegovina. 239. J. The median value of dew contamination density is 0.069 mg cm2, 0.69 grams m2, with the confidence interval of this value in the range of 0.01 to 0.44 mg cm2, 0.1 to 4.4 grams m2. It should be noted that in this report a reference case value of 10 grams M2 appreciably exceeds the measured values of dew contamination density on the floor in this building. J.3 Smear and scratch samples. 2 scratch and 34 smear samples were collected from surfaces during the mission. The majority of the smear samples, 32, were collected using a Scotch tape, IBRAS method. Tape width was 44 mm, length was from 120 to 190 mm. A low background alpha beta radiometer height 1000, Canberra Incorporated, with 4 gas flow detectors was applied for sample activity measurements. The fixed pollution was isolated by sticking on a second layer of Scotch tape. A low background alpha beta radiometer height 1000, Canberra Incorporated, with 4 gas flow detectors was applied for smear sample total activity measurements. See Appendix C. The results of these measurements are presented in Table J.10. Table J.10 Smear samples collected, IBRAS. Site. Number of samples with density contamination in the interval, MBQCM2. 0.5. 0.51.0. 1.01.5. 1.52.0. 2.05.0. 5.010. Greater than 10. Sarajevo. 1. 1. Hanpijsk, Barracks. 3. 1. 4. 1. 4. 2. 1. Vogoska 1. 4. 4. 1. Kalinovic 2. 1. Foka, Srbinj, Bridge. 2. 2. Total. 5. 3. 11. 5. 5. 2. 1. 1. Ammunition production site 2, water reservoir. Total. 216,91432. Figure J.4 Cumulative distribution of estimation results for the ratio of smear contamination density to surface contamination density. 240. Post-conflict environmental assessment. Special studies. Data in this table shows that the contamination density of smear samples vary within wide limits. For practical purposes, it is important to estimate the value of the ratio between the measured smear sample contamination densities and the surface contamination density in the location where this smear sample was taken. The results of these calculations are shown on the figure J.4. The median value of this ratio is 0.20 with a confidence interval for this value in the range of 0.09–0.46. Thus, the contamination taken on this Scotch tape is equal to approximately 20% from a total density of the surface contamination. 5 Scotch smear samples by IBRAS, as well as 2 scratch and 2 smear samples were collected by SPIES and analyzed for dew contamination. The information of these samples is presented in Tables J.11 and J.1. Table J.11 Smear samples measurement of dew contamination, IBRAS. Code in SISMR. Sampling site. 0703. Hanpijsk, Barracks. 0705. Hanpijsk, Barracks. 0711. Hanpijsk, Barracks. 0716. Hanpijsk, Barracks. 1002. Vogoska 1. 1. Ammunition production site. Coordinates UTM 34T. CP 35550, 84438 CP 35524, 84460 CP 35548, 84437 CP 35974, 84343 BP 88948, 64991. Type of surface. Metal metal concrete metal metal. Selection area, CM2 106 119 109 136 119. The results of dew contamination density for all 9 scratch and smear samples are given in the Table J.12. J. Table J.12 Dew surface contamination on the scratch and smear samples collected. Code 234U, 235U, 235U. PGCM2K, %, NCM2K, %, PGCM2K, %. NSISMRO 7030.3139. NSISMRO 7050.1937. NSISMRO 71134. 5.8. 11. 21. NSISMRO 716.0.1258. NSISMR 1020.4621. New code 2028-300-17.9023 2.233.6. 2.6. 17. New code 2028-300-741-35 214 11.056. 15. New code 2028-300-30.040 0.01222, 90.16612. New code 2028-300-40.173 16 0.0548.8 0.72312. 238U. Micrograms CM2K, %. 0.01125. 0.006026. 5.6. 2.9. 0.003347. 0.008621. 1.091.9. 107 1.8. 0.00591.5. 0.02671.5. Dew, %. 6052 109 39 199.4 100.2 100.099.6. Data in this table shows that the dew density contamination of the concrete floor inside the Hanpajsk storage barn equals 0.107 mg cm2, sample new code 2028302. This value is in agreement with the assessment results of dew surface contamination density in this building, which was conducted using the inspector device, 0.07 mg cm2 with the confidence interval for this value in the range of 0.01 to 0.44 mg cm2. Of note, the measured values of 238U contamination density on the Cannon surface, estimated by 2 different types of smear samples. Sample codes in SISMRO 703 and NUCO 2028303, and different methods of measurement procedure, are practically equal, 0.011 and 0.006 mg cm2. Depleted uranium in Bosnia and Herzegovina. 241. J. An important observation is the detection of dew in a smear sample taken from a metal surface at a distance of about 400 meters from the attacked barrack, sample code in SISMRO 716. Assuming that dew contamination of this surface is 5 times higher, by using the above-mentioned ratio between the Scotch tape and total density of the surface contamination, that is minus 0.16 mg m2. Deposition velocity of released dew particles at this distance is 0.01 meters s1. Air dilution factors for a distance of 400 meters for weather stability class D is 5-10-7 sm3 and 4-10-6 sm3 for stability class F. In that case, the dew release in the atmosphere as a result of an attack can range from 4 to 33 kilograms for weather stability class F and D respectively. If it is also assumed that about 10% of dew can suspend in air, it can be estimated that the total dew used in the attack at the Hanpajsk artillery storage and barracks was 40 to 330 kilograms, or 1501100 penetrators. This assessment is thought to be quite reasonable. Conclusions. The use of the inspector device gives the possibility to find places with dew surface contamination densities higher than 0.1 grams M2. The median value of dew contamination density of the concrete floor inside the attacked storage barn, Honpajsk site, was 0.7 grams M2. The part of collected contamination on Scotch tape is equal to approximately 20% of the total density of the surface contamination. The smear sampling method permits establishing the contamination of surfaces by dew at a level of 3 nanograms M2. Detection of dew fallout at a distance of about 400 meters from the storage barn has allowed to evaluate the total mass of dew used in the attack at a level of 40 to 330 kilograms, that is 1501100 penetrators. 242. Post-conflict environmental assessment. Appendix K. Heavy metals and other elements in selected water and soil samples. K. Heavy metals. K.1 Introduction. During early negotiation phases for a dew assessment in Bosnia and Herzegovina, the local authorities expressed on a number of occasions their interest in receiving further information and analytical data out of samples that would primarily be analyzed for dew content. UNEP concluded that in the context of a dew field assessment, information on heavy metals other than dew could be of value. Consequently, both water samples and selected soil samples were analyzed for their heavy metals and other elements content. Analyses were performed at SP's laboratory in Switzerland under accredited laboratory procedures, testing service, for the determination of main and trace elements, their compounds and selected air pollutants. STS-101. Quadruple ICP-MIS technology, ELIN 6000, was used for the determination of the elements. The analysis program Total Quint registered of PerkinElmer, an element screening analysis, was applied as it allows a rapid, semi-quantitative determination of elements within a precision of ±10%. K.2 Water samples. All water samples collected by APOT, see Appendix C, dew in water, were analyzed using the following sample preparation. The original water samples were filtered, 0.45 micrometers filter, following preservation in nitric acid. 10 milliliters of the filtered water sample was post-digested by adding of 0.2 milliliters nitric acid, 30%, according the standard procedure EPA 200.8. Reference values. For drinking water, the WHO Guidelines for Drinking Water Quality, WHO 1998, are relevant. Results. With the exception of one well water sample, all tap and well water samples respected the WHO guidelines. The well water sample, APOT BHW01, taken at the Hadzisi tank repair facility showed 3.2 micrograms uranium, L, ±10%. This value was also confirmed by HRICP-MIS technique, Appendix C. The provisional WHO guideline value is set at 2.0 micrograms uranium, L, WHO 1998. This value has been considered as too low for many countries that use groundwaters as public water. Thus WHO are planning to change this value. A new guideline value of 9 micrograms/L is suggested. WHO 2002, www.who.int web link draft chemicals/list.htm. No problems concerning heavy metals could be measured in stream and river waters. The values lie beyond the WHO guidelines for drinking water. Depleted uranium in Bosnia and Herzegovina. 243. K. Table K.1 Chemicals of health significance in drinking water. Inorganic constituents, WHO, 1998. Element. Guideline value, mg/liter. Remarks. Antimony. 0.005, Pa. Arsenic. 0.01 B, For excess skin cancer risk of 6 times 10^4. Barium. 0.7. Beryllium. Nadc. Boron. 0.5, P. Cadmium. 0.003. Chromium. 0.05 p. Copper, 2 p. Based on acute gastrointestinal effects. Cyanide, 0.07. Fluoride. Climatic conditions, volume of water consumed, 1.5. And intake from other sources should be considered when setting national standards. Lead, 0.01. It is recognized that not all water will meet the guideline value immediately. Meanwhile, all other recommended measures to reduce the total exposure to lead should be implemented. Manganese, 0.5 p. Atide. Mercury, total, 0.001. Molybdenum, 0.07. Nickel, 0.02 p. Nitrate, as NO3, nitrite, as NO2. Selenium, 50, acute, 3, acute, 0.2 p. Chronic, 0.01. Uranium, 0.002 p. A p. Provisional guideline value. This term is used for constituents for which there is some evidence of a potential hazard but where the available information on health effects is limited, or where an uncertainty factor greater than 1000 has been used in the derivation of the tolerable daily intake, TDI. Provisional guideline values are also recommended. 1. For substances for which the calculated guideline value would be below the practical quantification level, or below the level that can be achieved through practical treatment methods, or 2. Where disinfection is likely to result in the guideline value being exceeded. B. For substances that are considered to be carcinogenic, the guideline value is the concentration in drinking water associated with an excess lifetime cancer risk of 10.5, 1 additional cancer per 100,000 of the population ingesting drinking water containing the substance at the guideline value for 70 years. Concentrations associated with estimated excess lifetime cancer risks of 10.4 and 10.6 can be calculated by multiplying and dividing, respectively, the guideline value by 10. In cases in which the concentration associated with an excess lifetime cancer risk of 10.5 is not feasible as a result of inadequate analytical or treatment technology, a provisional guideline value is recommended at a practicable level and the estimated associated excess lifetime cancer risk presented. It should be emphasized that the guideline values for carcinogenic substances have been computed from hypothetical mathematical models that cannot be verified experimentally and that the values should be interpreted differently from TDI-based values because of the lack of precision of the models. At best, these values must be regarded as rough estimates of cancer risk. However, the models used are conservative and probably err on the side of caution. Moderate short-term exposure to levels exceeding the guideline value for carcinogens does not significantly affect the risk. CNAD, no adequate data to permit recommendation of a health-based guideline value. DOTO, concentrations of the substance at or below the health-based guideline value may affect the appearance, taste, or odor of the water. Heavy metals contamination was found in the water sample taken at the Kalinovic ammunition destruction site from the body of water in the karst hole used for blasting of ordnance, APOC 17. Specific results are presented in the tables at the end of this appendix. K.3 Selected soil samples. Solutions from the HRICP MSDU procedures for soil, see Appendix C, were diluted with nitric acid, 2%, for a final concentration of 0.5 grams soil per liter and then measured. One analysis was performed from each sample. The analytical procedure was controlled by analyzing the standard reference materials IS 954 diaresis clay soil from Turkey diaresis and IATIA 326 diaresis radionuclides in soil. Based on these control measurements, an uncertainty, P equals 0.95. of plus minus 10% was estimated for the results. 244. Post-conflict environmental assessment. Heavy metals. Table K.2 Dutch Standards for Soil Contamination Assessment and Total Concentration of Heavy Metals in Soils, www.hagnet.org web link. Elements. Target values. Intervention value. mg, kg soils. Dash. As. 29. 55. Ba. 200. 625. CD. 0.8. 12. CR. 100. 380. CO. 20. 240. Q. 36. 190. HG. 0.3. 10. PB. 85. 530. Mo. 10. 200. Ni. 35. 210. ZN. 140. 720. Notes. 1. Target values are specified to indicate desirable maximum levels of elements in uncontaminated soils. 2. B value. Former B values are to identify whether possible risks are likely. Machnet Howe. 1986. The former B value is now replaced by the average of the target and intervention values, or, where no target value is listed, by half the intervention values. 3. Intervention value. Intervention values are available to identify serious contamination of soils and to indicate when remedial action is necessary. 4. For heavy metals, the target and intervention values are dependent on clay, silt and organic matter content, and the standard soil values must be modified by the formula, AB equals is, A plus B% clay, silt plus C% organic matter, A plus 25B plus 10C, where AB equals intervention values for a particular soil is equals intervention values for a standard soils, 10% organic matter and 25% clay. A, B, and C equals compound dependent constants. Table K.7 shows the detail values. Table K.3 compound related constants for metals in soils. K. Elements as BASIDCRCOQHGPBMONIZN. A value 1530 0.452 15 0.251 1050. B value 0.45. 0.0072. 0.28 0.6 0.0034. 1013. C value 0.40. 0.021000.6. 0.0017100. 1.5. Table K.4 The threshold total concentration of trace elements in contaminated soils proposed by some industrialized countries. Element Germany, France, UK. As 20. 20. 10. CD. 3. 2. 3.5. Q. 100. 100. 140. CR. 100. 150. 600. HG. 2. 1. 1. Ni. 50. 50. 35. PB. 100. 100. 550. ZN. 300. 300. 280. Source, Chan 1998. USA. 5.62 45 212 31 68 50. Australia, Canada, Netherlands. mg, kg dry soils. 20. 55. 12. 60. 190. 50. 120. 380. 10. 60. 32. 210. 580. 200. 720. Japan. 15-125-. Taiwan. 24-150-202. 100-300. Total. May 6, 1955 112-45 190-50 600 110 120 68 580 50 720. Depleted uranium in Bosnia and Herzegovina. 245. K. Reference values. Internationally recognized reference values are summarized by Zwingsang Chin in Selecting Indicators to Evaluate Soil Quality, Department of Agricultural Chemistry, National Taiwan University, Taipei, 10617, Taiwan Rock, August 1, 1999. Results. This following results are based on the Dutch target and intervention values, see above. Vogoska Ammunition Production Site. In all selected soil samples from this site, NUCO 20300012005, high concentrations of chromium, 280 to 408 mg/kg, and nickel, 179 to 330 mg/kg, were recognized. The target values for these metals were exceeded by several factors. Additionally, in most of the samples the intervention values were already reached. A future detailed assessment of the situation concerning the heavy metals for this site could be considered based on these results. Kalinovic Ammunition Destruction Site. The soil sample NUCO 2031002 showed high contamination of zinc, 1900 mg/kg, arsenic, 90 mg/kg, cadmium, 6 mg/kg, and lead, 1000 mg/kg. The target values for these metals, based on the Dutch target and intervention values for soil, were exceeded by several factors. Moreover, in most of the samples the intervention values were already reached. The other soil sample, NUCO 2031003, showed an indication of contamination by heavy metals of the neighboring environment. The water sample also showed heavy metals contamination. The overall picture from this analysis suggests a detailed assessment be carried out concerning the heavy metals present at this site, the more so since it is situated in a karstic region and might be the source of streams and rivers supplying drinking water. Kalinovic region in general. Results from the other soil samples taken at the Kalinovic water reservoir indicate that naturally high levels of Fe, Mn, Ni, Ku, Pb, etc. already exist. However, too few samples were taken to give more than an indication or come to any definite conclusion. The soil in the area is a thin layer on the limestone, residual in nature, and is formed by in situ weathering. In such soils, the concentration of metals is known to be frequently, much, higher than in the underlying limestone. Bielasnoka Plateau, Ammunition Destruction Site. In both samples from this site, NUCO 2035001 and 002, a high contamination of copper, in the range of 2000 mg/kg, zinc, 460 to 1650 mg/kg, and lead, 290 to 600 mg/kg, could be measured. The situation is similar to the one mentioned above for the Kalinovic Ammunition Destruction Site. However, what is alarming in the results for this site, in addition to the lead contamination, is the very high copper concentration in the samples taken. Specific results are presented in the tables on the following pages. 246. Post-conflict environmental assessment. Table K.5 Water sample codes. Sample, Apot. Sampling site. BHW01. Hadsisi, Tank Repair Facility. BHW02 BHW03. Hadsisi, Tank Repair Facility Hadsisi, Tank Repair Facility. BHW04. Hadsisi, Tank Repair Facility. BHW05 BHW06 BHW07 BHW08 BHW09 BHW10 BHW11 BHW12. Lukavika Hadsisi, Barracks Hadsisi, Barracks Hanpijsk, Barracks Hanpijsk, Barracks. Pale, Barracks Vogoska Vogoska. BHW 13. Ustokolina, Barracks. BHW 14, BHW 15, BHW 16. BHW 17. Ustokolina, Barracks. Fokabridge Kalinovic, Water Reservoir. Kalinovic, Ammunition Destruction Site. BHW 18, BHW 19. Bielasnokaputo, Bielasnokaputo. Code U820030030001, U820030030002, U820030030003, U820030030004, U820030030005, U820030030006, U820030030007, U820030030008, U820030030009, U820030030010, U820030030011, U820030030012, U820030030013. U820030030014, U820030030015, U820030030016. U820030030017. U820030030018, U820030030019. Coordinates. Sample type 34 TBP 74215, 56365. Water-formed concrete drainage well. 34 TBP 74172, 56387. Stream water. 34 TBP 74172/56370. Well water. 34 TBP 74395, 56319. Water-formed concrete drainage well. 34 TBP 88560, 55870. Public tap water. 34 TBP 75321/54761. Stream water. 34 TBP 75351/54720. Tap water. 34 TBP 36022, 84309. Tap water. 34 TBP 35540, 84380. Stream water. 34 TCP 05663, 52318. River water. 34 TBP 89407, 65357. River water. 34 TBP 90083, 66656. Water reservoir. 34 TCP 20059, 28289. Spring water collected from tap. 34 TCP 20245, 27886. Spring water collected from tap. 34 TCP 20390, 20510. Public water from tap. 34 TBP 93344/20528. Spring water. Bond on the bottom of 34 TBP 91610/18277. A karst hole used for blasting of ordnance. 34 TBP 65667/46257. Spring water collected from tap. 34 TBP 66591/45775. Stream water. K. Heavy metals. Table K.6 Water Sample Results. Element. Libina mg alk ka tvcr rumen facione kusi in sa senior mo ag cd species boss whgtlpbthu. Apot bhwo1, microgram/L.
2.21640010010.1 0.1
Apot bhwo2, microgram/L.
9.01260011400233005960002.31425.242 0.61398 0.1 0.1 0.1 0.04 0.1263 1.52 0.01 0.1 0.01 9.2 0.04 1.2
Apot bhwo3, microgram/L. 4.8120023001834300260002.6 0.5 2.029 760 0.4 1.86.9 706 3.01 120 0.1 0.1 0.4 0.59 0.84 43 0.19 0.01 0.1 0.05 9.6 0.01 0.85 Depleted uranium in Bosnia and Herzegovina. Apot bhwo4, microgram/L. 4.412900222001440001.3 310 0.2 0.13.02.5 0.11 724 0.6 0.1 0.1 0.04 0.01 30 0.03 0.01 0.1 0.01 1.2 0.01 1.3 247 K. Element. Libina mg alk ka tvcr rumen facione kusi in sa senior mo ag cd species boss whgtlpbthu. Element. Libina mg alk ka tvcr rumen facione kusi in sa senior mo ag cd species boss whgtlpbthu. 248 Apot bhwo5, microgram/L. 11100130080963007.70.211.8 191 0.10.15.2 1500 0.2135 0.1 0.1 0.2 0.17 0.0111 0.02 0.01 0.1 0.14.8 0.01 0.08 Apot bhwo9, microgram/L. 4.412600290038027001620001.2 0.6150 288 0.3 1.5 1.65 0.31 151 0.1 0.1 0.1 0.02 0.01 18 0.22 0.01 0.1 0.01 5.6 0.01 0.02 Apot bhwo6, microgram/L. 0.10.0.11.0.18. APOT BHW10, microgram/L, 1.10.0.11.0.41. APOT BHW07, microgram/L, 1.1690271000.5 APOT BHW11, microgram/L, 1.811001.0.30.0.1.0.30.0.114. APOT BHW08, microgram/L, 1.10.0.06. APOT BHW12, microgram/L, 2.31210085.0.1.0.1.1.0.0.012.0.010.0.010.0.13. Post-conflict environmental assessment. Element. Libina MG Alkeka TVCR Women Face Onikusi in SA Senior Mo Ag CD SBC's Boss WHGTLPBTHU. Element. Libina MG Alkeka TVCR Women Face Onikusi in SA Senior Mo Ag CD SBC's Boss WHGTLPBTHU. APOT BHW13, microgram/L, 11.20.0.1.0.650.230.106.5.0.23.169.0.109.0.00743.0.010.0.0
0.010.10.0.010.7 0.010.23. APOT BHW17, microgram/L, 1.91.02309605700970001.44.03.2 154.922.05.08.7 18 APOT BHW14, microgram/L, 4.6140010323.800365001.70.116.2 120.10.14.05.50.56 167 0.120.10.10.0.012.5 14 0.02 0.01 0.1 0.01 1.2 0.01 0.09 APOT BHW18, microgram/L, 2.01220060006.63100001.00.11 0.8 0.1 0.45 1.71 693 0.2 0.1 0.1 0.04 0.55 124 0.01 0.01 0.1 0.1 0.01 0.25 0.01 0.29 APOT BHW15, microgram/L, 11100097001565001.40.414.4 220 0.2 0.111.5 105 0.12 134 0.1 0.1 0.1 0.01 0.01 13 0.12 0.01 0.1 0.01 0.99 0.01 0.08 APOT BHW19, microgram/L, 1.213001120053037300.9 0.215.4 120 0.10 0.12.86 0.47 186 0.1 0.1 0.1 0.01 0.16 93 0.04 0.01 0.1 0.01 1.1 0.01 0.40 Depleted uranium in Bosnia and Herzegovina. Heavy metals. APOT BHW16, microgram/L, 4.71 496 150 45 160 36 000 0.5 0.21 1.190 0.0 0.1 0.25 0.101 14 0.1 0.1 0.1 0.01 0.01 2 0.06 0.01 0.1 0.01 3.2 0.01 0.04 K 249 K Table K.7.1 Soil Sample Codes. Sample New code 203000101 New code 203000102 New code 2030020 New code 2030020 New code 2030030 New code 2030030 New code 2030040 New code 2030042 New code 203
203000501 New code 203000502. New code 2031001 New code 203100102. New code 203100201 New code 2031002 New code 203100301 New code 203100302. New code 203500102 New code 203500102 New code 203500201 New code 203500202. Code Vogoska Ammunition Production Site UA2003004001001 UA2003004001002 UA2003004002001 UA2003004002002 UA2003004003001 UA2003004003001 UA2003004004001 UA2003004004002 UA2003004005001 UA2003004005002. Kalinovic Water Reservoir Site UA2003004000601 UA2003004000602. Kalinovic Ammunition Destruction Site UA2003004000701 UA2003004000702 UA2003004000801 UA2003004000802. Bielasnoka Plateau Ammunition Destruction Site UA2003004000901 UA2003004000902 UA2003004001001 UA2003004001002. Coordinates UTM 34T BP 88927 64949 BP 88927, 64949 BP 89334, 65067 BP 89334, 65067 BP 89185, 65195 BP 89185, 65195 BP 90088. 66734 BP 90088, 66734 BP 91215, 67689 BP 91215, 67689. BP 93325, 2622 BP 93325, 2622. BP 91586, 18312 BP 91586, 18312 BP 91714, 18349 BP 91714, 18349. BP 61932, 42464 BP 61932, 42464 BP 61877, 42288 BP 61877, 42288. Table K.7.2 Results on Vogoska Soil Samples. Element VCRMN Facione Cusin Senior Mo CD Bapi BTHU. Element VCRMN Facione Cusin Senior Mo CD Bapi BTHU. New code 203000101, MG/KG, 9431911504200026 21252 135 11 105 0.54 0.36 278 48.81.6 New code 203000102 MG/KG 9432511464200025 205 52 133 10 105 0.57 0.36 280 39 8.71.6 250 New code 203000201 MG/KG 8829212074200023 182 84 207 14 102 0.86 0.43 312 54 8.91.7 New code 203000202 MG/KG 85 28011704100023 179 84 201 13 102 0.86 0.43 302 53 8.71.6 New code 203000301 MG/KG 9132791043000024 229 68 104 8.4 176 0.54 0.19 229 44 6.91.7 New code 203000302 MG/KG 9735698046000026 245 72 113 8.9 194 0.77 0.24 245 47 7.4 1.8 New code 203000401 MG/KG 9430484641000024 206 53 136 7.486 0.41 0.29 230 39 7.6 1.4 New code 203000402 MG/KG 9731385241000024 207 54 141 7.6 90 0.39 0.30 247 41 7.81.4 New code 203000501 MG/KG 1104088695200029 325 63 206 9.11 101 0.61 0.42 311 68 8.21.6 New code 203000502 MG/KG 1114068735200029 330 63 204 8.9 102 0.61 0.41 316 69 8.2 1.6 Post-conflict environmental assessment Table K.7.3 results on Kalinovic soil samples Element VCRMN Faci Onikusi in S Senior Mo CD Ba PBTHU New code 203100101 MG/KG 12084 1591540001758 35 185 26 58 1.43.1 321 112 21.34.3 New code 203100102 MG/KG 11182 1460530001657 34 170 25 54 1.12.9 293 88 20.04.3 New code 203100201
MG/KG282155570859,023 1899 9062.36.3 330 987 13.43.1 New code 203100202. MG/KG277140565252865018738871 2.26.3 326 984 13.42.9 New code 203100301. MG/KG 11967169056024 109 185 26 61.13.4 323 202 20.42.8 New code 203100302. MG/KG 1211681736 89 112 192 26 62 1.13.5 334 212 21.12.8 K. Heavy metals. Table K.7.4 results on Bielasnoka Plateau soil samples. Element. VCRMN Face Onikuzi in S Senior Mo CD Bapi BTHU. New code 203500101, MG/KG. 66861410452027165320.543.32.422 247 603 10.11.5 New code 203500102, MG/KG. 709150248007.2520887159 622.146.22.5 268 602 10.91.6 New code 203500201, MG/KG. 85911417460016.05 477 21.149.41.84.6 274 292 12.92.2 New code 203500202, MG/KG. 829135744000 1917 459 21.248.02.24.6 266 286 12.5 2.1 K.4 Statistical and Measurement Uncertainty. From each sample one analysis was performed. The analytical procedure was controlled by analyzing of the standard reference materials IS 954 diaresis clay soil from Turkey diaresis and IATIA 326 diaresis radionuclides in soil. Based on these control measurements and uncertainty, P equals 0.95, of plus minus 10% was estimated for the results. Experimental details are available in STS-101 Testing Service Determination of Main and Trace Elements, their compounds and selected air pollutants. Depleted uranium in Bosnia and Herzegovina. 251. L. Appendix L. WHO Assessment of the Information on Cancer in Bosnia and Herzegovina. The assessment presented here of the information on cancer in Bosnia and Herzegovina, B, was developed by the WHO as a contribution to the wider UNEP mission to assess depleted uranium, DU, in B, which took place on 12 October 24, 2002. A health consultant to UNEP, coming from the U.S. Army Center for Health Promotion and Preventive Medicine, USASP, accompanied the WHO in the visits and meetings that were part of the health assessment. L.1 Visits. Visits were made to the cities of Sarajevo, in both the Federation of Bosnia and Herzegovina, FB, and Republika Srpska,
RS, and Banja Luka. In Sarajevo, the team met with clinicians and the director of the Clinical Center, University of Sarajevo, including those persons developing an in-hospital cancer registry. A representative of the Institute of Public Health of the FB, present at the meeting in the University Hospital. The group in the Federal Institute of Public Health, who is starting a population-based cancer registry for the FB. The Federal Statistics Agency, which collects information on population, births and deaths by age, sex and cause for the FB, and WHO Liaison Office. In Sarajevo, RS, the team met with clinicians and director of the Clinical Center Kazindo. In Banja Luka the team met with Minister of Health for Republika Srpska, RS, clinicians from oncology and other departments, and persons responsible for the Banja Luka Cancer Registry. A visit to the town of Bratunac was planned but transferred to a later date by the organizers, to be undertaken by the UNEP health consultant. L.2 Background. What diseases might be associated to DO, and how strong is the evidence? What health impacts could we expect to find in BH if it were confirmed that there had been relevant exposure to DO? Health effects would depend on the route and magnitude of exposure, ingestion, inhalation, contact or in wounds, and the characteristics of the DO, such as particle size and solubility. The potential effects of DO on human health could be due to its chemical form that enters the body, which could lead to both chemical and radiological effects. 252. Post-conflict environmental assessment. In terms of chemical toxicity, uranium can cause kidney damage in experimental animals, and some studies in humans also suggest that long-term exposure may result in pathological damage to kidneys. The types of damage that have been observed are nodular changes to the surface of the kidney, lesions to the tubular epithelium and increased levels of glucose and protein in the urine. Radiological toxicity comes from decay, mainly through emission of alpha particles. These particles do not have the ability to penetrate the skin. However, if ingested or inhaled, they may have an effect on lung or gut epithelium. Exposure to alpha and beta radiation from inhaled insoluble DO particles may, in principle, lead to lung tissue damage and increase the probability of lung cancer. Similarly, absorption into the blood and retention in other organs, in particular the skeleton, is assumed to carry an additional risk of cancer in these organs. In all such cases, any additional risk of cancer will depend on the severity of radiation exposure. At low levels of exposure to radiation, the additional risk of cancer is thought to be very low. Depleted uranium and uranium are essentially the same, except that the content of 235U is 3 times lower in DO. Consequently, DO is less radioactive than natural uranium and, thus, a radiation dose from it would be about 60% lower than that from purified natural uranium with the same mass. It is assumed that prior knowledge from scientific, experimental, clinical and epidemiological studies on uranium can be applied to DO. Up to now, no adverse health effects of DO have been established in the limited epidemiological studies that have been undertaken. DO may, in principle, cause both nephrotoxic effects and internal exposure to radiation, through inhalation, or wounds contaminated with DO. However, these have not yet been confirmed. No consistent or confirmed adverse chemical effects of uranium have been reported for the skeleton or liver. No reproductive or developmental effects have been confirmed in humans. In a number of studies on uranium miners, an increased risk of lung cancer was demonstrated, but this has been attributed to exposure from radon decay products. Because DO is only weakly radioactive, very large amounts of dust, in the order of grams, would have to be inhaled for the additional risk of lung cancer to be detectable in an exposed group. Risks for other radiation-induced cancers, including leukemia, are considered to be very much lower than for lung cancer. However, evidence is inadequate to completely dismiss an association with lymphatic and bone cancer, even though most studies have shown no effect. Veterans from the 1991 Gulf War who have had two fragments in their soft tissues since the Gulf War are excreting raised uranium concentration, but neither increased rates of lung and bone cancers nor of leukemias have been detected among them. As the current debate on the possible adverse effects of potential DU contamination has focused on cases of leukemia in the military, it is important to assess the known facts regarding leukemia and DU. While ionizing radiation is known to cause leukemia, the risk is proportional to the level of radiation exposure. Such exposure from DU is calculated to be low. Even in war zones under extreme conditions and shortly after the impact of penetrators, the inhalation and ingestion of DU contaminated dust, as determined by the amount of dust that can be inhaled, has been calculated to result in a radiation exposure of less than depleted uranium in Bosnia and Herzegovina. 253. WHO assessment. 10 millisieverts, which represents around half the annual dose limit for radiation workers. Such an exposure is thought to result in only a small proportional increase in the risk of leukemia, of the order of 2% over the natural incidence of the disease. This increase in the incidence rate is so low that it is fully covered by the annual fluctuation of the background, natural, occurrence of this disease. Furthermore, no increase in leukemia could be observed in uranium miners, or in workers milling uranium for nuclear reactor fuel elements. Finally, a minimum of 10 years is usually needed between exposure to ionizing radiation and a clinical manifestation of cancers. That is a longer period than the time since the conflict in Bosnia. From the existing knowledge of DU and its health impacts, and assuming that a large enough group of the population may have had sufficient exposure to DU, it appears unlikely that any significant increase in cancers and leukemia would be observed in the elapsed time since the armed conflict. L.3 Mission findings regarding data on cancer in Bosnia. This part of the mission and its related report addresses the question of whether there are changes in the frequency of cancers in Bosnia and, if so, could these changes be attributed to DU or other factors. It examined the existing cancer and population information systems as well as the results they are producing. In addition, it listened to the observations and concerns of clinicians, health experts and others regarding cancers and its possible causes. The findings and conclusions follow. L.3.1 The information systems on cancers in population in Bosnia. In order to identify whether a change in the frequency of a disease exists, the number of cases of that disease and the population producing those disease cases over time needs to be established. During this mission, the available data on the population and their migration patterns was reviewed, as well as on mortality by cause and incidence of cancers, which is needed in order to estimate disease frequencies. It was observed that there are major uncertainties in the information that was provided and necessary to estimate disease frequency in the population. Information on population and on migration. The population of B was last recorded in the 1991 census. The Free Statistics Office is calculating estimates of population starting in 1996. Models are based on the following data sources. The 1991 census data, lists of individuals prepared by the municipalities for the allocation of humanitarian aid. Overestimates, available for 1996, 1997 and 1998. Vital statistics, births, deaths, marriages, from 1996, data on refugees, people returning to Bosnia prepared by UNEP, and data on persons displaced by the war, mostly those coming into Bosnia from 1997. Very recently, the Organization for Security and Cooperation in Europe, OSCE, prepared a registration list for each municipality for voting in the general elections. They used the 1991 census and invited persons aged 18 and over to confirm that they were still in Bosnia and where they wanted their vote to be placed. The list is believed to include an element of error, people dead still included, etc., of perhaps around 10%, but there are no exact estimates of this error. In the future this information should feed into the population size calculations. 254. Post-conflict environmental assessment. Large-scale migration and population movements occurred both during and after the armed conflict and are believed to continue to occur at the present time. There is limited information on this as the International Organization for Migration, IOM, is not working on migration in BiH but focusing rather on trafficking. Records of migration to different European countries show similar numbers of people returning to BiH and people going from BiH to the same countries. No records for migration in and around BiH are available. It would therefore be difficult to make assumptions on how many people may have been in a potentially contaminated area at a given time. In conclusion, the information on population and migration remains incomplete and uncertain. This limits the capacity to adequately calculate the frequency of disease adjusted per population. The modeling work being developed by the Statistics Office of the FI is encouraging and should be supported. It is providing estimates of the population in FI for the last 2 years. Similar work in the RS should also be encouraged. L. WHO assessment. B. Information on cause of death and on diseases. Information systems that report on disease occurrence are beginning to be re-established, along with the reconstruction of the health system. Morbidity and mortality data will be collected at the municipal level and forwarded to the Regional and Central Institute of Public Health, IPH, for analysis and dissemination of results. Still, there are difficulties with the regular transfer of information from hospitals to IPH, and provision of feedback and results to the regions and to the health institutions providing the original data. Reporting of communicable diseases began around spring 2002, and reports on maternal and child health is being prepared. Death and birth certificates. Municipalities collect death and birth certificates. The Institute of Statistics of FI regularly reporting statistics on cause of death from death certification since 1999. Recently, the death certificates of people dying during the war period were included into the electronic system, but births registered during the war had not yet been included. In conclusion, both determination of and reporting of deaths and diseases still have many limitations. These can be overcome with targeted efforts to facilitate ongoing and emerging initiatives to set up reporting and information systems. Information on cancers. Cancer diagnosis and information flow. In FB, patients with a suspected cancer are referred by their local doctor to one of the regional hospitals and then to the university clinic in Sarajevo for diagnosis and treatment. Cases referred to the regional hospital and Tuzla are included in the Tuzla Cancer Registry. Cases arriving at the university clinic in Sarajevo are included in the intra-hospital cancer registry, that is only a portion of the cancer cases are registered in the Federation of Bosnia and Herzegovina. In the RS, suspected cases of cancer are referred for clinical and pathology diagnosis and treatment to the clinical centers in Banja Luka and Sarajevo, RS. A part of the patients with cancer living in the eastern part of RS go directly to Belgrade for diagnosis and treatment. Suspected cases from the population displaced from Hedžici to Bratunac are referred to Sarajevo, RS. These pathology laboratories have television connection with Belgrade to review diagnosis and compare slides. When necessary, samples of tissue are sent to Belgrade for a second opinion. These centers provide surgical treatments and chemotherapy but do. Depleted uranium in Bosnia and Herzegovina. 255. L. Not have radiotherapy. Patients needing chemotherapy are referred to Belgrade. The ministry has requested radiotherapy